Sorry, Benedetta.
See?
First we have an intro video. After that,
perfetto.
we can start. Thank you very much.
After intro, we can start directly with you.
Okay.
Merhabalar, ben Volkan Demir. Şu an mikrofonum çalışıyor ama ekranım henüz çalışmıyor. Sadece bilgisini vermek istedim eğer.
Tamam hocam.
Evet, video, evet.
Evet, sesiniz güzel geliyor gayet.
Volkan hocam hoş geldiniz.
Merhabalar Süleyman hocam. Çok selamlar, saygılar.
So good morning to everybody and welcome to the first session of the second day of the conference. Today in the program we have one plenary speaker and two invited speakers, so be prepared to hear a lot of interesting research. And I'm very honored to introduce the first speaker of the day, who is Professor Hilmi Volkan Demir. of Bilkent University. He got his PhD and Master of Science degrees in electrical engineering from Stanford University in California, and his bachelor in electrical and electronic engineering from Bilkent University. And presently, he is a professor of the Department of Electrical and Electronics and Engineering and the Department of Physics at Bilkent University. And he is director of the National Nanotechnology Research Center of Turkey. Moreover, he is also professor at the School of Electrical and Electronic Engineering, the School of Physical and Mathematical Science, and the School of Material Science and Engineering at Nanyang Technology University in Singapore, where he is also the founding director of Luminos, the Center of Excellence for Semiconductor Lighting and Displays. He has a very huge career in science. He published over 350 peer-reviewed research articles in major scientific journals, and many of them belong to the Nature journals. He co-authored a textbook on applied nanophotonics published by Cambridge University Press, and he has delivered over 250 invited seminars. Now he is a Springer Nature Series editor of Nanoscience and Nanotechnology, and is sitting on the ACS Photonics editorial board. As a PI, he has contributed to commercialization and licensing of over 10 new enabling technologies, generating over 100 patent applications. And the scientific and entrepreneurship activities resulted in several important international awards. So he is here today to speak about emerging semiconductor nanocrystal optoelectronics from colloidal quantum dots to wells. And I'm very pleased to give you the microphone for your presentation, and thank you very much for joining us.
Well, thank you very much, Dr. Marmirori. It's a very kind introduction. So let me share my screen. I believe you should be able to see the screen at this point. It's most probably coming up.
Yes, we can.
Just a second. I hope you can see the first page.
Perfect, yes.
All right, wonderful. Well, a very good morning to everyone. It's my great pleasure to be here with you today and be part of the UNESCO's International Day of Light. And for that reason, I would like to thank Professor Özçelik, Professor Sönmez, and the whole organizing committee and the crew working behind the scenes for their kind invitation and allowing me to be part of this wonderful celebration. Also, I'd like to congratulate Professor Özçelik and all his colleagues for putting together such a wonderful program. I was able to go through the variety and the range of the talks, which I was impressed. Unfortunately, this week, we also have an event running at UNAM. And as part of my duty, I need to take part in this event. But luckily, we were able to get the timing to work for me to be here today with you. So as the chair pointed out, I'll be talking about our research work on the development of an emerging field. This is semiconductor nanocrystal optoelectronics, which uses these colloidal nanomaterials. And for me, this is indeed a journey, starting with colloidal quantum dots, going all the way most recently to wells. And in this talk, I would like to share with you the most recent developments, where in some cases, we were able to push the limits, and in some situations, we were able to even break some records in terms of material performance or device performance. Once again, I am coming from Bilkent University and UNAM, and at the same time NTU, where we have a MOU for over a decade now. And for that reason, I'm very pleased to acknowledge both institutions. And my team working as a whole in two places. What I will present you today is surely a result of teamwork. And for that reason, I would like to acknowledge our current group members and alumni. And most probably, I'm most proud of our alumni who have graduated over the years and now dispersed both in Turkey and around the world. And 10 of them actually returned back, just like myself, to serve their countries. And they're now quite successful as academicians themselves, my colleagues at these different universities, including AGÜ, Koç University, TOP-ETÜ, Ankara University, Izmir Teknik, and so on. Also, I would like to acknowledge equally our team, and this is Luminous, which is a center of excellence I established at TNTU under this MOU with Kent. And there I'm working with a group of very talented scientists and research fellows and researchers. And for that reason, today, what I'll be presenting is the result of all these efforts. So with that, let me share with you what we do in my research program. This really covers basic research and in certain cases takes it to innovation level, even sometimes deep tech applications. Obviously, as we all know, being in the field, this takes quite a long time. But the good news for us is we can start from materials level and go to devices all the way to systems. This really gives us the whole food chain for us. Indeed, we span both optical frequencies and radio frequencies. This means a lot of room for innovation for us. We basically work in three main research thrusts: semiconductor nanocrystals, which is the topic of today. And as I mentioned, I will motivate you starting with colloidal quantum dots, but then share with you most recent advancements in wells. We work in light generation aspects, harvesting aspects, but today, again, in the interest of my talk's coverage, I will be more focusing on the generation. We look into energy transfer and near field phenomena. We look at coupling, particularly with dielectric and metal nanostructures that act as antennas or metasurfaces. We also make functional composite structures. Of course, we try to do that in a smart way. And several of these efforts have been, as of today, commercialized successfully, and we'd like to push more, if we may, in the coming time. We also take these materials to device level, and we make what we call light engines. These really combine LEDs in different device configurations. We design these light emitting diodes for high brightness in the visible range, but then we push it towards near UV, further deep UV. We also make soft material platforms, including nanocrystals. This could be 2,6 or perovskites. And finally, I will share just with one slide. This is quite recent. We also make chip scale solutions for deep UV, where we use cathodoluminescence, because this is really, really cheap, but quite high performing platform for us. Again, in the interest of time today, I won't touch upon at all, but just to share with you, we also work in the direction of implantable materials. This is more in the line of implantable electronics, where we borrow some ideas in optics and apply to RF. This is more in vivo sensing applications or wireless probes for a number of purposes. With that, just let me share you one slide before I quickly move into the technical part of my talk. This is our recent deep UV technology platform that we developed, and now we work together with Light Lab Sweden, and this is now fully licensed and transferred, and the products are actually available. This is what our chip scale device looks like. This is one we made ourselves fully packaged. This is actually 5 centimeters laterally and sub-centimeter vertically, so we can make it millimeters range. And if you would look at inside, this is what you would see. Actually, inside we have a quality vacuum cavity. This is high integrity cavity integrated with nanowires. These nanowires we grow ourselves, and we actually hermetically seal this whole structure, so it's under vacuum, and we use cathodoluminescence by applying high bias but very, very low current, which means the electrical input power is indeed very low, but then we can do the conversion through cathodoluminescence with high efficiency. We are operating below 280, so around 265, we reach 4% efficiency. This is better than what is possible today commercially with deep UV LEDs, and we believe we will be able to push this further with now new nanomaterials we are in the process of making. Good news here is that with this efficiency, we actually reach the benchmark. This is a germicidal efficiency of what is called log 6. This corresponds to 4 decimals, so it is 99.9999%. And in the community, it is indeed deep UV mercury lamps that can really achieve this level of germicidal efficiency. But for mercury, obviously, it is not environmental friendly, but more importantly, it's quite expensive, bulky, and it doesn't operate well at low temperature or high temperature. Whereas in our case, so this is the operation curve as a function of ambient temperature for the case of mercury lamps, and this is what we can achieve using this technology. So this was just a quick example I want to share. I thought this could be interesting for some because given pandemic these days, low-cost germicidal disinfection is a critical functionality. But what I'd like to carry on is today nanocrystal-based color conversion enrichment. And I'd like to hopefully motivate you that this is an important problem, and there is a major growing market today where nanocrystals with the color technology they provide actually leads the advanced TV market. And but of course, as scientists, we need to ask what is next. And what we see is coming next is for high segment laser-based lighting. And I'd like to tell a little bit about the story of laser-based lighting and motivate you for nanocrystal lasers. So we can do them for spontaneous emission, but then we can, if you want, induce gain, so push into actually amplification and thus lasing. But no matter what we do, colloidal quantum dots, which is a material system being quasi-zero-dimensional with 3-dimensional confinement, actually hits some fundamental barriers. And I'd like to share with you those and how we can address them, changing the system from dots to wells, the wells being atomically flat. This is indeed a new paradigm for us. So I would like to, from this point on, tell you this recent development there. All colloidal quantum well lasers, their record gain performance, advanced heterostructures, an important direction. And then I will quickly touch upon, in the interest of time, for our capability to orient them in 3D, putting them face down, putting them edge up, which is somewhat critical for us because in the ensemble, having the ability to really fully control them in orientation is a major milestone. Finally, doping these colloidal quantum wells offers us now new possibilities. This is before I conclude. So I think for this audience, it's pretty clear that semiconductor-based lighting is the only choice for future lighting. This is already well known, well recognized, and the answer really relies behind the performance efficiency versus cost benefits. This is, I think, pretty clear. But what is most of the time maybe not as much acknowledged is the quality of the lighting, and it is indeed essential to achieve certain level of quality for certain applications and applications. And if we are to have large scale penetration, the quality has to be delivered. And this is true for general lighting and display backlighting. But good news, this is possible. And that is indeed now what is driving the advancement of color technologies offered by this type of semiconductor nanocrystals, as I'll show you. At NTU Luminous, we have been actually working, as I mentioned, across the entire food chain, starting with epitaxial growth. This is something we had started earlier at Bilkent, and then with the agreement between two universities, indeed, we continued the work at NTU. Using our MOCVD system in my lab there, we can grow epitaxially these structures. And we have been working on these structures for a very long time. You can see it is almost a decade or so now when we started the work in actually early 2014 there. And what we have is we have different modular epitaxial designs that we develop, provides us very high quality crystal, quite uniform and quite efficiency emission. You can find some of the early work in here from our group. And we, of course, collaborated for many colleagues around the globe, including Professor Nakamura with Santa Barbara. And this happens to be his last publication right before having won the Nobel Prize. And we were very proud about it. So this is what it looks like. We make these devices using our clean room fabrication. This is indeed wafer scale. You can see one under microscope in operation. And over the years, my team have developed a number of different generations. This is what it looks like, going from left to the right. Lateral chip, flip chip, vertical and reverse vertical. And each time as we move on, the complexity of the device design and thus fabrication increases. You can clearly see that with the number of lithography steps needed. This, of course, provides the benefit of being able to increase the optical output power we can target, but doesn't come for free. Actually, with the complicated device process flow, obviously, the device yield drops to a certain extent. However, all of these have been successfully commercialized with NTU Singapore, with number of patents at the time obtained, and created partnership with China and India. And this ended with a successful exit at the end. So these platforms are important for us because we can also integrate them with high quality nanocrystal based color converters. This is what it looks like from my lab at NTU. We start really from scratch. You can see the wafer level epitaxy, wafer device fabrication, and then we package them with our packaging line there. And when we package them, we can use, if we wish, spatial materials. And these are all homemade for us with the customization of achieving the best photometric performance. And this is what it looks like. We can do in a remote way or we can do in an intimate way. And this is one, for example, fully packaged device, as you can see. The critical point behind all this work was actually a paradigm shift in color science. Because maybe about a decade ago, it was very commonly believed in the community that we should have as broad emission as possible in the visible so that we can achieve the best white color point. And this is historically coming from a wonderful group of material system known as phosphors. Phosphor is very robust. Actually, phosphor uses some garnet alloy. The host is very robust, and then you would dope it with, as emitter centers, with rare earth elements. So these emission centers can be quite efficient. So that's the good news. However, they have many transitions, and all these emission transitions end up with quite broad, uncontrolled spectral profile. And as a result, it is almost impossible to avoid the tails, which is one reason for a fundamental drop in the efficiency, or you can't make sure you hit the right wavelengths as you desire. As opposed to this type of rare earth containing phosphors, our hypothesis was that we can push narrow quantum emitters. Actually, closed quantum dots have been known for a very long time. Indeed, there is a large community behind this work. I could say maybe over, well, close to 30 years, surely more than 2 decades. But the essence of this sharp emission wasn't as much known. And that with the right combinations, we could actually really hit all the metrics we want for color performance. So that was the hypothesis we started. And luckily today, this is well accepted. And actually for high-end, high-performance white LEDs, you can find this type of devices where they will have discrete emitters, particularly at certain wavelengths, for example, red. So I won't go into the too much technical detail because of the time, but I would like to point out yellow phosphorus, which is the early days, and this is a low quality, and you surely have rendering problem. Rendering means to reflect the true colors of the illuminated object, and at the same time to make it warm white is very difficult. You can address this problem introducing red and green phosphors, but then even if you improve the rendering, so you can really reflect the true colors of the object and maybe make it warm enough, you would trade it off substantially with actually optical spectral efficiency. So it will be very difficult to go beyond certain number in terms of efficiently using the photons you generate by human eye. There are other issues which I will touch upon. In the case of colloidal quantum dots, or for that matter, rods and wells being quantum emitters with sharp emission, actually right combination can allow one to have it warm shade with high rendering capability, and at the same time make it spectrally more efficient. And I'll show you what is achievable. So surely with a smart design, one can achieve photometric performance to be superior then that is possible with phosphors. But there are other issues here there, most of which is addressed. For example, large-scale production is possible, stability, eco-friendliness, so on. That there are different ways how you can address these. This is surely still work in progress. There has been a lot of advancement, but there is still long ways to go. But I can tell you at this point, this has been already successful, and we will see more and more of these materials actually deployed wide scale. So today, this type of nanocrystal emitters reaching a market value of $1 billion. And in 5 to 10 years time, this is expected to reach 10 billion point. So that is the focus. We would like to have carefully engineered spectral content provided with these sharp emitters. This is what it looks like. This is some materials we synthesize in our lab. You can see the crystal structure is pretty clear. You can see how monodispersed they are. This is just self-assembled by themselves on a TM grid. And this is how we synthesize them, actually coming from more traditional epitaxy community. This is for me always very surprising, using such a low cost and simple setup. One can reach high crystal quality. And of course, using here wet chemistry, we have also the additional advantage of material in solution, meaning we can process them in solution. So in principle, these material systems are applicable to large area application if you get the processing parameters right. And I should acknowledge a large group of numbers in the community over the years made substantial contributions to this field, taking these material systems in their early days where the efficiencies were low. And now I think in the community, we can very reproducibly have high efficiency, quite robust materials. Of course, there's still more to go, but I can tell you this is already an important point, I believe, that has been achieved by the whole community. And now we can control shape, size, composition very well, and we can really engineer for a specific extonic property of our desire. In terms of lighting, I think the critical aspects is that we can hit the same peak emission again and again within 1 to 2 nanometers precision. And this is, I have to say, as good as it gets, because in terms of visual acuity and color performance, this is quite acceptable. This is something, for example, we can't quite do with conventional epitaxy when we use MOCVD. With MB, this is more possible, but MOCVD large volume, we have to bin the LEDs at the end because it's very difficult to hit exactly the same peak emission. And we can make them quite narrow at the same time. This depends on the chemical route one uses, but we would typically target to have emission in the range of 30 nanometers, because at this point, for human eye, the color purity is sufficient. As I mentioned, efficiency has been increased over the years tremendously. This is typically more for cadmium-containing material systems. We can reach near unity efficiency levels. This is, of course, in solution, and this is limited by our measurement precision. But I can tell you this is quite high. In film, this efficiency will drop. This is very typical. Still in the range, quite usable. Depends on the material system. In the range of 80% to 60% is quite likely. In cadmium-free options, certain routes still reaches this numbers, but for a large number of them, actually, still they would have lower efficiency levels. This is, I think, being in semiconductor field, very obvious to all of you, but again, less acknowledged. These nanocrystals being semiconductor below band edge, they have very strong absorption and continuous absorption line, basically broadband absorbers. But this is not the case at all for phosphors, because phosphors having rare earth elements, these ions in the ion form, when they are hosted in the garnet, actually have a limited absorption band. And 90% of these phosphors that happen to provide very good emission properties to match the emission range you desire, unfortunately will be screened out because their absorption band will be in the wrong place. So this comes already for free when we use nanocrystals. Finally, stability in the case of photo bleaching, photothermal stability is achieved depending on the specific application you desire. Obviously, different applications require different levels of stabilities, but today, for example, in TV backlighting application, this is quite possible. But if you would go to some other applications, you may need to have stability under higher influences. There are many different strategies developed. Using different strategies in combination works very well. There was a discussion almost a decade ago in the community pointing out that these rare earth elements also have the problem for supply chain, particularly because you can't find them all around the world. And some countries even use this material system as a negotiation, international negotiation chip. So we were invited to contribute to this discussion, making the point that on the other hand, semiconductor nanocrystal material systems 2,6 are widely abundant. Of course, if you go to indium phosphide, there is always the issue of indium, which is well known. But for the other material systems we use, different elements are abundantly available. And indeed, as we also pointed out at the time, these semiconductor nanocrystals can actually photometrically outperform at the same time too. And this is among the best one can achieve, rendering in the range of 90, quite warm white light. This is collected color temperature. The lower it is, the warmer shade you achieve, and spectral efficiency. This is above 300 lumens per optical watt. So if you would compare this with the best numbers in their class, this is conventional phosphors. This is typical benchmark. These numbers may change more or less, but they would be about these numbers. And in the case of using colloidal quantum dots as the color converters here, you can do better. This is actually rendering color shade and spectral efficiency. And the challenge is to do them all together. You can always do one really, really good, but you would typically sacrifice the other metrics. There is another metric which I have not talked about at all, and that is known as scotopic to photopic ratio. This is related to scotopic, dark adapted vision, and photopic, which is photon adapted vision. So this number quantifies the capability of the light source to be used also for outdoors night vision when you have fewer photons available to your eye. The reason is eye sensitive curve shifts when you start receiving fewer and fewer photons to your eye. So actually outdoors and indoors lighting are completely different, and they have to be carefully engineered. And having this number above 2.5 is an important achievement, because all the light sources we today use for outdoors lighting actually falls below this 2.5 SP wall. This is what we have done to transfer these nanocrystals for use in a solid environment. This is together with my former PhD student and now my colleague, Professor Mutlu Gün. During his PhD, we developed these standalone large-scale sheets. You can think of them as, if you wish, freestanding membranes, and we can make them quite large. This is at the time half millimeter by half millimeter. You can do monocolor here, or you can do multicolor. And this is now with Evren turned into an entrepreneurship activity too. And we are actually working in one project, 1004 code named by Tubitak, to push this further for commercialization with other partners. You can do also, if you wish, multicolor. You can put them. Now, over the years, we were able to push this to generate quite large area, basically many meters long sheets for this purpose. And there has been a major effort worldwide. This is one example using remote phosphor. This is a spin-off from MIT, later acquired by Samsung. But this technology is not used at the moment. Samsung actually has its own technology. We also work with Samsung. They are focusing on advanced TV and using these nanocrystal color converters in the backplane. This is another and quite recent example. This is actually during pandemic. You can see this is 2021, and this is with Osram. We did a project with Osram, funded by European funding, European framework program. And most recently, they developed the single page nanocrystal integrated LED. And this is, to the best of my knowledge, the only directly integrated nanocrystal system in use at the moment and commercially available. This was a project funded by Samsung, where we wanted to impart additional functionality to these nanocrystal color converters. Of course, color conversion enrichment is already by itself justifies this effort. And it is actually a quite low-cost solution, and you don't need to change your LCD fabrication or your back-end packaging to assemble the TV components. You just actually insert one sheet along with the diffuser. But if you wish, you can do more than that. And in this case, we wanted to demonstrate polarizing property, and that's what we got to work using this spatially designed metasurface integrated nanocrystal structure. But what I'd like to take you to is actually how we can do for the next piece of work, and this is related to using laser for lighting. And there's a very strong motivation behind this. Simply comes from efficiency group. This is well known with 3 nitrides LEDs for fundamental reasons, basically urge recombination and indeed electron leakage. We have inevitable reduction of the efficiency. As opposed to laser diodes, with increased power density, you actually overcome this efficiency, low efficiency levels. So there is this value of droop. And with obviously more coherent light source, for example, it could be partially coherent, you can do better photo management. So there is really a good reason why you wanted to do that. And this is already happening, for example, for automation. Headlamps are moving towards laser-based lighting. Of course, there are issues you need to handle, like speckle and so on. But if you get everything right, this is possible. And there has been work by my good friend and colleague, Jeff Sell from National Lab in the US. And they demonstrated that indeed, human eye cannot distinguish laser-based lighting from other conventional lighting, including incandescent or LEDs of different types. And this is a strong motivation for us to push also into lasing using these nanocrystals, again, for lighting purposes or even displays in the future. And this is the material system we developed. This is spatial because it has zinc blank in the core and wood side transition. And this is really good material for high gain purposes. This is actually near unity efficiency, quite monodispersed, high crystal quality, as you can see. And we can intimately integrate this being solution processable. This is where we put these nanocrystals sandwiched in a pair of alternating titania and silica layers of Bragg reflectors. This is very, very compact structure, and you can indeed place it essentially on any platform of your choice. So this is both colloidal cavity and colloidal gain intimately integrated. We call it all colloidal laser. And this gave us the best performance at the time. But no matter how we push this to engineer further, it was actually not possible to go beyond certain levels. And the reason is we have some fundamental constraints. And this has to do with the possible gain coefficients we can induce. This is in the range of hundreds of inverse centimeters, accompanied with ultra short gain lifetimes, 50 picosecond or shorter. And this actually manifests together itself in a large optical gain thresholds. This is in the hundreds of microjoule per centimeter square, at least, if not higher. And the root cause is we have ÖJ combination kicking in at high influences, and absorption cross-section, of course, being colloidal, confined in 3D, you have a very little cross-section. This is geometrical cross-section, and then the oscillator strength is not as strong. Therefore, absorption cross-section is not as strong as, for example, possible in wells. So these are the reasons. And one way to try to make them bigger, what is called giant quantum dots. In our case, we wanted to push for wells. So I will be quick here, assuming we started maybe 10 minutes late. I will use just 10 minutes to finish up my talk here. If this is okay by the organizing committee, I suppose, I hope it is okay.
Yes, of course.
Okay, I'll finish in 10 minutes. I think we had a little bit late to start, but should be fine. So this is atomically flat, and we can make them magic size. And this work was inspired by a group we know well, and they are very, very friendly, and we were inspired by their work, where they demonstrated for the first time from SNRS in France that you can reproducibly obtain these atomically flat surfaces. And before that, it was more accidental. And this opened out for us a new path. We can make these only core or core shell, which is shell coating everywhere, top, bottom, and peripheries, or you can do an isotropic growth, and you can extend them basically laterally to make this core, what we call core crown. So this was interesting for us because we were excited about the possibilities to do optoelectronics using these flat nanocrystals. And the nice thing is you can make them as large as you want and still keep extremely tight confinement vertically. So you can actually induce giant oscillator strength, but with the absorption cross-section being so high, you can do great things. And since it's all magic size, and this is the dominating quantum confinement vertically, we achieve ultra narrow emission. just 7 to 8 nanometers in certain simple material systems, limited by homogeneous broadening. We don't suffer in homogeneous broadening unless we go to more advanced structures. Finally, we have another degree of freedom here, being an isotropic system there. We can place them in different orientations we choose. At the end of the day, using all these benefits, we were actually able to surpass all those difficulties. So one major barrier we overcame was we were able to reduce the optical gain threshold to at least an order of magnitude, and these days more than 2 orders of magnitude, because we can induce higher gain coefficients easily in the thousands of inverse centimeter, and these days even 10,000s we are able to reach. And finally, they have longer gain lifetimes. This is biexonic gain lifetime. So that's what you see, very sharp emission, 7 to 8 nanometers at full width half maximum at room temperature, and shown in red curve. On the background, you see the dotted black line presenting you the absorption profile. And this is a wonderful quantum system. You can see well-resolved heavy hole, light hole, electron transitions, extonic peaks there, and then a plateau. This is something you would very rarely see in two-dimensional systems. This is like a textbook quantum absorber in itself. And we, again, applied the same idea, intimately integrating in a colloidal cavity, and we're able to see the first account of lasing using single photon absorption. And at the same time, indeed, another group from Chicago independently also demonstrated for the first time along with us lasing. In their case, though, they use core only, and we use core crown architecture. We can do also 2 photon, and that's what we additionally push for. So this is 2 photon absorption-based pumping. We switch from 400 nanometers, doubling it to 800 nanometers, and you can see again lasing property. But over the years, we push this with higher material quality and using higher influence levels, we can induce net model gain in the range of several thousands of inverse centimeter. And if you'd like to put this in a perspective, this is what you would find in the literature as being the best in their classes: organic dyes, polymers, colloidal quantum dots, rare earth doped fibers, epitaxial quantum wells. This is prior work, the best in their class. This is a very standard epitaxial growth. These are for the wells. And they all fall in here at room temperature. And this is what was achievable with this material system. But again, to be fair enough, this is the highest number we found in literature reported. This is bulk gallium nitride, however, at cryogenic temperature. And this is perovskite, a very important and rising star of material system. We also work on this material system. This is also reduced temperature. This was another discussion. This is now material gain. The previous one I showed you model gain, so one has to extract and predict the material gain. This is in solid dots at room temperature, cryogenic, and our prediction is this is where we are. And with most recent material design, we were able to get here. So from this point on, I will just show you ideas and not really go into technical details. This is very rich. You can think of quite advanced structures. You can go in many different directions. I won't tell every one of them, but you can do different electronic alignment, type 1, type 2. You can inverse them. This is early work. These days we can do them very nicely aligned. So it is like a quantum ring. You can study very systematically different optical, photophysical properties in general, optical gain, if you wish. And that's what we did. Just an example, going from core to core shell or core crown. You can combine the 2 strategies, make core crown shell. So this is like well in a box structure, and that will be the cross section. This obviously increases the stability tremendously. Remember, we are really bombarding these materials with high photon density. We push this to have this shell coating very spatial, hot injection. This is indeed typical for quantum dots, but this was not available for wells. So that's what we developed. And what we found is we can really achieve a near unity efficiency. Even if we very rigorously wash them, still the efficiency is indeed preserved. You can make them film, as you see, in glow box with no barrier. you achieve a good level of efficiency well sustained. And this is just within the last 2 years. Using this material system now available to us, we can make, for example, LEDs, or we can make lasers. And here, what we achieved was the highest efficiency possible. And these color quantum well LEDs now, in terms of performance, are on par with color quantum dot LEDs and other soft material systems. This is without any light extraction feature. This is pretty close to the theoretical limit. With extraction, we can go actually beyond 20% too. And there is a schematic study behind it that you really have to design these and understand the effect of the lateral size going from rectangular to squarish, and do a large number of devices to achieve these numbers. This is the hero device, 19%, and on the average, you will see you are in the 15% range with many devices. This is the solution laser. I will again cut short here. This is basically very high density hot injection shell ground color quantum wells integrated into microfluidic channel with it. You can put pair of mirrors as facets. This is simple Fabry-Perot cavity, and in solution you can induce lasing. And the result was surprising. We achieved 3 orders of magnitude lower threshold compared to any type of in-solution laser reported to date. And this was, for that reason, an important step for us to observe the details of the signature of lasing action there. You can take this hot injection shell growth one step further, and in this core crown shell, you can actually make alloyed shell, and you can carefully quantum engineer these structures in a way that you suppress urge recombination even further. And this allowed us to go sub-single exton level of optical gain in the ensemble. This is average performance, so this is per particle. And this is, to the best of our knowledge, the lowest ever reported for these material systems. And of course, with that, also stability is further increased, and you can do all different kinds of lasing actions. Finally, we orient them face down, edge up, and you can put multiple layers. This is 11 layers. You can use now well-oriented slabs if you wish for lasing action. This is what it looks like. And you can make them in large areas. This is more than 80 centimeters square. You can study their gain behavior as a function of number of layers you lay down. And we have good understanding you need at least minimum number of layers, for example, on quartz, to be able to optically support the guided mode. Finally, we dope them for different properties. This is copper. This is, for example, manganese, where you can impart magnetic properties, and a lot of different applications come out of this. This is, for example, a luminescent solar concentrator. With that, I am happy to conclude. I hope I was able to convince you that this is a very interesting field. This type of colloidal nanocrystals actually enable high performance for color conversion and enrichment. And more recently, colloidal quantum wells, as being the latest subfamily of the nanocrystals, offer excellent gain properties. And there is more to do with their highly engineered heterostructures. And 2 new directions emerged. One is orientation control, and not only designing the emitters themselves, but the whole ensemble is, I think, very exciting. And finally, doping surely is a new playground for us. And I'm very happy to acknowledge funding sources from a variety of agencies and also private sector. And if you are more interested to read about colloids, this is a recent book that came out with my friend and colleague, Professor Gaponenko. I would be happy to promote if you are interested. Finally, we have positions available for researchers and scholars, as well as PhD candidates. Please feel free to reach me out. And thank you so much for your time and interest.
Thanks very much, Professor Volkan Demir. This was really an impressive talk. Thank you very much.
You're very kind. Thank you.
So we have time for a few questions from the audience. Are there any questions? Please write also in the chat. Okay.
I have a question. Okay. Thank you very much, Professor Demir, for your nice presentation. One question comes from the student about the quantum confinement effect. It is a very general question, but it will be useful for the student.
Sure.
What's the border of the nano effect for different materials? There are some materials show the nano effect at 100 nanometer size, and there are some materials also in 150 nanometer. What's the exact? There is no exact border. It depends.
Sure, I'll be very happy to discuss this point. I'm aware we have very young student researchers in the community, and this is quantified by Bohr exton radius, and this is different for different materials. It depends basically on the effective mass of the charge within the crystal structure. But given the Bohr radius, you would think of this as electron and hole pair coupled together. And this is really the Coulombic interaction that keeps them together. And this we call an exciton. Now, if the physical confinement of the piece of the crystal is comparable to Bohr radius, we are, or smaller, we are going into the strongly confined regime. As you relax this, meaning you are still close, but larger, you are in moderate range. And if it is significantly larger, weakly confined. And the bigger it gets, obviously, more converging towards bulk behavior. And it is different for different material systems. I can give you a very good example. For example, many of the cadmium containing material systems would have Bohr radius in the range of 2 to 3 nanometers, depends on the exact composition. As, for example, these colloidal quantum wells I mentioned already a good part of my talk, which are laterally large in 2 directions, x, y, let's call so, and vertically z, very confined. Now, instead of making them squarish, if we wish, we can actually shorten them along one edge laterally. And as we do that, they become more rectangular-like. But the cross-section is still a rectangle. So we still indeed maintain the general geometry. Now, as we make it shorter and well, narrower and narrower laterally along one direction, and while we keep it, we actually observe that we have another confinement kicking in, and the behavior is changing from 2D towards 1D. So this we do with just the size. So it depends, but at the end of the day, how close you are to the Bohr radius in the crystal system. I hope that was a quick explanation.
That was perfect. So another super quick question, if there is. If not, we thank Professor Volkan-Demir again. Thank you very much.
Well, thank you. It was my great pleasure.
And then we pass to the next speaker, who is also an invited speaker. It's Dr. Angela Dudley from the School of Physics of University of Witwatersrand of Johannesburg in South Africa. And she got her Master of Science in Physics from University of KwaZulu-Natal. Then she joined the CSIR National Laser Center on a PhD studentship. And after completing her PhD, she commenced a postdoctoral fellowship followed by a senior researcher position at CSIR. Then she joined the University of Witwatersrand, when she is currently a senior lecturer in the physics department and a research group member of the Structural Light Lab. Her talk will be about the generation and control of the structural polarization. Please take the word, and we are eager to hear your presentation.
Thank you very much. I'm just going to share my screen quickly.
Perfecto, we can see it.
Thank you. So you can hear me, see my screen, and see my laser pointer.
Yes.
Ah, that's great. Thank you so much. Okay, great. So hi, morning everyone. As you've heard, my name's Angela Dudley, and I'm from the Structured Light Laboratory at the University of the Witwatersrand, which is located in Johannesburg, South Africa. I would first like to just thank the organizers for this invitation and to this conference, that I've really been enjoying this conference so far. There've been some really great talks. So in this talk entitled The Generation and Control of Structured Polarization, I'll provide an overview of the work that our group performs in shaping both scalar and vectorial fields, and then some of the tools that are needed to create and control and detect these optical modes. Then we'll look at a very specific case where we control the polarization structures to not only rotate about their propagation axis, but that they can be made to accelerate independently from their spatial profiles. And then finally, we'll look at some digital approaches to extract the polarization structure of these fields. So as you heard yesterday, we're based at the University of the Witwatersrand, which we colloquially term WITS. And in Andrew's plenary, you would have seen the beautiful nighttime shot of our Great Hall. So I thought for today, I would show you a daytime view of the Great Hall. And this is where we have graduation ceremonies, ceremonial lectures, and sometimes we even have music concerts are held here. And as Andrew was saying yesterday, our lab is just based in the physics department, which is just to the left. So this building over here on the left-hand side of the Great Hall. So the core focus within our group is structured light, and this is illustrated here in this slide by controlling the spatial profile of light. And from the talks that you've seen from our group already, just from the various group members, you would have noticed that we work both within the classical and quantum regimes, and we predominantly create these spatial profiles external to the laser cavity. But we have also done some work whereby doing it internal to the laser cavity. So now structured light refers to the shaping of light in all of its degrees of freedom. So such as in the time and frequency domains for the creation of ultra fast pulses, or in our case, the spatial degrees of freedom. So such as shaping the amplitude or intensity, the phase, and the polarization structures. And in the case of controlling both the phase and the polarization structures of an optical field simultaneously, we can create these very topical vector beams, which I will go into more detail in some of the upcoming slides. And then if you are interested in reading a review article on structured light, how it's created with the various approaches and the applications in which structured light plays a role, I can highly recommend this review article that appeared in Optics and Photonics News back in June in 2020. So now there exists a variety of tools that one can use to create structured light, ranging from spiral phase plates, and then we saw yesterday afternoon with metamaterials. We can also use things such as cube plates. And then there's more dynamic approaches that can be used, such as our spatial light modulators and our digital micromirror devices. And then I think most of you within this audience is familiar with the physical mechanism behind how the encoding approach works on these spatial light modulators and these digital micromirror devices. It's just based on the long-standing and well-known technique of digital holography, of this holographic process. So here in this illustration on the right-hand side in the bottom corner, we have a hologram that's created by illuminating some object, this object over here, with a reference beam, with a laser beam. And then the interference pattern that's obtained between the reference beam and the object beam, that is termed the hologram. And then by running the process in reverse and just illuminating the interference pattern of the hologram with the reference beam, you can then create the object beam. And again, if you are interested in looking through a more tutorial approach of how to encode spatial light modulators, this is a very good textbook to get hold of. Now, in our lab, we predominantly make use of these spatial light modulators and digital micromirror devices to create our spatially structured modes of light, and each of these have their own advantages and disadvantages. So while the spatial light modulators offer a higher efficiency, They are polarization dependent and they have much slower refresh rates, and they're also they're more costly. Whereas the digital micromirror devices, on the other hand, due to the fact that they involve amplitude-only modulation, this results in a low first-order diffraction efficiency when you use them to modulate phase. They are, however, much more cost-effective, and they have much faster refresh rates. And the fact that they are polarization insensitive, this is what makes them suitable and conducive for creating vector beams and vector beam control, which I will highlight in an upcoming slide. So now that we've seen that these devices are capable of modifying the spatial structure of optical fields, they offer many more opportunities and capabilities. So we also use these spatial light modulators and digital micromirror devices in our lab to mimic free space propagation. So usually if you want to investigate how a beam propagates, you need to physically move a camera or a sensor along the path of the beam, making the alignment more problematic. But the digital approach here allows you to simulate the behavior of beam propagation by just using static optical components. So it removes any need for actually physically moving optical components in your system. And then we can also use these holograms to assign specific carrier frequencies. And this allows us to control and shift our spatial mode to various locations within our sensor plane. And this is a term that's termed multiplexing. And then we've also shown that these devices, more in the case of spatial light modulators, they can be wavelength dependent when operated in the first diffraction order. And this allows us to vary the spatial profile of multiple beams across different wavelengths. So you would have already seen from previous talks that these spatial profiles have numerous applications. And one that I just want to highlight here in the slide and the upcoming slide is that we use them to increase the bandwidth of optical communication systems. So this is just one particular application. But from the talks that you would have seen over the course of the conference, we use them in many other applications. So in this specific case here, we use these spatial profiles as various information channels to encode a much larger alphabet. So in order to increase the bandwidth of optical communication systems. And this is just illustrated in the following slide here in this video. So here we have three various wavelengths. So these three panels over here just represent the sensor or detector planes of our three individual wavelengths, and each of these wavelengths is then encoded with 35 different spatial profiles. And this offers over 100 information channels that we then use to encode the red, green, and blue colors illustrated in this following image of the Rubik's Cube. And this reconstruction of this image that's getting sent across the communication channel is all done in real time. So there's no speeding up of this video over here. So up until now, we've only been considering scalar modes. So all the slides that I have shown up until this point over here have only considered scalar modes. And now we're going to look at the case for vector modes. So in order to illustrate what vector beams are, we're going to make use of the Jones formalism. So if we consider our scalar polarization, the following Jones matrix represents horizontally polarized light. So this top image over here, and then we have the case for vertically polarized light. If we have a field whose horizontal and vertical components are represented then by the exact same spatial profile, so this case over here, we can then create our linear polarized polarization states. And then by just introducing a phase term, you can then create the right and left circularly polarized states of light. If the two components are then represented by different spatial modes, so just illustrated over here where we now have two different spatial modes represented by two orthogonal states of polarization, we can construct what we term vector polarization. So in the case over here, we can create this radial vector polarization state. And then in the case down over here, we can create this azimuthally varying polarization state. And with these beams, you can see that the local polarization state is linearly polarized at different orders across the field. So at azimuthal positions across this optical field, sorry, at radial positions across this optical field, and then at azimuthal positions. So here you can see that we have the spatially variant polarization structures, which is unique to vector polarization. Then often in the lab, in order for us to verify that we do have a vector mode, what we do is we pass these modes through a polarizer. So for example, if we just consider the circularly polarized states of light, so illustrated in this image over here, and we pass it through a polarizer, you would obtain uniform intensity profiles as you rotate the angle of the polarizer. So this is just illustrated in these subsequent snapshots, and this video over here, which might not look like it's actually playing anything, but it's just as you rotate the polarizer, the intensity profile appears uniform. And then if we then pass a vectorial state of polarization through our polarizer while varying the angle of the polarizer, you can see that you get differing spatial profiles at various angles of the polarizer. So this just illustrates that the local polarization state, when selected by the polarizer, is linearly polarized at different orientations. And with generating these vector beams, we can create a multitude of various spatial profiles. So this equation that's illustrated over here is the general form for our vector beam, where the two orthogonal polarization states, in this case, are just represented by right and left circularly polarized circular polarization states, are assigned to different spatial profiles. So we can assign them to the Gaussian spatial profiles, Bessel Gaussian, Hermite Gaussian. There really isn't any limit to the spatial profile that can be assigned to these vector polarized states of light. And these modes have become extremely topical in that they also offer increased bandwidth for optical communication systems. They're also used in increasing the dimensionality of entanglement systems, as well as allowing the possibility for interaction-free detection with quantum imaging. And we've also seen that they offer tighter focal spots when focused under high numerical apertures. So these are just some of the applications as to why we're interested in being able to create and also detect these spatial modes. So now we'll just look at two different approaches for actually creating these vector modes, which we make use of in our lab. So the first approach just makes use of our digital micromirror, whereby its insensitivity to polarization is what makes it conducive to creating these vectorial modes. So because we can simultaneously assign various spatial profiles to orthogonal polarized states of light, which is just illustrated in this following illustration over here. So by illuminating this digital micromirror with two orthogonal states of polarization, so here right and left circularly polarized states of light, and encoding the digital micromirror to have two multiplexed holograms, which each contain a unique spatial profile. And then the gratings are assigned in such a way that the two encoded orthogonal spatial profiles lie collinear on one another. We can then create our vector mode. So in this first order illustrated over here, this is the order that would contain our vector mode of interest. And usually this first step over here, where we separated our incoming mode into two orthogonally polarized states of light, we just achieve this with either using something such as a polarizing beam splitter, a Wollaston prism, or polarization grating. And then the second approach that we make use of is by using a spatial light modulator, which just involves an interferometric method that involves splitting our scalar beam into two subsequent beams. And then we are able to manipulate the polarization states of one of the beams with either polarization optics such as a half-wave plate or quarter-wave plate, and then by encoding unique spatial profiles onto each of the modes. So this is just to illustrate the two types of techniques that we use in terms of creating these vectorial structured modes of light. So now that we've covered some of the basics as to what these modes are, how we create them, we will look at something a little bit more exotic. So as to how we can make these polarization structures accelerate. So we first need to know how to create accelerating spatial structures. So before we can look at how to create accelerating polarization structures, we first need to look at how we are going to create accelerating spatial structures. And even more so before that, we need to look at how we can just create a rotating spatial structure. So if we were to do this by just using a vortex mode, so this mode that's illustrated over here, you can see that it would be very difficult to witness any angular rotation due to the continuous circular structure of this mode. But if we created a superposition of two vortex modes, producing this petal-like structure, having these individual petal structures over here will allow us to actually track the rotation of a single petal. And then by being able to remove any diffraction effects, so this is just illustrated in the video that's playing over here, it should be playing. Yeah. You can actually see that we can get this mode to angularly rotate. And then by just removing any diffraction effects, this will allow us to measure the angular rotation without any contributing factors. So in this slide here, the takeaway message is that in order to be able to create an angular rotating spatial structure, we need to have two requirements. We need to be able to actually visualize a petal-like structure that we can then witness the rotation, and we need to be able to remove the diffraction effects. So in order to achieve these two requirements simultaneously, we make use of superposition of higher order Bessel beams. So an interesting feature in when creating these superimposed higher order Bessel modes is that we're in essence creating a mode that carries no orbital angular momentum. And then this is just illustrated in the following example, where we have created a mode that contains orbital angular momentum values of +3 and -3. So the overall orbital angular momentum is 0. But when propagating this field, we still witness a rotation in the petal structure as the mode propagates. And this is actually due to the fact of the slightly differing wave vectors that make up these individual Bessel modes. So here we're able to quantify these rotation rates and show that it's dependent on two factors. So these two factors over here, which is the difference between the wave vectors and then the azimuthal order that's encoded within the Bessel mode. So although this angular rotation is constant, it's not displaying any acceleration. So we're now going to move on to looking at how can we actually create an angular acceleration in these optical fields. Okay, so the reason that these azimuthal, that these modes only display a constant acceleration lies in the fact that the azimuthal phase contained within each superimposed Bessel beam varies linearly. So this is just restricted to the motion of the petals to being a linear constant rotation. So this is just illustrated in the following image over here. This is the type of azimuthal phase that's encoded that has a linear variation, and you can see that in the plot over here when we plot it against the azimuthal angle. So it then follows that in order to obtain an angular acceleration of the beam profile, one needs a nonlinear phase variation in the phase as a function of the azimuthal angle. So this is just illustrated here in this phase profile. If you look very carefully, you can actually see that as you vary from this dislocation in a clockwise direction, you can see that this phase variation is not linear. And this is just represented by the orange plot over here. Okay, so in experimentally then demonstrating the angular spatial profile acceleration, we address each of the two ring slits with a nonlinear azimuthal phase variation. And you can witness the resulting intensity profile as the field propagates has this angular acceleration. So just in this video over here, and these ISO surface plots on the right-hand side over here. So where you see these regions of tight twisting, this is where the field is actually accelerating. And by controlling what we call this morphology parameter, denoted by this angle theta over here, or often referred to as an anisotropy parameter, we can then control the acceleration and deacceleration of these optical modes. So now, in order to witness a similar angular accelerating effect with polarization, so this is from before this, we've only seen it with the intensity profile. We need to look at how we can create radial polarization fringes. So we already know very well how to make intensity fringes from just looking at Young's double slit experiment, whereby if you illuminate two circular apertures, you can get these intensity fringes. And by just increasing the spacing between the two circular apertures, you can decrease the spacing between the intensity fringes. And then in order to move from linear fringes to radial fringes, we've already seen this in the case of Bessel beams. So by just increasing the number of circular apertures that sit on this angular ring, you can then start forming the Bessel mode. So now the question is, we can do this in terms of the intensity profile, but can we create a similar effect with polarization? So it's known that if we combine two fields having the same polarization, it's possible to cancel and interfere, and the interference pattern can be seen. But if we combine fields with orthogonal polarizations, it's impossible for them to cancel, and so no interference pattern will be seen. And that's true in the case of looking at the intensity profile, but it's not true in looking at the polarization map. So by viewing the polarization map of the resulting field, we see these fringes by just varying the phase difference between the orthogonal polarization states. And we can then engineer the resulting polarization map to either have linear fringes or radial fringes. And then if we want to witness an angular rotation in this polarization map, it would be ideal to be able to create polarization petals. So these types of azimuthally varying polarization petals. So if we now assign oppositely varying azimuthal phases to two orthogonal polarization states, so represented here by this X hat and Y hat, where we've represented the phase profile associated with each of these orthogonally polarized states of polarization, in this case with L equals +3 and L equals -3, we can then create this, these radial polarization fringes. Now, if we combine our previous case of creating angular accelerating spatial intensity profiles together with the generation of polarization fringes by just encoding components of the optical field with superpositions of two Bessel beams that have opposite azimuthal indices, so as to produce an optical vortex with a nonlinear phase variation, we can then see this angular accelerating polarization structure. So in the case over here, where this anisotropy parameter is just assigned to 0, there will be a nonlinear phase variation between the two orthogonally polarized states of light. And so the angular acceleration that you witness is then a constant rotation. And by assigning this to a non-zero term, you can then witness an angular rotation in the polarization structure. So this slide over here just illustrates the angular accelerating and deacceleration trajectory as the field propagates. So if you look at this isomorphic plot where the red just denotes the right circularly polarized state of the right circularly polarized mode, you can see that when you get these regions of tight twisting in the right circularly polarized state of light, you get a deacceleration in the orthogonal left polarized state of light. And this is also witnessed when looking at the Stokes parameters on the Poincare sphere. If you just, for instance, watch the green vector, you'll see that at points along the Poincare sphere, there are points where it actually speeds up and points where it slows down. So up until this point, we've looked at how we can create various polarization structures. But our group's also very interested in how we can actually measure them. So there's two various approaches that we make use of. The one is where we use the modal decomposition approach. And then this just involves decomposing an unknown optical field into orthogonally weighted superpositions of various match filters. And by determining these weightings over here, these which are complex amplitude coefficients and intermodal phase values, we can then reconstruct our optical field, our unknown optical field. And so we already know how to create these match filters in the lab. And just by running the process in reverse and illuminating the match filter with the mode of interest and monitoring if there's an on-axis intensity, you can then detect if the mode is present or not in the optical field. And then by measuring all these on-axis optical intensities, we can then reconstruct the optical field of interest. And by just separating this into its two orthogonal polarized states of light, so in this particular case here, which is right and left, we can do a similar approach in just repeating the exact same modal decomposition in terms of reconstructing our vectorial spatial profiles of light. And this approach allows us to measure all the physical parameters associated with optical fields. So we can reconstruct its intensity, its phase, its orbital angular momentum density, the pointing vector, as well as the wavefront of optical fields. And then another final approach that we'll just briefly look at is a digital analogy to the Stokes polarimetry measurements. So Stokes polarimetry is just based on measuring 4 intensity profiles, and from these 4 intensity profiles, so for example here measuring right, left, diagonal, and horizontal, we can reconstruct the Stokes parameters. And these Stokes parameters give an indication of, in the case of S0, the optical field, and then subsequently the polarization states associated with this optical field. And from this, we can then reconstruct the state of polarization. So in our approach to create a digital analogy to the Stokes measurements, just based on the conventional approach, there are 2 requirements that need to be satisfied. So we need to have independent control between the orthogonal states of polarization. And since our digital micromirror is insensitive to polarization, we can achieve this with a digital micromirror device. And then we need to be able to measure within the orthogonal basis. So we can either use something such as a Wollaston prism, a polarization grating, or a polarizing beam splitter to be able to achieve this. And just in more experimental detail, this is what our digital Stokes polarimetry device looks like. We have a generation section where we're able to recreate our vector and scalar modes by just using a Q plate. We then project into 2 orthogonally polarized states of light. And then by encoding a phase difference of 90 degrees on our digital micromirror device, we can then project into our right, left, horizontal, and diagonal states of polarized, diagonal polarized states, which allows us to then reconstruct our state of polarization. And this illustration on the right over here just illustrates that we're also able to do this dynamically. So we can look at dynamical variations of the polarized state of light. So this illustrates doing the measurements both with scalar fields in terms of reconstructing the Stokes parameters and then vector fields. And you can see that there's very good agreement with what we experimentally measure and what we theoretically expect. And this approach allows us, just in this illustration over here, to reconstruct the state of polarization. So in our digital Stokes polarimetry device, we pass through a circular polarized state of light, a radial polarized state of light, and we're also able to extract the intermodal phases. So this is just a comparison between the conventional and digital approaches. And you can see that there's a very good agreement in terms of extracting the intermodal phase between the orthogonally polarized states of light, in terms of looking at the actual experimental measurements, and then the insert, which just depicts the theoretical expectation.
So you
and
have
we can
still
also
5
do this
minutes.
with digitally propagating optical fields. And so in closing, I would just like to highlight and end with the photo of our group. So as Andrew was mentioning yesterday, this work is only possible with all the students that we have involved in the group. And I'd just like to point out Wagner and Keishan, who both worked on the accelerating polarized work. And in that, I'd just like to say thank you very much for listening, for your attention.
So thank you very much. Your talk was really interesting. I'm not an expert in the field, but I enjoyed it a lot. So as we are a little behind schedule, we have time for only a quick question from the audience. Please write in the chat if you have questions, because I cannot see raised hands in the, so.
It's a question in chat bar, Benedetta.
Perfect. Is it possible to determine the structure of an undefined light? Is it the superposition of different defined structures?
Yes, so in answering that question with our modal decomposition technique, as the main requirement is that the modes that you measure against in terms of a match filter have to be orthogonal to one another. So any optical mode can be decomposed into a series of weighted orthogonal modes. So by encoding the match filters with whatever basis you pick, you can then reconstruct this unknown optical field. So obviously, practically, there's a limitation to the number of modes that you're going to check against, but usually by doing this dynamically, you can check against a wide range of modes, and by being able to determine the weightings associated with those modes, you can then reconstruct your unknown optical field. So hopefully I have answered that question correctly. So I'm just reading it again.
Yes.
So you can determine both the spatial structure and the polarization structure.
Perfect. Thank you very much. Yes, your answer was really clear. So thank you very much for your talk again. And we can switch to the last speaker of the day, who is of this session, who is Prof. Alexander Vladimirovich Bolyer, who is head of the General Physics Department in the Crimean Federal University, Navy, and he was given the degree of the Candidate of Technical Science in the field of Physical and Quantum Electronics at the Moscow Institute of Radioelectronics. And he got also the degree of Doctor of the Physical Mathematical Science in the field of Optics and Laser Physics at the Institute of Physics of the Academy of Science of Ukraine in 1992. Since 1993, he works as professor of the Department of General Physics. And beginning in 1999, he is also the head of the Department of General Physics. And he is author of more than 170 scientific articles in the sphere of nonlinear optics, fiber, and singular optics. And he will talk today of structurally stable transition in combined vortex beams upon excitation of each of its degree of freedom. Please, Professor, the field is yours.
Good day, dear colleagues. I'm from Crimea Federal University, more exactly from Institute of Physics and Technology. And first of all, I'd like to thank our committee for inviting me to your remarkable conference. And my report is structurally stable transitions in combined vortex beams upon excitation of each of its degree of freedom. We will talk about transforms of structural beams when big data is inserted into them, namely structured beams vortices, structurally stable transitions, fast oscillations of the orbital angular momentum, and two sides of Shannon entropy or information entropy, as well as competition of topological charge and invariant of fast oscillations. My character. my postgraduate students, Maya Britko, Yana Akimova, and also Associated Professor Yuri Yegorov, and also Professor Evgeny Abramishkin from Russian Academy of Science. The development of computer technology and discovery of spatial light modulators made it possible to transfer structural beams to a completely new qualitative level. Here we should note the great contribution to these advances of Professor Andrew Forbes from South Africa, Izhi Chen from China, Viktor Kotkar from Russia, and many others. Some was about structural beams. Structural beams contains a great number of standard vortex or vortex-free beams are matched strongly over phase and amplitude to be structurally stable when propagating or under weak perturbations. I will not talk about widespread employing these beams in communication systems, systems for trapping and manipulation of microparticles, in quantum photonic information protection system, etc. But we will focus on what happens to the structural beam when big data is inserted into all its degree of freedom, say in the form of the orbital angular momentum that is exciting each layer Gaussian modes, or a fine structure of these modes. Most simple example of the structural beams are triangular spiral beam. Spiral beam contains a great number of vortex layer Gaussian modes, matched strongly over phases and amplitudes to be structurally stable when propagating. In order to excite each modes, we use function, two-parametric function. Here, epsilon is amplitude parameter, and theta is a phase parameter. This picture illustrates transformation of the triangular spiral beam when increasing the phase parameter. In the initial state, without excitation, we have an ideal triangular state. But when we turn on phase excitation, the structural beam transfers into a new unstable state. And this unstable state changes when increasing the phase parameter. I mean the case when amplitude parameter equal to units, that is very small. But when we make the phase amplitude parameter very large, say 100, excitation of the structural beam do not change its structural stability when inserted the phase parameter into each layer Gaussian mode. At the same time, if the measurement is carried out in the basis of the Laguerre-Gaussian modes, then the violation of structural stability will not affect any information distortion, since there is no cross-talking between vortex modes. But a completely different situation arises when the inference interfere with the fine structure of Laguerre-Gaussian modes. Indeed, ordinary Laguerre-Gaussian modes can be presented in the basis of Hermite-Gaussian modes, as you can see for a simple case. But we will insert amplitude and phase parameter into the fine structure of Laguerre-Gaussian modes. And as a result, we obtain a whole gamma of structurally stable beams. This fine structure of the intensity patterns and phase patterns. When varying the excitation parameter, you can see here two sets of structural beams for a small amplitude parameter equal to unit and for large excitation parameters. These beams remain structurally stable when varying phase parameter in each vortex modes. But we will peer deeper in the structure of the triangular spiral beam consisting of many structural vortex Laguerre-Gaussian modes. Thus, the spiral beam contains a lot of Laguerre-Gaussian modes. In turn, each Laguerre-Gaussian modes contain a set of Hermite-Gaussian modes. What will be happen if a multiple phase is excited in each Hermite-Gaussian mode of the spiral beam? And what we obtain when we increase the phase parameter, we obtain a whole gamma of structurally unstable states when propagating and even slight perturbations. But despite any irregular excitations that are inserted into the beam, there is no cross-talking between eigenmodes upon the condition the mode detection have to be run in the Hermite-Gaussian basis. But what happens if the measurements are carried out in the basis of Laguerre-Gaussian modes? For simplicity, we return to the structural Laguerre-Gaussian beam and insert phase excitation into each Hermite-Gaussian mode. We will find that the radial number and mode topological charge or azimuthal number are entangled with each other. Indeed, we can present the structural Laguerre-Gaussian mode as a finite composition of fundamental Laguerre-Gaussian mode. But if we look at its radial and azimuthal numbers, we see that the quantum numbers are entangled between each other. Indeed, at first we present the structure Lagrangian mode in basis of Hermite-Gaussian mode. But when we insert the excitation into it, we have a whole gamma of standard Lagrangian beams, but with entangled radial and azimuthal numbers. Nevertheless, when we measure the orbital angular momentum of such structural composition, we see that orbital angular momentum depends on the local topological charge of each vortex mode in the superposition, and also on the squared amplitude of each mode. The same situation we observe for informational entropy. I will say about physical sense of this informational entropy later on. But here we see that informational entropy depends also on squared amplitude of each Lagrangian mode and binary logarithm of the squared amplitude. Despite the entanglement of quantum numbers, the eigenmodes do not lose their inherent properties, but the property of the structural beam as a whole is undergone a drastic modification. You can see here two situations. In one situation presented here, we turn on the radial number in the structural beam. Here you see the dependence of the orbital angular momentum per one photon on the phase parameter. For small amplitude parameter equal to unit.
I feel so silly. I forgot that I had the key. I forgot about my background. Just from last week.
And you see that this dependence has a smooth character. What different initial topologic charge of the structural beam from 5 to 20. But when we turn on the radial number, we observe a fast oscillation, both orbital angular momentum and informational entropy. Such an entanglement of the quantum numbers has far-reaching consequences. Let's look just a few of them. I'd like to talk about informational entropy. Back in 1948, Claude Shannon considered informational entropy with two sides. From one side, Shannon entropy is a measure of disorder, a measure of uncertainty to detect a light mouse in a wished state. On the other hand, informational entropy is a measure of information capacity of a structural beam and evaluate quality of transmission channels. But how to distinguish between these two completely different physical representations? How can we measure it experimentally? You can see here two sets of Hermite-Gaussian and Laguerre-Gaussian modes. They connected with each other point-to-point correspondence. When the excitation is turned on, turned off. Also, each Hermite-Gaussian mode has point-to-point dependence of the set of Hermite-Gaussian modes. But when we insert the excitation into the structural Laguerre-Gaussian beam, we obtain a very complex situation. The function of the structural beam becomes multivariate, and as a result, the radial and local topological charge are entangled. And our results depends on how we can measure the orbital angular momentum or informational entropy. As you can see, the phenomena or informational entropy depends on the squared amplitude of each mode. But we can measure this amplitude in different bases. When we measure the beam in the Hermite-Gaussian basis, we obtain informational capacity. As you can see, we obtain a smooth dependence of informational entropy on the phase parameter. But when we measure the entropy on the Laguerre-Gaussian basis, we obtain the oscillation of the informational entropy and also Laguerre-Gaussian beams, orbital angular momentum, sorry. Thus, we deal with uncertainty. Thus, when measuring informational entropy in the Laguerre-Gaussian basis, we deal with the measure of uncertainty to find a specific Laguerre-Gaussian modes in a certain strictly specified state, while the measurements of the informational entropy in the Laguerre-Gaussian mode basis describe the information capacity of the data transmission channel. But is it possible to find invariance of the fast oscillation for the process of orbital angular momentum and Shannon entropy? One of such invariants is the total topological charge of structural beam. According to Michael Berry, the total topological charge numerically equal to a number of trajectories of optical vortices, taking into account their signs that cross the cross-section of a complex singular beam. On the other hand, the total topological charge is equal to the maximum local topological charge of vortex modes in the mode spectrum. But as a result, we will come across with something like a competition between vortices with opposite topological charges when measuring. Indeed, here you see a simple presentation, Lagerhausen beam in the basis of standard Lagerhausen beams. And we have to compare amplitude, more exactly squared amplitude for what is beams with positive and negative topological charges. The total topological charge equal to the maximal, to the topological charge with the maximum amplitude. But when we measure the contour of this maximal amplitude, we measure the spectrum, more spectrum, amplitude and phases. And as a result, we obtain two contours for negative and positive vortices with negative and positive topological charges. But our experimental setup have a finite experimental error. And in reality, we come across with two contours. One contour can be resolved from one and another. For example, for initial topological charge, 5. But when we deal with topological charge equal to 15, the contour are overlapped, and we cannot talk about what science what we deal with topological charge plus or minus. Thus, the entanglement of the radial and initial topological charge does not change properties of the eigenmodes caused by harmonic excitation of the structural beam, but radically changes the properties of the entire structural Lagerhausen beam as a whole. There are fast oscillation of the orbital angular momentum and information entropy, the frequency and amplitudes of which can be controlled by excitation parameters. Nevertheless, the total absolute value of the topological charge remain unchanged for any variation in the excitation parameters, being the invariant of the fast oscillation process. Thus, thank you for your attention.
So thank you very much, Professor Vollier, for your nice presentation and the nice slides full of cats. So is there some question from the audience? Please write in the chat. Otherwise, if there are no questions, as we are a little late, I would like to thank all the speakers of this first session again for their nice talks, and we can have a coffee break now.
Thank you, thank you.
Okay, hello everyone. Welcome to the second session of today conference. We have interesting talks today. We will start with Dr. Luca Saravalli from Institute of Materials for Electronics and Magnetism from Parma, Italy. His research interests are CVD growth of 2D materials, metal organic vapor phase epitaxy growth and characterization of high-band semiconductor oxides, and metal organic vapor phase epitaxy growth characterization and modeling of semiconductor nanowires for application in sensing, modelization of semiconductor nanostructures. His talk will be on two-dimensional molybdenum sulfide for photonic applications, the CVD growth and properties. So, Dr. Luca Saravalli, the floor is yours. Thank you very much for your attendance.
Thank you. Okay. Right. Okay. So first of all, thank you for the invitation to this conference. I found it very interesting, and for giving also me the opportunity to talk about our work on this new and exciting 2D material for photonics. So here is brief outline of my talk. I will start with some motivation and why this molybdenum disulfide is an interesting material for photonic application. And I'll give you some very few examples for this application of this material. I'll show you what are the tools that are usually useful for having a basic characterization of the structure. And then I'll move to the main part of this talk, that is how it is possible to obtain this structure by using chemical vapor deposition. And I'll discuss the opportunities and challenges of this technique. And then I'll show you our most recent results on this research activity, moving them then to the conclusions. So probably all of you know that nowadays the realm of 2D materials is expanding at a very fast pace, up to the point that we can say that there are actually now 2D materials for the whole range of electromagnetic waves, starting from graphene, that is the most common one, that has the disadvantage, we can say, of having a zero gap. So we are interested in going into the range of visible light and infrared. The most one of the most interesting 2D materials is actually molybdenum disulfide, as shown here, because the gap of these two-dimensional materials falls in this range. And so let's have a quick look, general look to this material. And this is the crystal structure. You can think of it as a layer of molybdenum atoms sandwiched between two layers of sulfur atoms. And this is a monolayer, single layer of this material. Of course, there could be more of one layer stacked one on the other, but the important point is that on the plane there are strong covalent bonds, while on the vertical plane the bonds are much weaker, kind of van der Waals bonds, and this means that the most important properties come from the covalent bonds. Looking at the top view, you see that the structure has an hexagonal symmetry, and the other fundamental features said before is that in bulk form, this material has an indirect band gap. However, when you go to a few layers down to the monolayers, the band gap becomes direct. That means it can have very interesting properties for light detection and emission. Moreover, another important point that is a common feature of 2D materials is that you have a large carrier mobility. This means that you can have a material with tunable band gaps in the visible and near infrared, and also material where you have strong light-matter interactions due to a planar exciton confinement effect, and also the material with a large mobility. So these are nice properties for photonic application, and indeed, there are already a lot of examples of devices based on this material, starting from the first molybdenum disulfide phototransistor, that is shown here. This is an image of this two-dimensional material from the top. And the first demonstration was very nice because it showed you that you can have a nice photo detection. And also this early works proved that in this material you can have very low dark currents, and also you can change the photo detection, tuning detection on different wavelengths depending on the amount of layers. Then, of course, there is another interesting properties of this material, that is the strong mechanical strength in plane. This means that this material can be bending. Moreover, if in this nice demonstration, it proves that by bending your material, you can actually change the amount of photocurrent coming from this material. You go from here where you have your dark current, and then if you impinge light of a low intensity, you see that you have an increase of the photocurrent, a maximum photocurrent to a certain amount of strain, to a certain amount of bending. And this is true also for high intensity. And you see here that the photocurrent is very high in area where the strain actually results in a lower current. So all these properties open the way for a different range of devices based on piezophotonic, phototronic effect, and other combination of light and strain. And then these materials have been studied also as elements for future and actually already developing nanophotonic circuits. For example, here is a nice demonstration of how it's possible to convert light, photon light, to surface placement polaritons in a silver nanowire, and then this surface SPPPO can be converted back to exciton when these nanowires interact with the two-dimensional molybdenum disulfide layer, as indicated here. You see here there is a picture showing that the light impinges on the end of these silver nanowires and then travels up to the area where there is molybdenum disulfide, where you can have the emission of a photon. And mind you, this emission can be controlled externally by applying a gate. So these are more or less some combination of elements that you can try to put together into circuits where you can convert your exciton to surface plasma polaritons that, of course, can be used to make light transfer in smaller areas, smaller of the wavelength, and then convert them back to excitons. So I will show you these nice examples, and I think I demonstrated you that these structures are very interesting for light. Let's have a look now, closer look to this structure. First of all, it's nice to show that if you have this material on a silicon substrate with silicon dioxide layer of appropriate thickness on this range, it's actually possible due to the contrast of the light on the substrate and on this material to look at them just by a common optical microscope. And by watching on them, you see that this material has this kind of common and nice triangular shape. So on the community, they are informally known as molybdenum disulfide flakes. And these flakes, of course, can be observed with atomic force microscopy, where you can, beside giving an image on plane, you can actually measure the thickness, like in this case, where you see there is clear evidence of this step that correspond to a monolayer. And then studying other flakes, you can see that this structure are usually composed by monolayer, multi-layer, in this case, going up to a large amount of layers. Another important technique is, of course, transmission electron microscopy. As here you can see, you can, of course, go to atomic resolution and distinguish a single atom of molybdenum disulfide. An interesting point about TEM is that by looking at the contrast, it's possible to distinguish between single layer and monolayer. The reason is, if you look at the single layer, the different columns that you look at them are different because you have sulfur atoms here, molybdenum atoms here, and you look at them and you see a different contrast, of course, because the atoms have a different atomic mass. But if you go to a few layers, due to the fact that these layers alternate one on the other on the position, so the position of the sulfur here correspond to the position of molybdenum to the layer directly above, and this means that in TEM you have the same contrast. So by looking at the contrast, you can actually distinguish between monolayer and bilayer or multi-layer. Now, looking at the optical properties, another fundamental tool is Raman spectroscopy, and the reason is that for the 2D crystal structure, there are two fundamental modes, that E2G and A1G, corresponds to vibrational modes in the plane and out of plane. The important observation is that the Raman shift of these two modes depend on the number of layers. You see here for the bulk, they are more or less in this point, and their difference is about 25 centimeter to -1. But if you go down with the number of layers going to one layer, there is a distinct difference that you can see here. And this is another important tool to tell you if you have a single layer, multi-layer, and is, of course, a nice, quick and non-destructive technique. And then, of course, as we are talking about material for light application, and we are interested in emitting light, photoluminescence spectroscopy is the most important technique. And here you can see a typical PL emission spectra that is basically composed by two free peaks. The first one is called peak A, and then there is peak B, and they are both associated to exciton coming from this material. And there are two due to the spin-orbit coupling of the valence band that actually makes splitting, and you have a different energy for the exciton. Then, of course, you can have also a smaller contribution for a trion component due to the presence of an extra electron that binds with the exciton. And of course, you can do a lot of nice refined photoluminescence studies and see also other carriers, so other exciton or other components. The important point here is to notice that the peaks have a redshift when there is an increase of number of layers. So this is quite clear to see. Now, how can this material be obtained? Well, in general, talking about the realization of 2D materials, there are basically two fundamental approaches. The first one is a top-down approach that was historically the first that allowed us to have these 2D materials. And it means you start from the bulk of your material and you try to, some technique, to go down and try to obtain some two-dimensional layer. Of course, this was successfully for many materials by using exfoliation technique, either mechanical or in solution. And then, of course, there are some methods based on electrochemical approaches, and where you can actually obtain 2D layers. Of course, there is also the bottom-up approach that has advantages that you can try to control with many more parameters the material you wish to obtain. And among this technique, there is thermal annealing that's usually used for graphene, but the most important one to date is chemical vapor deposition. And if we talk about chemical vapor deposition, from a general picture, we have to consider what is the route to get to the growth of this material. So first of all, we have to consider that the ingredients, starting ingredients are this precursor, metal precursor and chalcogen precursor. In our case, this sulfur and this molybdenum. And by evaporating them, you can have a flow of atoms that can arrive on your surface, raw surface, SiO2, and you can try to facilitate the combination of this precursor to have a growth. Now, of course, depending on the growth condition, you can end up in different situations. Let's look here first on the left-hand side, and we consider we have a high mass flux, so a large amount of atoms coming from these precursors. So a large amount of atoms arrive on surface, maybe in combination oxygen and other material, and then you can have, again, two possible ways. If you have a low growth rate on the plane, what happens is that you can have a lot of these small flakes with some 3D growth on them. So not only on the plane, but also on the out of plane. And this, if you go on this route, you end up with a high density of small flakes with possibly also some 3D regrowth. If on the other hand, you try to go to a high growth rate, and this can be done by acting on some growth parameters I will discuss later, such as, for example, temperature and some presence of other elements and so on and so forth. However, then, if you have a high growth rate, you can actually have your flakes that are more favored to have a lateral growth, and you can end up of having a coverage of your surface with actual 2D materials of a monolayer, single layer, and you have kind of a nice covering with some grain boundaries coming from these flakes that combine together. Okay, this is a situation where you have a large amount of atoms arriving. If you go to a low mass flux, like shown here, then situation can be similar, but different from some point of view. If you have a low growth rate, you again have a possibility of a three-dimensional rate, but also due to the amount that you have a smaller amount of atom, you can have also a larger, higher possibility of lateral growth, and you can end up with larger flakes in comparison with this area, but with this 3D regrowth on the top. And then, as the most optimal situation is you get to have a high growth rate in plane, and you actually obtain a few density of flakes that enlarge, and you can end up with a very large flake in the range of tens, hundreds of microns with almost little or no 3D or multi-layers. Okay, the system for growth is very simple. It's basically a quartz tube where you have your substrate, ECO2OC resin susceptor, you have your precursor that can be considered used as powders for molybdenum and sulfur powders. One important point to notice is in this situation, you need to have two different temperature zones because you need to go in this temperature range to have a growth, but also you have to have a lower temperature range for the evaporation of sulfur because sulfur melts and evaporate in this range. So by adjusting these parameters, you can get to a growth rate and going through a carrier gas that usually is nitrogen or something inert. Of course, there's been a lot of work on this material, so there are different options have been explored. For a better control of the amount of material in molybdenum, you can deposit, for example, a thin layer instead of having solid precursor, thin layer molybdenum here, carrier gas, and then you actually have also sulfur powders. Also, another option, again, to try to avoid the little control you have on molybdenum powders, is to have molybdenum precursor put into a liquid solution that can be drop casted and spinned on the substrate and then loaded into your CVD growth system. On this, from this approach, another possible option is to actually eliminate solid state precursor and also rely only on precursor in a gaseous state. And then from a point of view, this means you are going actually to more of a MAO-CVD system that can give you higher rate of control of the flow of your precursor, of course, but it's a much more complex system and you need to use this precursor that have some safety issues and you need a more complex system to control. It should be stressed that a fundamental element in order to have 2D growth of this material is the use of promoters. It's been shown that if you don't have any of these materials that can help the growth on 2D, it's very difficult to have large size flakes. And a lot of amount of different promoters have been studied in these years. You see some, these are organic ones, but there are also inorganic like carbon, some kind of carbons, some components with sodium and so on and so forth. Basically, there are, again, different possible approaches. You can have a promoter solution, spin cast on a substrate next to a growth substrate, or you can also have everything put together on the growth substrate directly. So to sum up, in general, what is the important point about CVD? This is a list, but the two most important in my view is the first one is an expensive fabrication technology. Really, you don't need a large amount of money to work on this, and it's possible to obtain atomically thin films. Challenges, however, still remain to be addressed. Of course, the growth of very large single crystals. And another important point is the control of doping, and also the need to have a reliable and reproducible control of the properties of your nanostructure, both morphological and from rheological point of view. Okay, now I'd like to show you very briefly what we've done in these last years on this topic. The first study we did was studying the effect of the promoter. In this case, we use this organic promoter, PTCDE. Then we spin on a substrate next to the growth substrate. The first observation is in this configuration, the flakes preferentially grow only in some zones, indicated here, and reproducibility was not optimal. So what we did, we tried to have a look at the system by using this configuration to study what is the effect also, not only the flow of precursors, but also the flow of the promoter. And you see our results here. This is the sample, and we looked at different areas of the sample. Z1 is the point closer to the promoters and farther from the closer to the precursors, sorry, and farther to the promoter. While Z3 is the area where it was closer to the promoter. And you see that the structure are quite different from one area to the other. In this area, we had some triangular multi-layers, shown here with these dendritic structures. In Z2, in this area, we show a triangular crystal affected by some three-dimensional overgrowth. And in Z3, finally, we obtain a monolayer with a high coverage in just a few layer islands. And this was confirmed also by looking at the Raman characterization, where you see the shift of the peaks, and also looking at the PL emission, where you see here that there is a consistent difference in the emission for the different areas. So what happens here in the growth, we believe can be understood looking at this picture. You have the flow of precursor from this side, and you have a backflow from a promoter on this side. So here, the promoter arrives not in sufficient quantity to favor a two-dimensional growth, and actually you have this structure, dendritic structure, with also some overgrowth. Then, if you move along this direction up to the end, you actually can get to a more nice triangular shape with very little multi-layer growth. And so this is more the optical situation. Then another point we studied up to last year, we wanted to study the effect of gold nanoparticles on the growth of these flakes. This is important because gold nanoparticles are also used in these materials to have a structure where you couple the exciton coming from MOS2 with the plasmon connected to the gold nanoparticles to have enhancement of light. So we wanted to see what happens if we put these gold nanoparticles before the growth and not after, as usually done. And to do that, we actually compare the situation with two samples grown in the same condition, one with gold nanoparticles and one without them. And you see the difference is quite striking, because with gold nanoparticles, there is a strong enhancement of lateral growth, and we are able to obtain very large, not very large because this is 5 micron scale, but larger than in the similar case without the gold nanoparticles. So this means the gold nanoparticle can act as seeds for the growth of flakes. And by studying by FM the frequency of monolayer, bilayer, trilayer, and checking them by Raman shift, we think that the situation is that gold nanoparticle, after acting as seed, favor the growth of two-dimensional materials. And then if you increase the amount of material coming to the substrate, you can have also the synthesis of bilayer and trilayer islands. On the last point, we are now starting, we have started to grow with liquid precursor. The work I showed before was done with solid precursor. Here with liquid precursor, we already observe there is a nice and better control in the flow uniformity. And in this way, it's possible to have more reproducible and also more homogeneously distributed on the surface flakes. And you see, we also did a study as a function of the flow of inert gas, nitrogen, coming here. And you see that going to 300 ccm, we are able to obtain flakes with a large lateral size up to 100 micron. Okay, as a conclusion, I hope I've demonstrated, I showed you that this material is very interesting for photonic application because you can tune your band gaps in a material where there is a strong light matter interactions. And this nanostructure can be characterized by different techniques, morphological structure, optical properties. And CVD, in our view, is the ideal method because it's not very expensive and it gives you various possible options to control precursors and promoters. And this has been demonstrated a very powerful technique to grow this kind of two-dimensional materials. In particular, in our group, we studied the effect of the flow of this promoter and of gold nanoparticles in the growth of monolayers, few layers. And also we studied the effect of the flux of nitrogen carrier glass when using molybdenum precursor. So thank you for your attention. Would like to acknowledge the work of other people in Parma, also in Pisa, and our collaborators at Shenzhen University. The last point, if you have more interested in this topic, we have just published a review on this topic. And thank you very much again for your attention.
Thank you very much, Dr. Saravelli, for the nice presentation. We have time for a couple of questions. Is there any question from the audience? Please write them in the chat session if you have so. So there seems no question. So thank you very much again, Dr. Liko, for this nice presentation. And we are moving forward with the second talk of this session. It will be given by Amardeep Bharti from Elettrosynchrotron, Italy. The title of talk will be The Times Results SAC Study on Nucleation and Growth Kinetics of PVP Stabilized Silver Nanoparticles. So the floor is yours, Amardeep.
Good morning, everyone. In just a moment, I'm sharing my presentation.
Okay.
So I think you can see my presentation, right?
Yes, we can see. Please go to full screen.
So good morning to everyone. So today the topic of my talk is basically the reaction and the growth mechanism of the PVP capped silver nanoparticles. And as far as we know, this nanoparticle, especially a metal nanoparticle, either gold, either platinum or a silver nanoparticle, they are widely used in each application. So it's a widespread application. And the people who are working in the material science or in the chemistry or in the biotechnology, they know much about this nanoparticle. So that is the reason I'm skipping about the application part of this nanoparticle. So I'm just pointing out how we can study the actual growth of this nanoparticle and this effect of the capping agent over the growth. So I split my presentation in 3 parts. First is the introduction part about the synthesis procedure. And then second part is motivation behind this experiment, why we choose to study this PVP stabilized nanoparticles. And finally, we will discuss about the SOX code and the analysis part of these nanoparticles. So in this work, we have chosen the radiation-induced synthesis of the nanoparticles. The motivation behind to choose this reaction procedure, except like there are other procedures which are much more simple, like material with the using the chemical reduction. But the beauty of this radiation-induced synthesis, we are avoiding the external reducing agent so that we can study the pure interaction between the metal core and the capping agent. And this reaction goes like we have a nano metal precursor in between the water solvent with the same amount of the precursor capping agent. And when the X-ray start hitting this sample and the water is basically radiolyzed under the radiolysis and split into the different parts, and it produces the aqueous electrons and the many things which are some of the reducing agent, like this aqueous electron as a reducing agent. But these OH radicals are basically oxidation agent. So the reaction goes like there is a radiation induced radiolysis. And when these particles like aqueous electrons or the hydrogen radicals came in vicinity of the metal ion, so it's convert the reduction to the metal ion, metal nanoparticle, and then after that nucleation will start. However, when it starts interacting in the vicinity of the OH radicals, it possesses actually in a reverse direction, to start oxidizing to the back of the ions. So first thing is to control the OH radicals, the oxidation. So we can use the scavenge agent to capture these OH radicals to avoid this oxidation. So the first step was to use actually investigate the role of the scavenger agent. So we perceive the reaction with and without the scavenger, and we see that even without the scavenger, the radiation-induced synthesis actually proceeded in a positive way, and we got the nanoparticles. However, the intensity, you can see the difference in the intensity. So that is the number of particle came out with the use of the scavenger is very large in the amount. And then finally, we study the stability of this nanoparticle up to 70 days, and we found that they are highly stable nanoparticles. And that means even this reaction can be proceeded with scavenger or without the scavenger. And scavenger is nothing but the simple ethanol or other similar chain group. And then finally, we studied this reaction with the time, and we study with the increase in the integrated dose, the particle size is growing. So please keep in the mind that this integrated dose is very small. So it's like a 0.05 kilogram to 0.04 kilogram, so that this area we can cover even in the laboratory with the laboratory X-rays rather than the synchrotron also. So that means this work can also proceed for the industrial application if one can really believe in the radiation-induced synthesis process. And the second part of that, we study the role of the X-rays energy towards the growth. And we choose the X-ray energy from 10 kV to 25 kV. And we see that there is really a growth in the particle. The thing is that this experiment was not so simple, because if we want to see the actual role of the energy, and you can see in this graph, the X-ray cross-section area and the percentage absorption of the water is decreased with the increase in the X-ray energy. So to study the real mechanism behind the energy role of the energy, we keep the integrated dose constant with the product of the energy and the radiation time to make it a constant. And then we see that there is really a growth. So that means with the increase in the X-ray energy, there are the possibility of an production of this aqueous electron is very high. So that is the role of actually X-ray energy. And then we study basically the precursor to capping agent ratio. So we see that there is actually a critical point where the precursor to capping agent ratio leads to enhanced the reaction, and below which and above which the particle size remains in a smaller range. And this case is not only in the X-rays, but also in the microwave radiation-induced synthesis. So that means the more important part is to study the precursor to the capping relation. So this is the motivation behind our experiment which trigger us to investigate the role of precursor for the growth of the nanoparticles. And rather than just only varying the precursor to capping agent ratio, we chose a different precursor, like the same precursor family like a PVP, but with a different chain length from 10,000 to 1,300,000. So it's very large, from smaller to the large. And then we study the growth mechanisms using the SARCs. So this is the beamline setup for the SARCs experiment. Here you can see the incoming X-rays, and here is the sample holder. This is basically our vacuum chamber with the scattering, and this is a detector. So this detector to sample distance can be tuned from smaller to the higher to make it the Q range with respect to the particle size. So in our beamline, we can study the particle size from 1 nanometer to the maximum of 100 nanometer. And this is actually basically a capillary holder. And you can see we split this capillary into a different section of the reaction, with each point have a relative distance of 1.5 millimeter, because our beam size is 1 mm in the horizontal, and in the vertical is 10 to 20 micrometer. We wanted to see the growth in single capillary so that the reaction condition and the environment would be the same for all the series. And basically we have the 6 series. And for this experiment, we first made a fitting model. And so not going into much detail in the mathematics, I just explain a little bit about it. If we just consider this is the metal nanoparticle with the metal core, and outer surface area is covered by the polymer. So there is basically a 4 different parts, 1, 2, 3, and 4. The first part is basically from the core, like it's a metal core, which is basically in the spherical range, and this is the form factor of the spherical sphere. And this second part is belongs to the polymer, which is basically a PVP in our case, which is a Debye Gaussian chain. So this is the form factor of the single polymer. And the third term is basically represented the interaction between the polymer and polymer. So it's the self-interaction term between the polymer. And the fourth term resembles to the interaction between the metal core and the interaction of the polymer to the metal. So these are the 4 terms which is actually govern the full fitting code. And we modified this because previously this PG model was built for polymer chain, but in our case we have replaced the core of the polymer with the metal. So we modify this code to the modified code is like the same. It's a little bit but the fundamental is same, but it's a little bit defined in more appropriate for the metal nanoparticles. And here you can see the first with the PVP. P represents the PVP, silver is the silver, and 10 is basically the molecular weight of the chain. And with that time, we can see the increase in the intensity of the scattering. And these graph represent the bare polymer in the water solution without silver nanoparticles. And here first we fit the polymer and calculated the radiation of gyration of the each polymer. So radiation of gyration is basically, if you see this picture, so this is basically a radius in which you can assume the most of the particle, most of the polymer mass is concentrated. So here it represented like the radius of gyration, the polymer is inside, but it could be could be the outside in this tail or maybe the outside. But the radiation gyration represent the most concentrated part of the mass of the polymer. So you can see with the increase in the polymer weight, molecular weight, the radiation of gyration is increasing. And but for the last one, like the 1300, it's a small range. That means so center of this is really concentrated, but the tail is a little outside of this radiation of gyration for the highest polymer weight. And then if you look at in this graph, this is a fitting of the SARCs. This is the red one is the experimental one, and this golden one is the fitting. And we split this fitting into the 4 different segments to better understand the contribution of each part to the scattering. And this blue one is basically scattering from the core. And this green one is basically the chain itself interaction. And this golden part, the light golden part, is basically the scattering from the polymer chain itself. And this pink one is the interaction between the core and the polymer. So this is the four different part of the scattering intensity, and the resultant is basically this. So with this fitting, we can calculate the each part, like the radius of the core and the radius of the polymer, and also there is an interaction between these two elements. And here I just show the outer, like there are 6 different polymers, and this is a final segment after 1 hour, like this for final one for each fitting. And then with this information, we try to make a model of the growth of these nanoparticles. So if you see for the very first series of AGP10, the first 10 second is basically blank for us. This is the time where X-ray induced water radiolysis is happening. And after the 10-second, the reaction is actually start. And this red line is showing the core radius of the core only, not the polymer. And this is actually the polymer, because polymer is for this P10 is of 1.7 radius of a nanometer of radius of gyration, and it remains constant for full segments. That means the polymer is not destroyed at all. And this blue part is actually the density of the particles. So initially the particle density, like the very smaller particle, there are many particles in the samples. And after that, in this part, in the 100 seconds, so this is a self-rapid quenching of relaxation of the core. So that means at this stage, there is enough silver particles in the polymer that can make a nanoparticle. And this self-rapid quenching is happening. And after this, this growth is started proceeding in a positive way. And if you see that this is basically a sigma. Sigma is the polydispersity index, and the polydispersity is decreasing with increasing in the time. And this is a number of aggregation number of the polymer to the attacher to the core. So from this, you can see the number of polymer is attaching on the surface to cover the surface area. And this is in the large number because our polymer is very smaller rather than in compared to the core. And if you see in this graph, there is a background. Background is basically your water content. So if you remember the first process here, so this reaction is triggered with the degradation of the water in the vicinity of radiation use. And this water is also serve as a stabilization for the polymer, excess polymer chain, which is not attached to the silver nanoparticle. And here you can see initially there is a water content inside the polymer. And here at the 100 second time, when this self-rapid quenching is happening, the water molecule is started in really in a very small amount. This is showing that the polymer is actually start attaching on the surface and make it a polymer. And after that, this is the growth. And with the growth, you can see of course, there is like a surface of the particle, which is a hairy particle because of the smaller polymer chain, and the water is also increasing. And this is the mechanism of the growth of the meta nanoparticle.
1 more minute, Amari.
Okay, just a second. And finally, we see the contribution of the polymer chain over the growth of the nanoparticles. And you can see the growth rate is increasing with increasing the polymer chain number. So that means the particle can really be getting a more if you see like a polymer in the large range. So more and more number of silver ions can be attached in the single polymer chain, and when it compress, it make it a bigger particle in a smaller time. And here you can see that plot of the water radical in the final system. And here in the smaller particle, there is the water stabilized with the polymer. And in the final, there is no water content inside the polymer chain, and it is the pure nanoparticle. So you can see within case the polymer weight, the less number of water is remain inside the system, and the particle is growth in the with the size. And this is what we have studied in this experiment. And the concluding point is that here you can see we did not use any reducing agent. So there are large studies on this nanoparticle growth is either with the EXOF or the SOX techniques is available. But the point is when we study, when you want to probe this system, you are also reducing. So that is the important point. If you're using the water as a solvent, you're simultaneously reducing the system with the probe. So that is the important point to remain in mind for this study. And thank you very much.
Thank you very much, Dr. Bharti, for this interesting talk. Actually, we are pretty behind of our schedule, so I will skip for the question session. If you have some, you can ask through chat directly to Dr. Bharti. So thank you again. Thank you very much again for your interesting talk. So our next speaker is Dr. Zeynep Baz from TÜBİTAK Defense Industries Research and Development Institute. The title of her talk will be the Surface Enhanced Raman Scattering Properties of DLC Films on Gold Nanoparticles. So please go ahead, Dr. Zeynep.
Okay, is the presentation visible?
Yes, we can see it. If you go to full screen, it will be better.
Okay. My subject, surface enhancement, Raman scattering properties of DLC films on gold nanoparticle. Okay. In the presentation I will make today, the topics will be as follows.
Actually, the screen is not changing. The screen is not changing, Dr. Zeynep. The one you share is not the presentation mode, it's the overall view.
Okay. What's the problem? Is the presentation visible and slide?
Yes, I can see, but it's like the slide view. It's not in presentation mode. I can see the left section with the all slides. So when you change your slide, it is not changed on the screen.
Okay. And next, visible?
No, we still see the first slide. Okay. Now it's in the, yes. No. Buradan gidebilirsiniz. Yes, I can see it, but not in the presentation mode, as I said.
Okay.
Okay, we can go through like this.
Okay. In the presentation I will make today, the topics will be as follows. Briefly in introduction and DLC and properties, thin film deposition methods and microwave ECR system, characterization of gold nanoparticle, DLC and gold DLC thin films and results. DLC thin films were deposited on glass and gold nanoparticle coat substrate by microwave ECR plasma deposition system at room temperature. Methane gas was used for producing the plasma UV spectroscopy, XRD analyzed, Raman spectroscopy, atomic force microscopy were performed to characterize film. Gold nanoparticle with a size of about 60 nanometer were obtained in the form of nanospheres, and the size is suitable for SARS experiments. Enhancement factor of DLC thin films produced on gold-coated substrate were calculated. Nanoparticle burada nasıl nanoparticle have been used in science and technology in research years because nanomaterials gain a number of properties different from the molecular space. These properties vary greatly depending on the shape and size and the material forms which the nanoparticle are centers. Because of these extra properties, nanoparticles are used in new chemical and biological sensors, electro-optical devices, high capability data storage, and surface enhancement Raman spectroscopy. Diamond-like carbon properties. There are many allotropes of carbon, the most well-known being graphene and diamond. Materials in this group can be classified under traditional metal, ceramic, or polymer classification. Carbon allotropes have emerged as a result of the bonding of 7 subgroups of carbon atoms in different ways, and each exhibits different properties. These allotropes, diamond, graphene, fluorine, amorph carbon, suggest.
Değişmiyor slaytlar. Yandan tıklamanız lazım şey olması için.
Hiç mi değişmiyor şu anda?
Şu an 4. slaytı görüyoruz biz.
Şu anda?
Şu an hala 4. slayt. Siz paylaşırken büyük ihtimal program paylaşmışsınız. Programda PowerPoint olarak paylaşmışsınız. Presentation'ı paylaşmadığınız için presentation modunu aldığınızda biz göremiyoruz.
Nasıl yapacağız onu ki? Onu nasıl yapmam gerekiyor anlamadım ama.
Share screen'den belki ekranınızı paylaşabilirsiniz.
Öyle yapalım o zaman. Tekrardan mı yapayım? Çünkü böyle çok sağlıklı olmayacak. Ben de hani şey kısmını görüyorum, gereksiz yere. Almış olduğum notlar gözüküyor. Bir saniye.
Ekran olarak paylaşın.
Şimdi şöyle yapalım o zaman. Bir saniye. Slide açayım. Bunu ekran olarak nasıl paylaşacağım? O kısmı halledemedim ama bilemedim şu anda.
Share screen'e bastığınızda sol üstte screen var. Ona basarsanız bilgisayar görüntünüzde ne varsa onu görürsünüz. Onu paylaşırsınız bizle.
Şöyle oldu mu acaba? Hala mı yok?
Şu an bir paylaşım gelmedi. Ekranınızı göremiyoruz sizin. Paylaş dediniz mi?
Paylaş dedim evet ama ekran size gelmiyor evet. Şimdi tekrardan Zoom'a girmeye çalışıyorum. Ona da giremiyorum. Okey. Şu anda ne durumdayız? Ben hala ekrandan paylaşım yapamadım.
Yok, şu an evet bir paylaşımınız gelmiyor maalesef.
Şöyle ki hani Zoom da şu anda çalışmıyor. Bir kilitlenme var. Tekrardan giriş çıkış mı yapayım bilemedim.
Sesiniz ve görüntünüz net geliyor. İsterseniz siz bir gir çık yapın. Ben bu arada sizden sonraki konuşmayı alayım. Siz sonra
Bence
devam
öyle
edin. Olur mu?
yapalım. Ben bir ayarlamamı
Tamam.
yapayım hocam. Öyle
Tamam.
yapalım.
Tamam,
Sağlıklı
o
değil
şekilde
şu anda.
So there's a technical problem. So we will skip to the last talk, and after Bahare Kakkar Jalali talk, Zeynep Baz will join again and present her research. So Dr. Jalali, are you here? So the talk will be given by Bahare Kakkar Jalali from Kharazmi University, Department of Physics. The title of the talk will be Differential Evaluation of Normal and Cancer Breast Cell Lines by Optical Methods. The floor is yours. Thank you very much. We cannot hear you.
On behalf of my assistants, Dr. Salmani and Dr. Shahi, to present our experience results entitled Differential Evaluation of Normal and Cancer Breast Cell Lines by Optical Methods. First of all, I should say a brief overview of the study, introduction including some information about breast cancer cell lines and the optical method which is used in the system.
Haldun Bey,
The second step
tam ben bu
is
konferanstaki
sample preparation.
başkanlık
The
yaptığım
third
session'dayım da
refers to
açamadım.
the
Kusura
theory
bakmayın.
of the
Buyurun.
scan to evaluate the nonlinear refractive index, and then investigation of the specific result of breast cell line cancer and discussion about its characteristics compared to normal cell lines. And the last step would be conclusion. As you see in this picture, which is reported by WHO in 22, most part of the world face a very high human development index all over the world. I mean the dark blue part. So it shows that the prevalence of cancer is rising day by day. If we want to focus on one of the most prevalent cancer, we should mention breast cancer among female. In this diagram is clear that in some areas the rate of mortality close to incidence. So diagnosis, therapeutic and imaging of cancer is a really challenging issue these days. As a result of our study addresses the basic part of diagnosis with all optical methods for evaluation of differentiation of cancer cells for normal cells of breast cell lines. Regarding this, we chose two cell lines, one of them a cancerous named MCF7 and the normal one named MCF10A. We consider MCF7 as one of the common cell lines for most prevalent cancer cells, and MCF10A because they both have the same biological structure. For example, both are epithelial cells. For cell culture conditions, we need some material that can simulate an environment like a tissue for the proliferation of cells, such as MDMA, FPS, penicillin, and streptomycin. After placing a slide of lamellar on the bottom of each well of each well plate, well of 6 well plate, cell culture is added, and after 24 hours, all samples are prepared. I should mention that we consider 4 samples uh, for every cell lines because the arrangement of cells is not the same as each other, and we want to improve the accuracy of data by different samples. After that, all lamellar is fixed by paraformaldehyde, and layers were prepared for arranging in optical methods. The first step is adjusted based on a linear absorption coefficient by 532 nanometer continuous wave Nd:YAG laser and a detector. As you see, alpha can be measured by the equation is Beer-Lambert law. Here, the schematic optical closed aperture Z-scan is shown. By crossing the sample, the focus laser beam passing through the aperture center on the axis of the beam, moving the sample over the z-axis around the focal points from minus z to plus z will lead to various variations in the incident beam intensity. This trend can cause changes in the refractive index of the material, leading to the variation beam radius of the aperture plane. As a result, the nonlinear refractive index of each material could be measured by transmitted power. In this study, a 532 nanometer Nd:YAG laser with 110 milliwatt maximum output power was used. The laser beam will be focused by an 80 millimeter lens's focus length, and the beam base would measure 44 micrometers. Then the laser beam passes a nonlinear sample, making a change in the total refractive index is proportional to the beam intensity and material's nonlinear optical behavior. You can see this in equation 1. A laser incident beam with Gaussian profile intensity induces a nonlinear refractive index in the sample and works like a positive or negative lens to change the wavefront. So N2 is calculated by equation 2. All parameters are listed here. And the other most important of them is delta TPV, difference between maximum and minimum of normalized transmittance power. I will show you in further graphs. The linear absorption coefficient, these samples have been calculated by 1 millimeter sample length and the slope of each line. They can be seen in table 1. It is obvious that linear absorption coefficients are much more, so the cancer cells are more attenuator than normal cell lines because cancer cells uptake more nutrients. On the other hand, this clear difference would be a positive point as a label for every cell to make difference for each other. All nonlinear effective indexes of MCF10A and MCF7 are shown in both graphs. When transmittance peak comes after the valley N2 is positive, and when transmittance peak before the valley N2 is negative. Also, the exact sign and magnitude of each sample are observed in the table, so there is a very clear difference between N2 of MCF7A, MCF10A, and MCF7. This parameter for the cancer cell has a negative sign, and in terms of magnitude is much more than the normal cell. Of course, it is noted that both magnitudes have the same order. In conclusion, both normal and cell-breast cell line display nonlinear optical behavior. Based on graph A, the absorbance of MCF10 cells is more than the absorbance of MCF10A in the linear region. Based on graph B, the sign of MCF10A and MCF10 are both positive and negative respectively. So in MCF10A, self-focusing, and in MCF7, self-defocusing behavior are observed. By comparison, the nonlinear in this table, it is clear that the difference between normal and cancer cells in nonlinear behavior is more accurate than linear behavior because not only the magnitude of N2 but also the sign changes. In addition, the simple method could be reported many times without any making change sample properties. Thank you for consideration and your time dedicated for my presentation. I am ready to answer your question for clarification.
Thank you, Ms. Jalali, for your presentation. If you have any question, simply email to the email address that Ms. Jalali wrote in the chat session. So we are continuing with the last talk of today with Dr. Zeynep Baz from TÜBİTAK Defense Industries Research and Development Institute. So give one more try. And please keep in mind that after this talk, we would like to turn on every attendee's camera and take a snapshot before the lunch break. So be ready for that.
Okay.
So,
right.
Unfortunately, we do not see your screen. It's the same as previous, Dr. Zeynep.
Okay.
So, there's a problem with your voice. I cannot hear you. We are really behind our schedule. Please keep going with this configuration. Dr. Baz, are you there? So there was a problem, I believe. So okay, wait for one more minute. If everything is fine, then we continue. We ask for a quick presentation.
Dear Professor Umutaker, we can take a photo if you are agree in this.
Yeah,
case.
yes. Actually, yeah.
Okay.
Please,
We-
can
okay.
everybody turn on their camera? We would like to have a group photo.
Dr. Süleyman, thank you very much for attending the conference and being the section chair. Thanks for your support.
It's our pleasure. I'd like to thank the organizing committee for making all these valuable scientists to come together. Hope to have this conference face to face next year.
Hopefully. Okay, I'm checking if, sorry. Okay, I'm checking if everyone is ready. Please, please, could you open your camera, dear participants? Thank you. I'm waiting for you. Yes, please. Okay. One screenshot. Yes, ready. Okay, but please one more. I'm sorry. Yes, now is okay. Please, let's laugh more, please. Okay, yes, now is good.
So, cheese, everybody.
Yes, thank you. Thank you very much. And see you after the lunch. Thank you very much.
So the third session will be at 1 o'clock. So it's
Yes,
the lunch
correct.
break now.
1 o'clock.
Take a quick lunch and see you at 1 o'clock afternoon.
Okay, see you again.
Have a good day. Bye-bye.
Good afternoon, everybody. And I would like to start the third session of the second day. The first speaker is Professor Alpan Bek from Department of Physics of Middle East Technical University. Professor Alpan Bek. No, it's just a minute. So I think it's the time we can start the presentation of Professor Alpan Bek. The title of talk is LIPSS for SERS, metal coated direct laser written periodic nanostructure for surface enhanced Raman spectroscopy. Can you hear me, Professor Dr. Alpan Bek? Okay, I can see your screen just now and voice is also okay. I would like to pass the microphone to you to start your invited talk. Thank you.
Okay, thank you so much for this introduction. I'm associated with the physics department of the Middle East Technical University, and I also do conduct research in the Center for Solar Energy Research and Applications in Ortagunam. And I would like to thank all the organizers for inviting me for this nice conference. And as the theme is light and light-based technologies, today I picked up a theme which goes very well with the general center of weight of the conference. And the title is LIPS for SERS in short. Now I will talk about what LIPS is, what SERS is in a while, but essentially I will present you an application in which we use light to structure material, which in turn has properties that structure light. Okay, so light works for modification of matter, and matter works for alteration of the properties of light. So now these are LIPS is a relevant, relatively recently re-explored field of laser materials processing technique. It's laser-induced periodic surface structuring, stands for that. And it's a direct laser writing technique. With this technique, you do modify the material surfaces in a periodic fashion, in a self-organized manner, not by scribing, but in a self-organized manner. When you have this structure at the nanoscale, it can be used to further work as a surface enhanced Raman spectroscopy tool when it is coated with a thin noble metal layer. So as an application, I will show a couple of different regimes. And let me now move on with the first a brief introduction to Raman spectroscopy. The talk is going to be centered around the applications of Raman spectroscopy. Now Raman spectroscopy is an inelastic scattering of light, and in the perspective of light. So when the light energy is altered upon scattering, such as a portion of the light energy is transferred to matter, or a portion of the energy in the matter is transferred to light. This sort of scattering is referred to as the inelastic scattering, so non-energy conserving scattering. And Raman is a beautiful method which we use to explore internal potential energy landscape of molecules or crystal materials. And these are, the inelastic scattering is due to internal vibrational or states in molecules or phonons in crystal material. And the transition taking place in a manner that when the electrons are coming back to the original states, if they go down below their original energy upon scattering, and the photons gain this additional vibronic energy. And if they go down to a state which is slightly higher than in energy from the originating state, then the photons have to supply this additional energy to electrons. So the photons have less energy. So this sort of energy altering scattering is Raman, and when the photons have less energy, then it's Stokes, and when they have more energy, then it's anti-Stokes scattering. Now, for what is this good for? Well, it can be used for identification of molecules. So, because every molecule has a different vibronic energy landscape. So these energy differences from the original excitation energy of the electron and the emitted energy upon returning electron, the energy difference between them is specific to the vibronic energy differences, and vibronic energy differences are specific to molecules. That means the Raman photons, position of the Raman photons in the energy domain relative to the original excitation is a very specific fingerprint to a particular molecule. Now, this is good on one hand, because you can identify by looking at the position of the Raman peaks, you can identify the molecules, but on the other hand, this process is highly inefficient. The scattering cross sections of Raman scattering is very low when compared to energy conserving Rayleigh scattering. It's about 1,000,000 to 1 billion times less probable. So now that makes it less impractical than other spectroscopy techniques because the signal levels are too low. So on what we have to apply some amplification schemes to make good use of Raman scattering in identification of molecules. In that respect, a phenomenon called surface enhancement comes into play, which is actually of two different origins, physical and chemical. Here I focus myself on the physical origin. Now, it was found that in the near field vicinity of small nanoscale noble metal particles, the incident photon field is intensified by large factors, but this intensification takes place only in the near field of these metal nanostructures. And you can see this from a simple Gauss law point of view. Smaller the radius of curvature, more the free electrons are accumulated on the surface of metals, and more electron density means more response field by the electrons to the incident radiation. And the total field is the sum of the response field plus the incident. So in the near field, we expect an intensification. This is pretty much like the antenna theory. The poles of the antennas do have very strong electric field, where here our antennas are of nanoscale when it comes to visible radiation, because the wavelength of visible radiation is at the nanoscale. So our antennas have to operate also at the nanoscale. Now, when you have a single noble metal particle, such as gold or silver metal particle, in the vicinity of this metal particle, there is a certain amount of enhancement, let's say about a factor of 2 or 3. Now, however, when the metal nanoparticles cluster together, they make they compose not only near field at their exterior, but they also compose these nanoscale gaps in between them. And it turns out that the field enhancement right at the gap becomes still more stronger than the field enhancement at the periphery. Okay, here is an example to that. So if the black curve shows normal Raman, where it is so low that you don't see anything actually, and you do regular surface enhanced Raman scattering around the surface of the particle, you get some amplification and start to observe some distinct peaks. But when the molecule is right here at the gap, the intensification is so high that you can now clearly see individual vibrational levels, and even a spectrum from a single molecule is possible. So you can use this scheme to identify even single molecules. And there are many different top-down approaches for fabricating these antennas in a clever fashion in literature. So nanorod dimers have been demonstrated, two-dimensional bow tie antennas have been demonstrated, even 3D versions of the bow tie antennas have been all demonstrated in the literature. A good review you can see in this link that I quote below. Now we have performed several experiments in that sense. Our primary aim was to reduce the costs of fabricating surface enhanced Raman scattering, because why? Well, these top-down approaches typically require very costly technologies such as e-beam lithography, etc. And when you don't have access to such costly technologies, you have to refrain to low-cost approaches. But albeit you, of course, have a trade-off. For example, liquid synthesis is a technique in which we can synthesize metal nanoparticles. However, we have no control on the exact shape or location of the particles when we fabricate or decorate a surface with these in solution synthesized metal nanoparticles. Okay, that's the trade-off. Nevertheless, it lowers the costs quite a lot, and the enhancement factors that one can attain can be really high. And I showed here one example from gold, silver nanoparticle work we have done before, in which we have simply spray coated surfaces of silicon wafers with in solution polyol synthesized silver nanoparticles, and we have observed quite effective enhancement when we did the experiment on a model molecule such as this one that I show here, brilliant crescent blue. You see the Raman spectra is very clear, signal to noise is great, so you can pick up a certain vironic state and even concentrate your interest in that range and make a nice map out of the distribution of your molecules on a surface decorated with metal nanoparticles. And you can actually perform simulations on the expected Raman enhancement and compare it with those that you observe experimentally and confirm that what you're receiving is from a plasmonic response of these metal nanoparticles. Well, another example, the material, the particle in solution synthesized particle do not always have to be in the nanoscale domain. Here is an example from gold, actually, in which we have fabricated not nano but micro spheres. Nevertheless, our microspheres had nanoscale features on their surface. Okay, so nanoscale is essential for enhancement of the field in the vicinity of the surface, but the original carrier particle does not have to be itself in the nanoscale. Okay, that's an example to that. So again, we have in solution synthesis of mostly microscale gold nanoparticles. Gold microparticles, sorry, and this is a TEM image of such a such gold nanoparticles. You see, and this is 50 nanometers, so the range of the size, the overall size is quite above 200, 300 nanometers. But you see the sharp corners and edges are below 50 nanometers scale, and those spikes that we call on the microparticles are the origin of enhancement of the field. So you see here, for example, you can compose a surface, decorate a surface in a closed pack fashion using these micro particles, and you can have a very nice coverage of the macro scale surface area with a quite dense amount of field enhancing, highly field enhancing so-called hotspots. Okay. Now you can use this also to identify trace amount of molecular species and have that. And these are quite how to say widely adopted classical examples to surface enhanced Raman scattering and substrates which are fabricated at low cost. Now, I here quote also the respective size. The size ranges from around a couple of 100 nanometers up to about 0.5 to 1 micron scale in this example. And when you take a look at the performance of these metal nanoparticles, you can see even a 10 femtomolar concentration of a certain molecule that we picked, crystal violet in this case, is discernible. So now you can make a limit of detection study by plotting the Raman intensity against the concentration of molecules. And as long as you're in the linear regime, that you're out of saturation. So the curve can be used as a calibration curve to figure out about the concentration from your Raman signal. Okay. Now you see here we have about around 10 femtomolar concentration demonstration with this gold microparticles. Okay, now the actual topic that I would like to switch now is what I want to focus today more, and it's an alternative technique to in-solution synthesis of surface enhancing substrates, surface enhanced Raman substrates, in which we propose to use lasers, ultra short pulsed lasers to structure the surfaces at the nanoscale. Structure surfaces of what? Structure surfaces of normally flat semiconductor or metal materials. And this has been demonstrated in literature plenty of times, as there are works as old as 1965, you see here in this view graph, on irradiation of an intense laser pulse on a germanium sample. The authors have figured out about these periodic structures forming. And the actual diameter of the focal spot was much larger than the period of these structures. So this one full area is about the size of the focal spot. So the periodic structures are much smaller in dimension than the actual focal spot. So this is not a regular laser scribing approach. Okay. Now, it has been demonstrated several times later on in literature, not only once. There are more recent work as well. People have tried to gain control on this self-organized fashion laser-induced periodic surface structuring technique by trying to extend the structuring. Several examples have been demonstrated with very nice control on not only one dimension, but 2 dimensions. One can write even 3-dimensional features at the nanoscale in a direct writing fashion. And here are a few more examples, which I would like to mention briefly about. Now, it turns out that there are two different laser-induced periodic surface structuring regimes, depending on the laser parameters, essentially. And it turns out that there's this normal and anomalous LIPS regimes. And it turns out that when the structure in a self-organized fashion appears perpendicular to the laser polarization, we refer to this as the normal LIPS. But when the structures occur in parallel to the incident polarization, this is an anomalous regime. Nevertheless, there is still some surface structuring. Now, here are a few more detailed examples from literature where you see there are really nicely periodic, strongly periodic structures appearance. And these periodic structures can be extended by moving your pulses and overlapping the pulses one after the other next to each other, and scanning these irradiation lines in a raster scan fashion, pretty much like scanning probe techniques. And both anomalous large area surface structuring or normal large area surface structuring has been demonstrated. Now, one thing I would like to attract your attention to, now if you take a look at this carefully, I think move a little faster. Now, the structuring can be fabricated not only on one single material, it's kind of universal as long as the materials contain sufficient amount of free electrons, free charges, which can interact with light in a strong fashion. So metals and semiconductors essentially, and you see here the raster scan fashion, how you can write large areas in this fabrication scheme. And you see here the pink spot actually represents the dimensions of the focal spot, where the period is smaller than the focal spot itself. Okay, and the good thing is this can be used also to structure surface of not necessarily very good conductors like metals, but also on semiconductors such as silicon. And it becomes quite relevant because silicon has quite a lot of applications. It's a well-proven material, it's biocompatible, etc. So silicon is highly interesting for many different reasons. And we can show here that we can really structure in a periodic fashion the surface of the silicon in very extended areas. Now you may wonder what is the period of these structures, and before I have a video in which I show how large an area I mean. This is a full wafer, 4-inch wafer, and you see the line which is modifying the surface in real time. The colors, opalescent colors here confirm that there is some photonic structuring on the surface. Okay. So, and this is a static view of an example of 3 centimeter by 3 centimeter. So we are talking about really macro scale large areas. Now here is one interesting observation I'd like to mention briefly. Now, when you take a closer look at the rims of these ellipse patterns, you notice that there is one periodicity which is going this way here, and with a range of the period, spatial period is around 800 to 900 nanometers. This is something we call low spatial frequency ellipse, or in short, LSFM. Now, not only that, close to the rims of these ellipse patterns, we kind of observe appearance of new periodicity, but perpendicular to this original one, with a much smaller spatial period. And this periodicity is called in literature as high spatial frequency ellipse. Okay, and the period is of the order of 200 to 300 nanometer range. Now, this has attracted our attention in a way that we wanted to compare performance of the close to microscale periodic surface structuring versus close to nanoscale periodic surface structuring for their performance as a substrate. Okay. For that, here I show you what we use in our experiments. First, we laser structure the surface. Here you see a full solar wafer, 15.6 by 15.6 centimeters. The total surface here has been structured by laser at the low spatial frequency. And we have also structured a 3 millimeter by 3 millimeter area on another polished silicon wafer with high spatial frequency ellipse. Okay, and we then later coated both of these surfaces with around 40, 50, 60 nanometers of silver to make a active surface enhancing Raman substrate. Okay, and that was the idea, and we wanted to test if this sort of periodic but also nanostructured surfaces would be good enough high-performing substrates for SARS. Okay, and here is a closer view of the low spatial frequency version. Here is the overview. Now, this is what a high spatial frequency ellipse parent surface looks like under SEM. And please note that the scale bar is 2 micron in both of them. And the lower one is the low spatial frequency regime. And we have around 250 nanometer period here in one, and about 800 to 900 nanometer period in the other one. Okay. Next, we coat them with silver, and then we deposit our analytes on the surface to check their surface enhancement qualities. Okay. Here in this figure on the right, I show you the enhancement factor range in logarithmic scale. So now what you see here are silver coating thicknesses, and for always with the first panel shows a high spatial frequency and second panel shows low spatial frequency surfaces with 40, 50, 70 nanometer silver thicknesses, 40, 50, 70, and 90. Just to see that there's a drop, we also coated with 90. And we have figured that for low spatial frequency surface, no matter which Raman excitation wavelength we use, there's an optimal coating thickness of around 70 nanometers. Okay, so 70 nanometers thick silver coating on this sort of LSFL surfaces turn out to have the best performing substrate, and the enhancement factors ranged around 10 to power 9, 10 to power, it's slightly above 10 to power 9. Okay, where HSFL structures have shown a similar trend, but they saturated more, close to 50 nanometers. Well, maybe even 70, you can call it again around 70. And now the thing is their performance have been slightly better than the LSFL version. So the high spatial frequency nano-textured surfaces had a slightly better performance in the Raman enhancement, at least at the excitation wavelengths that we have tested. Okay, these are the most common Raman excitation bands, and we have those in the lab. Here are the actual spectra. These are Raman spectra recorded for different concentrations of the analyte molecules. Here we show concentration range of 10 to minus 6 to 10 to minus 9. So down to 10 to minus 9, you can still see some or differentiate between the Raman peaks. With HSFL, it turns out that you can do a little further. So I regrouped so that the graph was not so crowded. So starting from 10 to minus 5 down to 10 to minus 9. Here we have 10 to minus 9 again. 10 to minus 10 and 11 are also discernible. So HSFL structures turn out to have slightly better limit of detection. And here are the calibration curves that I mentioned before. For 70 nanometer silver coated LSFL or 50 nanometer silver coated HSFL structures, we see that limit of detection lies of the order of 10 to minus 10 to 10 to minus 11. So around 10 picomolar for HSFL and 100 picomolar for the LSFL molecule, LSFL structures. And not only that, we have checked also the uniformity of the substrate. This is a micro-Raman view graph acquired from both of the substrates, HSFL and LSFL. And the relative standard deviations were found to lie in very close vicinity of about 27 and 24% respectively. Okay, which is not that great, it's but still acceptable for a such substrate. We have also performed simulations on the field enhancement. So we ran our simulations for 3 different wavelengths that we have used for both HSFL and LSFL structures. Well, these shapes were directly transferred from the SEM images of our substrates. So we did not model the surfaces by approximating them with analytical, well-known geometries. But we have, rather than doing that, we have replicated the SEM images, directly transferred the shapes, and ran our simulations on the shapes that directly represent the SEM images. And we see that and this is a logarithmic scale plotted Raman enhancement factors. You see, in some cases, even we see the expected Raman enhancement factor may reach of the order of 10 to 14 in some of the locations and tips of these structures. So in experiment, we don't observe as such. However, experiment, of course, gives an ensemble average number, not a particular maximum at a certain location. So as an average enhancement factor of 10 to the 12 or so is quite acceptable from our understanding. So this is also a continuation of that work. So we also tested polarization dependence of the performance of these substrates on Raman enhancement. And we have observed that actually LSFL structures have stronger dependence on the excitation wavelength, but not too much on the polarization. If you check the x-axis, it goes between 0 to 90 degrees. And the changes in the expected enhancement factor is not larger than 1 order of magnitude for every wavelength. However, there are about 2 orders of magnitude differences between different wavelengths. Okay. Now, on the contrary, for HSFL, it turns out that the differences in the enhancement factor for different wavelengths are not that great. They lie about of the order of 1, but the response to polarization can extend 2 orders of magnitude. So HSFL structures turn out to be slightly more susceptible to polarization dependence, and LSFL turns out to be slightly more susceptible to wavelength dependence. Okay. With this, I'd like to conclude in short. So we have demonstrated here a novel direct writing, laser-based direct writing method to fabricate SERS substrates. And we studied 2 different regimes, HSFL and LSFL on silicon. And it was found that both of these structures work very well as SERS substrates. And the maximum experimental enhancement factors were obtained for around 50 nanometer of gold, silver deposited on HSFL and 70 for LSFL. And the enhancement factors were very close, 1.5 times 10 to 9 and 1.3 times 10 to 9 in both cases. And we acquired this with using 660 nanometer Raman excitation wavelength, which is consistent with the simulations. And limits of detection for the CV molecule, crystal violet molecule, is demonstrated to be as low as 10 picomolar for HSFL and 100 picomolar for LSFL structures for 532 nanometer Raman excitation wavelength. And the uniformities of these SERS substrates turned out to lie around relative standard deviation turned out to lie around 27 and 24% for HSFL and LSFL, about over a 15 micrometer by 15 micrometer area respectively. So with these, I would come to the end of my talk, and I should mention that this work was essentially in the thesis work of Serena and Fırat, and Özge helped a lot with the Raman, and Kemal did all the simulations. Aryan and Ihor helped with the surface structuring of the samples, and I thank my grants and Ahmet Oral for allowing us to use his equipment for Raman scattering. And as one last slide, I would like to use this opportunity to make an announcement that we're going to hold the traditional nano-TR conference series, the 16th of it, this year in Ankara between 5 and 8 September in METU Convention Center. You're all welcome to submit your abstracts. The deadline is 17th of June, and visit us at nanotr.org. It's going to be held face-to-face in person. Okay, hope to see you there. Thank you.
For your presentation. If there is any questions, I can take only one, and all other questions can be asked and written from the chat section of this talk.
Thank you very much. I have a question, Professor.
Yes,
what are the importance of controlling the periodicity of surface morphology in application point of view?
Of course, well, in the SERS applications, we didn't know, we wanted to explore. So this was why we did this work actually. But they can be also used as light management interfaces for, in photonic devices such as solar cells or photodiodes. And it turns out that the periodicity plays a role in the diffractive efficiency of the or targeted wavelength range of the diffracted field into the device. And certain periodicities could be more efficient for certain wavelengths and so on and so forth. But that's not the end of the story. Of course, the peak to valley height is also an important factor in diffractive efficiency that has to be tuned as well.
So which parameters you use in experiment, for example, temperature, I guess, to control, you use for, in the experiment?
How do we switch from LSFL to HSFL?
Yeah.
Okay, well, average power, repetition rate, And we have two complete different laser systems for HSFL and LSFL structures, but differences in the wavelength doesn't matter too much. The pulse lengths are around several hundred femto for both of the cases, but I think it's more important to be careful with the average, or let's say pulse energy in general. So by switching from the one pulse energy to the other, you can switch from LSFL to HSFL.
How about the theory? You talked about the ensemble average and also single particle in theory. Do we have any theory to support the ensemble average of this experimental work?
Well, these Raman maps, micro Raman maps, were made for that purpose, and we have observed about 25% variation from one focal spot to the other, but even the micro Raman setup is a focal spot size of around a micron, and within a micron focal spot there might be more than 100 contributing hotspots. So that's not an easy to answer question. Simulations are done for exactly that, answering that questions. And our simulations suggest that what we observe is in the experiment, it really represents a kind of average, not the peak values that we get from simulation. That's probably because not every hotspot has a molecule lying next to it.
Okay, thank you very much.
You're welcome.
Thanks again. And also from the previous question, I have to adapt something. Do you have an ability to modify the beam shape of your lasers, or you just switch one laser to the another one?
Mm-hmm. We haven't checked that, but we have in plan, I should say. So far, they were always Gaussian profiles.
Okay, thanks a lot once again to our speaker. Let's move on to the next speaker. So there's a change in the next talk. The next talk will be given by Berkcan Erenler. Please, Berkcan, Mr. Berkcan, start your talk.
Berkcan, please open your voice.
So we cannot see your desktop or your presentation, Mr. Berkcan. Once again, your microphone is also closed. Let us check. Mr. Berkcan, it seems that your microphone is not connected to your computer or your system. Mr. Ayvazyan, are you with us? We can maybe move on to the next speaker, and then we can go back and continue with Mr. Berkcan Erenler. Mr. Aybazyan, are you with us? Okay, we have changed the parts of speakers. Mr. Kazım Canyurt, are you with us here? If the Kazım Canyurt is here with us, we can move on to his talk.
Yeah, I am here.
Okay, if you're ready, we can continue with your talk. I think the other participants are having problems with the connection and the speakers as well.
Yeah.
Mr. Canyurt, if you're ready, you can share your presentation or your screen.
Okay, I'm ready.
We can continue with you. Thanks a lot.
Can you see me?
Yes, you're visible, but we cannot see your desktop or your presentation.
Okay.
Okay, your presentation also visible.
Yeah.
Take the microphone, thank you.
Thanks to organizer committee. First of all, I would like to mention that all electronic devices have PCBs. All digital control systems have PCB. I want to tell you about our project, 3D PCB design and prototype production. What is PCB? Printed circuit boards are the boards that are used as the base in most electronics. Every electronic machine have PCB, both as the physical support piece and as the wiring area for the surface mounted and socketed components. PCBs are most commonly made out of fiberglass, composite, epoxy, or another composite material. A single layer or single site PCB is one that is made out of a single layer of base material of surprise. If you want to...
Mr. Canyurt, I think you're touching your microphone. Loud voice is coming to the from your microphone.
Microphone? Okay. Now.
Thanks a lot. It's clear now.
Clear. Okay. Most PCBs for simple electronics are simple and composite of only one layer. More sophisticated hardware such as computer graphic cards or motherboards can have multiple layers, sometimes up to 12. One single layer PCBs, very simple. If you make a new one, it's very simple. 4 steps, you can do it at home. One minute. Although PCBs are most often associated with computers, they can be found in many other electronic devices, such as TVs, radios, digital cameras, and cell phones. In addition to their use in consumer electronics and computers, different types of PCB are used in a variety of other files, including but 2D design. Where is PCB used? Medical devices, industrial machinery, lighting, automotive and aerospace industry, communication devices, all computer system, mobile phone, all digital system. PCB history. The first patent of the printed circuit board, which means creating an electric band on the insulated surface and combining circuit elements, was received in England in 1903 by the German inventor Albert Hansen. How to make a new design 3D PCB prototype?
Interrupted.
We derive the circuit design suitable for the surface type and depth. Cover the wall surface with copper. Abrade to unnecessary copper area with laser. This laser, 3D laser machine. After determining the location of the circuit elements, we paint the remaining area to isolate. We paint this area for isolate. As a result, we get a surface curved PCB 3D. This photo, an Apple AirPods you see in the photo, it consists of many flexible cable and bands. It's very technological. It's a very important design with flexible cable and other capacitor, CPU, all components. I want to bring into a more technological form and a new design. This wireless handphone. Let's redesign together now. On the 3D Max, we derive it. No. This drive handphone cup into the cup. We plate the copper first. Now it with laser machine, so that only transmission parts remain. Now, finally, let's lay out the circuits. This one not cable. This CPU and waves, sensor waves, some sensor, speakers, battery, voltage, and a lot of components, ways. As a result, the advantages of this prototype are as follows. Take up least space. This one very large, very least space. And enabling more technology, more sensor, more equipment, more CPU, more technology. Using the installating surface getting PCB cards, making the PCB resistant to vibrate and breakage, get rid of unnecessary cable clutter, obtaining a higher quality signal than the cable with carrying the transmission over the surface. It is suitable for every design because it doesn't need a planar place. Thank you for taking the time to listen.
Thank you very much, Mr. Cankut, for your talk. If there's any questions, we can take questions now. So if there's not a question, we'll have a short break because of the technical problems. We have 10 minutes break now. Thank you.
Yeah. Thank you.
Welcome again to today's third session. Now we're continuing with the Berkcan Bey. You can check the sound and the.
Can you hear me? Can you hear me?
Yes, we can. Thanks again, Mr. Erenler. You can start your talk. And if you share your presentation, you can check also your visuals.
Okay.
Yes, it is seen. Thank you. Microphone is yours. Thanks again.
Thank you. Hi everyone. Today we talk about grow and laser properties of thulium doped potassium yttrium double tungstate crystals. The growth of double tungstate single crystals by the modified Chokaski method is the complex physiochemical process in which heat and mass transfer play an extremely important, often decisive role. When growing single crystals, it is necessary to observe strictly specified thermal conditions. It is necessary to maintain constant temperature gradients at the growth front and high thermal stability of the process at a level several tens of degrees. In addition, it is necessary to create concentration gradient that ensures the diffusion of salt substance in the direction of growth surface on the seed crystal. The concentration gradient is created using the temperature difference between the zone of superheated solution melt and the zone of crystallization. The crystal growth was carried out using dynamic growth mode and selection of the required temperature gradient at the crystallization front. These factors fully provide the necessary process of the crystal nutrition at various stages of the growth. Diode pump thulium lasers operating in the spectral region near 2 micrometers are attractive for applications in different areas. Surgery, since their radiation is strongly absorbed by water, range determining, and the environmental atmosphere monitoring due to presence of the absorption lines of number chemical compounds in the spectral region around 2 micrometers. The thulium-doped crystals attract attention due to relatively high absorption and emission cross-section, broad emission bands, and the possibility to grow highly activated crystals. Experimental method section. The laboratory model of the setup growing crystals by the modified Chokaski method was equipped with the shaft 2-zone furnace with the premeter. It should be noted that the optimal axial temperature gradient in the crucible, at which there is no bottom contamination during the synthesis relative to surface of the solution melt, should have following form table. To study temperature concentration parameters of synthesis single crystals by the modified Chokaski method, we used melt solution based on the solvent KW oxide. Crystal growth was carried out using dynamic growth mode and the selection of optimal temperature gradient at the crystallization front. These factors fully provide the necessary process of the crystal nutrition at various stages of growth. Crucibles with a diameter 80-100 mm were used. The temperature range of colloidation is a range of 900-980 degrees Celsius. The height of solution melt varied between 50-70 millimeters. The sealed element in the form cylinder 8 millimeters and 8-12 millimeters long is oriented along the 0-1-0 axis with an accuracy of 0.5. All components of the solution immediately before weighing are annealed at the temperature between 250 degrees Celsius for a 1.5 hours. The solution melt intent the crystallization was heated in the crucible temperature 1030 and 1040 at a rate of 100-200 degrees Celsius per hour, and it was homogenated for 12 hours. Stirring with platinum stirrer used to ensure the complete homogenization of the melt solution. Then instead of stirrer and crystal holder with a single crystal seed installed, the crystal seed slowly lowered until its lower part touched the surface of solution melt, which is 4-5 degrees Celsius higher than saturation temperature, which is in the temperature range of 900 to 980, 925 degrees Celsius. The experimental laser setup is presented in the figure. The near hemispherical laser cavity consists of curved output coupler, and the plain high reflector was used. The cavity length was about 24 millimeters. A laser crystal was thulium doped single crystal with the thickness 2.8 millimeters and anti-reflection coatings on its working sides. The temperature of active element was kept at 14 degrees Celsius by means of copper slab and the thermoelectrical cooling of the elements with a water-cooled heatsink. A continuous wave fiber coupled diode lasers was used for pumping of the active elements. A pump beam was focused in the 200 micrometer spot inside the laser crystal. To set and maintain the temperature of laser diode and achieve stabilization of the spectral position of the radiation band, a mounting and cooling unit for the laser diode was developed, which includes a copper base 4, a pellet element 6, a thermistor 5, a clamping bar 2. In order to improve the thermal contact between the copper base 4 and the laser diode 3, a carbon heat conducting film with a thickness not exceeding 100 micrometers is laid. The maximum output power of 645 milliwatt and 1914 nanometer was measured with an output couple transmission of 3%. A slope efficiency 55% with respect to absorbed power was obtained. Laser emission was linearly polarized along n-axis. Input-output diagrams for the CW thulium dopes lasers are shown in the figure. The Q-switch laser experiments were performed taking into account comparatively low light-induced damage result of the chrome-doped zinc selenide saturable absorbers. The saturable absorbers was inserted to a cavity between active medium and OC at brevity angle. Two saturable absorbers with the initial transmissions of the 95% and 90% were used. The laser pulse with the energy about 26 microjoule and repetition rate of 6 kilohertz corresponding to 126 milliwatt of average output power at the 1910 nanometers were obtained at the 2.2 watts of the incident power for the saturable absorbers with the initial transmission of 95% nanometer and OC with the transmission of the 6%. With the increase of incident pump power from the threshold to its maximum rate, the pulse energy and repetition rate and varied from 10 to 26 microjoule and 0.22 to 6 kilohertz respectively. To depends of the pulse duration and repetition rate on the incidence pump power shown in the figure. The increase of pulse energy with incident pump power can be explained by changing in the TM mode size due to thermal effects in the gain medium. The spatial profile output beam was TM mode with at maximal incident pump power inset in the figure. The shortest laser pulse duration was measured to be 14 nanoseconds. The oscilloscope traced of the single pulse with the duration 14 nanoseconds and output pulse train with maximum repetition rate of 6 kilohertz and are presented in the figures. It should be mentioned that maximum pulse repetition rate was limited by the laser-induced damage results of the saturable absorber. Conclusion.
high-quality single crystals were grown by modified Choklavsky method. The values of grown parameters notably affecting the crystal quality were determined and discussed, focusing in their impact and the crystallization front-end structural defects. A maximum CW output power of about 0.65 watt with a slope efficiency of 55 was obtained, and the wavelength 1914 nanometers. In a passively Q-switched regime of operation, laser pulse with the energy of 40 microjoule and duration of 10 nanoseconds were obtained, and the repetition rate of 2.8 kilohertz and at the incident pump power of 2.2 watts. Based on the obtained results, it can be concluded that the thulium-doped single crystals had promising active media for lasers emitting in the spectral range near 2 micrometers for the usage in surgery and range finding. Thank you, everyone.
Thank you for your talk, Mr. Ömer. Do you have any questions? We can take 1 or 2 questions now. So if there's not any question, we will conclude and close up this session for now, for today. We are thanking to our all speakers. The next session will start at 3 o'clock. Thank you.
So, how was Turkey?
So Turkey was... Wow. Yes.
the meeting point of the roads between Europe, Asia, and Africa, and a perfect interweave of cultures, Ankara, a culture paradise of 5,000 years. These lands, which hosted many Western and Eastern civilizations, became the center of the Turkish War of Liberation, launched with the downfall of the Ottoman Empire, and became the capital of the Republic of Turkey. You can find the opportunity of treading the path of history by visiting the year-round open museums and open-air museums in Ankara, which serve as a bridge between past and present, remaining intact, defying thousands of years. There are many historical and modern mosques in Ankara. The roof of Hacı Bayram Mosque was built in such a way as to embrace the wall of the Temple of Augustus, as if to prove the centuries-old coexistence of religions in fraternity. You should never depart from Ankara without seeing the traditional Ankara houses. Ankara is also one of the most important stops on the historical Silk Road. The inns, caravansarais, and traditional bazaars of that period provide a safe transport, easy access, and a wealth of purchasing opportunities. Historically important Turkish baths and spas are the health and tourism sources of Ankara. Ankara is also a university city, boasting 5 big state and 10 private universities. Ankara is also a city of art, life and entertainment. The state opera and ballet performances, the plays staged by the state and private theatres, the concerts by the Presidential Symphony Orchestra, as well as national and international festivals keep its people occupied for a whole year. Seymens, the swashbuckling heroes and traditional dancers from central Anatolia, may show up in all corners of Ankara. All institutions and organizations complying with Atatürk's motto, sound mind, sound body, have spearheaded the construction of many sport halls in Ankara. Ankara also draws attention with its parks and recreation areas. It is located at the heart of many of Turkey's tourism riches. Ankara is the easiest city in terms of transport. Ankara is also easily accessible by air, land and rail from any country in the world. The Turkish cuisine is one of the world's most famous cuisines. The Ankara specialties constitute the select examples of Turkey's culinary marvels. Ankara is the homeland of the Ankara goat, the source of clothes vying with silk for quality, the Ankara rabbit, whose wool is as light as Angora wool, the world-renowned Ankara cat, and the flower of love, also dubbed the flower of the prophet. Its shopkeepers, the carriers of a tradition of 1,000 years ago known as Ahilik, the Guild of Turkish Craftsmen, are sincere and hospitable. They are generous, alms givers, and like guests, with their tables open for everyone. They are, in short, humanists. Ankara, of which Atatürk voluntarily became a fellow townsman, is a monument of peace, with its cultural foundation and a center of tolerance. With its history and natural riches, eating culture and tourism, agriculture and animal husbandry, its politics, sports people, art, and its residents, is a leader capital breathing life into Turkey. A culture of paradise of 5,000 years. Ankara, the heart of Turkey.
So, how was Turkey?
So Turkey was... Wow. Yes.
Hello, everyone. Welcome to the fourth session of the ICLLT-2022. The first speaker is plenary speaker, Professor Halina Rubinstein Dunlop. Professor Rubinstein Dunlop, you are here, yeah?
Yes, I am. Can you hear me?
Yeah, but sound is a bit low. Could you please?
My sound is on the highest possible. I cannot make it any higher.
Okay, yeah, we can hear you now. No problem. Thank you. Before your talk, I will give brief information about your academic background.
Thank you.
Professor Helena Rubinstein Dunlop is with Australian Institute for Bioengineering and Nanotechnology. Professor's research interests are in the fields of atom optics, laser micromanipulation, nano-optics, quantum computing, and biophotonics. She has long-standing experience with lasers, linear and nonlinear high-resolution spectroscopy, laser macro manipulation, and atom cooling and trapping. She was one of the originators of the widely used laser-enhanced ionization spectroscopy technique and is well known for her recent work in laser micro manipulation. She has been also working in the field of nano and micro fabrication in order to produce the microstructures needed for optically driven micro machines and tips for the scanning force microscopy with optically trapped stylus. Recently, she led the team that observed dynamical tunneling in quantum chaotic system. Additionally, Professor Rubinstein Dunlop has led the new effort into development of new nanostructured quantum dots for quantum computing and other advanced device-related applications. The title of the talk, Structured Light in Nano and Micro System. Okay, you can start your presentation, Professor.
All right, so I can share my screen now?
Yeah.
All right. Right, so I just have to go to full screen. Yes. It doesn't want to work for some reason. Let's see whether it will work now.
Yeah, now.
No, but I'm on the wrong. I'm very far in the talk, so I have to go out again, I think. Yeah, I have to. I'm so sorry about that. We'll get to the beginning.
That's fine, that's okay.
Not really, but never mind, we can't help it. Here we go. All right. Okay. Thank you very much for this lovely introduction to who I am. So my name is Halina Rubinstein Dunlop, and as it was said, I'm from School of Mathematics and Physics and the ASI Center of Excellence for Engineered Quantum Systems at the University of Queensland in Brisbane, Australia. In Aboriginal and Torres Strait Islanders tradition, it is customary to acknowledge country as we pass through. Today, I acknowledge and pay respects to the First Peoples, the traditional custodians of the lands and waterways. We respectfully acknowledge the Turrbal and Jagera peoples and thank them for their continuous hospitality. We acknowledge and celebrate the continuation of a living culture that has a unique role in this region. We also acknowledge elders, past and present, as well as our emerging leaders of tomorrow, and thank them for their wisdom and guidance as we walk in their footsteps. So this is customary to acknowledge the country in Australia. Structured light in nano and microsystem is the title of my talk, and let us see what I want to tell you about. So you can see here that I'm playing with light to my liking. Can you see full screen? Sorry.
It is not totally full screen, but it's okay.
Okay.
No problem.
No. I can do it. I can do it. Here. That's full screen now, right?
Yeah. Now
Okay.
it's full screen. Okay, thank you.
Okay. So so I will be playing with light in many different ways. So you can see here, I'm writing optical micromanipulation group with many Gaussian beams that form this structure, and into each of the beams I trap particles and I keep them trapped in optical tweezers. Now you can also use light to introduce rotation and build micro machines, and you can use light to cool atoms and trap them into the fields that can resemble whatever you want. And I'll show you a few examples of that. So saying that, let us move. Okay, so today I want to tell you about how to structure light, what I mean by structured light, and what are the devices that will enable me to do it. And then I want to show you linear momentum of light and what can be done with it, how I can use it to trap objects in using linear momentum of light. And then I want to extend that area to going into transferring angular momentum of light, optical angular momentum of light, and see what I can do with that. And transferring angular momentum of light means, what I mean by that is that I can transfer spin angular momentum or orbital angular momentum. And then I want to show you some applications of that. Okay, and so here, this picture of Mona Lisa is actually a picture where Bose-Einstein condensate is formed to form this picture of Mona Lisa. So it is quite smooth picture, as you can see here. And if you wonder about the resolution of it and how finally we can do it, so the eye of Mona Lisa here, the pupil of the eye of Mona Lisa is about 1 micron in size. So we can play with light to our liking quite substantially and very beautifully. So how do we structure light? So I take an example here of a ring-shaped potential, and I can use different devices, a number of devices, to build this ring-shaped potential of light. So for example, I can use acousto-optic deflector or electro-optic deflector. And I can then produce bidirectional beam. And if I rapidly scan it, if I scan it very rapidly, that beam, then using few lenses and mirrors, etc., in the image plane, I will form a ring of light. And then I can put particles into it, or I can put atoms into it, or whatever. Another way of forming some shaped potentials, this time again a ring, is to use direct imaging of a digital micromirror device. So I will be using digital micromirror device. So digital micromirror device is really a set of tiny mirrors which can wiggle with certain angle, and I can program them in such a way that I can create a pattern that will be a ring-shaped pattern, and then put light onto it, and then I will form my ring-shaped potential. Another way of forming ring-shaped potential in this case can be also liquid crystal spatial light modulator. And so this is a device in which I also, by using the properties of liquid crystals, I can address it in such a way that I can shape intensity and phase of the light so that I can form whatever shape of light I want. And again, here we have formed the ring. Now, what I'm showing you here is that if we talk about shaping light or sculpting light or angular momentum of light, if we add all those areas together, the number of papers that has been published in this area is growing quite dramatically. You can see that the field sort of started to take off in 1997, and where there were about 1,000 or maybe a couple of thousand of papers per year. And then now we are at, in 2020, we had about 8,500 papers in this area. So it is because this happens because it is sculpted light is very versatile and it can be used in many, many areas of science and technology. And on the other hand, angular momentum of light is very interesting property that light has. And again, it can be used in quite substantial number of beautiful applications. And I will choose a couple to show you that. And my slides don't want to progress. Okay, so a little bit more of where those papers are. So majority of the papers are in optics, but you can see that there are a lot of papers in multidisciplinary physics, and that's where I sort of fit in. And in nanosciences, there are also a lot of papers. And applied physics in this area is very popular, as is material science. Okay, so what I really want to show you is I want to use structured light for optical micromanipulation and imaging. So there are many other areas that structured light is being used, but I will confine myself to only optical micromanipulation and imaging. So what I'm showing you in this transparency is really the variety of things that the structured light can be used as far as optical micromanipulation and imaging is concerned. So what you are seeing here is a picture of Einstein, which is, this is just the image of Einstein. And then we take that image, program it into the digital micromirror device and form an image of it in light. And then we place into this image Bose-Einstein condensate. So very, very cold atoms. So what you are seeing in this transparency here, in this picture here, is Bose-Einstein Einstein in Bose-Einstein condensate. All right, and we can also do the same thing with the pictures of Bose-Einstein. We can play other tricks and do different images. And all these fields can be formed in very versatile way. So obviously this was very versatile way how we could form the light and then put objects into it. Other examples of light that we can form using either spatial light modulators based on liquid crystals or digital micromirror devices are shown here. And what this picture is showing you here is when we are forming light using acousto-optic modulator. So basically I have light in the sheet here. You can see the sort of orangey thing is my sheet of light, and into that I then paint a certain shape. And this shape is basically a ring that I was showing you before. And again, you can use this digital micromirror device to use things, to make things like dumbbell formed in light, to which I can then trap cold atoms and then move them from one part of the dumbbell through the channel to the other part. And this is all possible. You can see it in action here, and it is all possible if we can trap and cool atoms to very low temperatures, and the system is shown here. Okay, so one of the examples that I want to talk about is how we can, the example that I showed you in previous transparency, namely I formed the light into this dumbbell, and then I want to build a superfluid circuit that is something like electronic circuit, but in this example, it is has all to do with atoms and not electrons, and so I will call it atomtronics. So what I do here is I form my light into the dumbbell, as you saw in the previous transparency, and then I collect my Bose-Einstein condensate in one of the dumbbells, and then open the channel, and the channel has certain length and certain width, and then I see what happens. And what we can observe is oscillation of the atoms from one container to the other container. And depending on how long the channel is and how wide it is, those oscillations will change. So this is basically showing that such a system can behave as atomtronic oscillator. And we have modeled it, and we've shown that it works very well, and the parameters can be varied very precisely, and we can characterize the system in very precise way and show that it really works as atomtronic oscillator. And we have been also able to model it using acoustic model. Another example from cold atoms is to look at giant vortex clusters in two-dimensional quantum fluids. So again, we have Bose-Einstein condensate. I put the light into this pancake here, and then what I do is that I disturb the pancake with two fields here, dragging them in one direction, or with many spots, and drag these fields through the pancake. And what we can see is that what will happen with time is that the vortices will form, and as we stir them more and more, giant vortices will form here. And this was very surprising result, but what it shows is that those giant vortices have been predicted by Onsager many years ago, for which he got Nobel Prize. And this is first experimental evidence of those giant vortices forming and of negative temperature states. Now, let us go back to the beams that we can form using light. So this is an example that we all know very well. So this is Gaussian beam, which is propagating, and I here depicted you 5 milliwatt TEM00 beam profile. So that looks like that. And then we can characterize it by using by looking at the amplitude or intensity of the beam, variations with the position. So that's something that we know very, very well. But if I take circularly polarized light, on top of the profile that we had before, which was Gaussian profile, I have the electric field vector that is describing a circle. And so I can now form this Gaussian beam in such a way that it not only is has this intensity profile, but it also carries a spin angular momentum of ±1. And the question is, how can we form the light to be circularly polarized, and then how can we use it? But that's another example. Oops, something happened here. Oops, I'm thrown out. Okay, that's not what we wanted. How do I get out of this? I think I have to stop sharing and fix what I'm doing.
Yes, I think so.
Okay, well, let me just go back to sharing. Sorry, share the screen. And we want to go to here and share. All right, so we are back. You have full screen, right? Okay, so this is what happens, that this Gaussian beam is now carrying plus or minus 1 h-bar of spin angular momentum. Okay, so people for a very long time were very interested in transfer of spin angular momentum to objects. Beth did an experiment in 1936 trying to show the transfer of spin angular momentum. That was macroscopic experiment. It was very difficult, and he sort of showed it, but not very clearly. And now by using highly focused laser light, which is can be circularly polarized, I can focus it very, very strongly and then put it on onto an object that is birefringent. And we know from our optics lessons that if I have circularly polarized light that is impinging on a birefringent object, we will have propagation in X and Y directions with different velocities. And so on the output of the light, we'll get light in those two directions with different phases. And if we look at what is happening in the transmitted light, we can see that in order to conserve the momentum, some orbital spin angular momentum must have been transferred to this birefringent crystal. And what will happen then is that this crystal will rotate. So we'll achieve optical torque. So what will happen is I'm taking calcium carbonate, I put it in water. It's a small crystal, few microns in size, and I trap it in 3 dimensions using polarized light. And if the light, so what will happen is that the light, the rotation, the crystal will rotate continuously or align itself to particular orientation. So either continuous rotation or alignment. So if I have linearly polarized light, so I don't have lambda over 4 plate here, what will happen is that the orientation is controllable. So if I change the direction of linearly polarized light, I can then rotate that crystal by doing that. Or if I have elliptical or circularly polarized light, I will achieve rotation with controllable frequency. Okay, so we can demonstrate that. And so here is calcium carbonate crystal. And here we are showing on the left, it's the alignment. So I'm changing the linear polarization vector. And you can see that the crystal is following it. And then I am making the light circularly polarized or elliptically polarized. And you can see that this crystal is rotating, not very fast, not very beautifully, but it's rotating. So that's what happens when you transfer spin angular momentum. And what happened here was that my light was coming from above onto the crystals, and the rotation was in the direction of the incoming field. Now, I can have axial or transverse momentum flux. So I can have a longitudinal angular momentum, and I can also transfer a spin angular momentum transversely to the direction of propagation. And that's what you see in these two pictures. So how do we do this? So what I'm after here is that I want to transfer spin angular momentum in 90 degrees angle to the incoming field. So this is the description of what happens to transverse part of the beam, and the resulting situation will be that now I can rotate the object not in the direction of the incoming beam, but in 90 degrees. So transferring transverse angular momentum. So here is the depiction of what we are doing. The functional definition here is that the angular momentum transfer with component orthogonal to mean beam propagation direction. That's what I call transverse direction. So I displace a displacement from the beam causes this, but that is unstable. But in the focus, rotation can be stable. So we can look how. So this is how the rotation takes place. So the beam, you can see the beam direction here, and the rotation is around this axis here. And so the way to do it is depicted here. So this is experimental setup that has been used for this type of experiment. So I am coming with the laser light here, and I have my crystal on the microscope slide with high numerical aperture objectives and condenser, and then I can also have an illumination, and so look at what with the camera what's happening with it, and I can also detect the changes in polarization state of the light, having detection system here. And if we do that, we can observe the one crystal rotating. You can see that it's not very fast rotation. However, it definitely is in the direction that I was describing to you. So we are now transferring transverse angular momentum. Now we can go further. And here are pictures of this transfer of the momentum. And you can see that it definitely is causing quite substantial rotation, and it is rotating in transverse direction. And you might ask, why is that of any importance for any applications? And if we talk about using optical tweezers and transfer of momentum in optical tweezers in biological systems, very often we are, well, that was something else that happened there. So now the crystal has aligned itself into the propagation direction. And here we are back with what we were doing before. Anyway, to go back to why it is interesting is because as I said, if we want to use this rotation stuff in biological systems, very often we are dealing with very flat biological systems, and therefore introducing rotation in the direction of the laser beam is not the best idea. We won't do what we really want to do. So therefore having opportunity of transferring transverse momentum is very interesting in biological systems. Right, so going further, we can also transfer orbital angular momentum. And the way to do it is to form the light to Gauss-Laguerre beams of light. So what are Gauss-Laguerre beams of light? So what I have shown you here are a couple of them. So Gauss-Laguerre beam of light of certain charge, when of certain charge L, and if this number P is 0, then we will have, if the charge is 0, we have Gaussian beam. And then if L goes up, we create a donut beam, but it's not just flat donut. But what we can observe here is that as the charge of the donut is going up, the dark intensity profile in the middle is getting larger and larger. So what will happen when L is not 0? I will have helical wavefronts, and I will have angular momentum eigenmodes, and I will be able, in the best of cases, to transfer L times h bar per photon of orbital angular momentum to an object. Now
sorry for interrupting, Professor Rubinstein-Dunlop. Could you please summarize your talk in a couple of minutes, please?
I'm sorry?
Could you summarize your talk in a couple of minutes because time is...
I thought I had 40 minutes.
It is, I think it is 30 minutes, Professor.
Oh, is it? Okay. Okay, so let me just go further. So, okay, if you, I will summarize it very quickly. I will just show you that you can transfer this orbital angular momentum to the particles, and this is one example, and I don't have time to show you much, but you can use it for looking at a lot of interesting biological and physical systems. And I will skip that, and I will just show you one more example of how we use all that in optical tweezers. And so here, what I'm showing you is that I can transfer orbital and spin angular momentum. And this is how it all works. So we can transfer the momentum and use it for...
Sorry, Professor Rubinstein, your time is, I think I am wrong, is you can talk for 50 minutes, not 30 minutes.
Okay.
It is my mistake. Sorry about that. Okay, you can continue. All right.
Okay, thank you. Oh, that sounds a little bit better. That was a little bit...
Sorry about that.
Ooh, wow, I thought I couldn't be that wrong, but anyway. All right, so let us go back to a little bit slow motion now, or slower motion now. Okay, so in any case, to summarize this transparency, what I'm showing you, that I can produce these types of beams using digital micromirror devices or spatial light modulators based on liquid crystals, and I can produce them to have very high charge. That L can be equal to 1000. What will happen then is that the ring of intensity will be very narrow, very bright, and the dark spot here will be very big. Now, here is the first demonstration of this transfer of orbital angular momentum that we did many years ago. And so here we have helical wavefront, and we're transferring this helical orbital angular momentum to an absorbing particle. And as you can see, the absorbing particle absorbs this orbital angular momentum beam and rotates in the same sense as this helical beam was constructed. And here, what you see is the work from David Greer's lab, where they have constructed orbital angular momentum beams. There are two. One is plus 60, this one, and this is minus 30. And so you can see that he traps the particles in each one of them. And because the signs are different, opposite, then the particles are rotating in opposite sense. So that's the question is how do we form those orbital angular momentum beams? So here is a cartoon of how they are formed, and they have, the most important part to remember is that they have helical phase fronts, and so it means that the pointing vector is no longer parallel to the beam axis. It follows the spiral trajectory. You can see the spiral trajectory. And so if it's L equals 0, I have a Gaussian beam. If L is minus 1, this is my beam, and plus 1, this is how the beam will look like. And so what I'm doing here, I'm looking at the annular intensity profile here. And if I interfere those beams with a plane wave, this is what I will get. So why am I showing you this? Is that if I want to measure orbital angular momentum, it's the way to do it. So assume that I don't know what the charge is, I interfere it with plane wave, and then I can analyze it. And the way to produce it, as I told you, we can use spatial light modulator, we can use digital micromirror devices, we can use acoustoptic modulators if we want. And so if I now have the light which is has orbital angular momentum, and I put it on an object, then that object will rotate. All right, and so there are heaps of applications of orbital angular momentum use in different areas. So I give you just few examples. This is very early work from 2001 from Anton Zeilinger's lab, where the orbital angular momentum states have been used to look at the entanglement of the orbital angular momentum states of photons. And so the entanglement was very high, and they were able to analyze in the way that I was showing you before what sort of states were final states, and they were able to establish the type of entanglement they had. I will skip this one. And another idea of using this time circularly polarized light is rotating nanocrystals in spin angular momentum light. And what you could see here is the work from Mikael Schell's group in Sweden, where they are looking at Brownian fluctuations of an optically rotated nanocrystal. And they can analyze them, they can see the rotational frequency, and they can see all the geometry of the stuff. Another example is from Kishen Dolakia's group. So what he does, he is using levitated birefringent microspheres, the same that I will be showing you later in other experiments, but this time it is done under low pressure. So he shows, his lab has shown that you can have coherent oscillations of a levitated birefringent crystal, and it can be driven by non-conservative rotational translational coupling. And so you can see the evidence of the coupling here, and they can achieve incredibly high rotational speeds here. Now, what is optical tweezers? I want to show you a few examples of tweezers, so I better tell you what I'm talking about. So I have highly focused laser light is coming from below here, and it is highly focused, and in this particular example, linearly polarized, and you can see this field vectors here. You can see the intensity profile around it, and you can see that the most intense part of the beam will be where the gradient force is the greatest and where the particle will be trapped. And what is simulated here in this figure is that I have a particle going into the optical trap, and as you can see, when the particle is trapped, the transmitted field is changing dramatically. And if I'm able to characterize the changes in this field, I can tell you from which side the particle came, what is the force acting on it, what is the size of the field, what is the size of the particle, etc., etc. So that's characterization of it. And what can we do using optical tweezers? We can do what I just showed you, take Gaussian beam and transfer linear momentum of light, but we can also transfer orbital angular momentum of light, the one that I showed you before, and you can see that if I take this orbital angular momentum beam where I'm transferring plus minus LH bar per photon, I can take two particles, glue them together, put them into this orbital angular momentum beam and rotate them. I can also transfer, as I told you before, spin angular momentum, and we talked about it, and you can see two examples here. So there is a calcite rotating, the calcite that we created in the lab and rotating in spin angular momentum beam. And here is a spherical birefringent particle, which is called vaterite. It's another type of calcium carbonate. And it rotates so well, it's so round that you hardly can see that it's rotating. So what is it all good for? Well, you can use the rotation for a lot of things, and one of them is to measure the viscosity of the liquid in which the particle is rotating. So I come with circularly polarized light. I have my lambda/4 plate. my birefringent crystal, and if it happens to be the thickness of lambda over 4 plate for this wavelength of light that I am impinging on it, I will get linearly polarized light. And if it's not precisely lambda over 4 plate and it's circularly polarized light, which is coming up here, I will get elliptically, I will get change in polarization, and we will get elliptically polarized light. So what is happening here? I have optical torque, which is acting on the on this particle, on this lambda over 4 plate, and this rotational torque is determined by changing the polarization from between incoming light to outgoing light, so delta sigma here, power of my laser that I use for this experiment, and then optical frequency of the light. But it's all happening in a medium. The medium has viscous drag. So viscous drag is dependent upon the viscosity of the liquid, particle size to, if it's spherical particle of the size, particle size to cube, and frequency of the rotation. So now these two should be equal to each other. So if I equalize them, then I can determine the viscosity of the liquid. So what it means here is that if I can measure the change in polarization, and I know the power of the incoming laser, and I can measure the optical, the frequency of rotation, and I know optical frequency of my laser, and I know the size of my particle, which can be sometimes difficult, then I can determine viscosity of the liquid. So we're doing this, and now I want to go further and it doesn't let me. Here we go. So here is the example of the experiment that was done that way. So here is the birefringent crystal called vaterite, and it's being rotated in a spin angular momentum beam. And we have been able to determine that the experimental and handbook values of viscosity agree within 3%. And then we can use it for measurement of wide variety of liquids, and we can also go further. We can go to measurement of viscoelasticity, elasticity of the liquid as well. And what I'm showing you here is another type, type of measurement where we are using the stuff that I was telling you about before, that if I come with linearly polarized light and change the polarization angle, the particle will align itself with the polarization angle, and I can in that way measure the angle and then determine the angle and then measure the viscoelasticity. What is it good for? So this is one of the experiments done using rotating crystals. So these are the vaterite crystals, which are rotating in opposite sense. They are in the medium where we have nerve fibers growing. And if we rotate these crystals in opposite sense, what was observed was that this nerve fiber was growing straight. But if one of the crystals was turned off and only one was rotating, then this nerve growth will follow different path, will follow the rotation. So it was possible to determine with what sort of shear stress was applied here and determine what sort of forces were involved in order to get these neurons and nerve fibers to grow in a particular controlled way. But you can also use it in other tricky experiments in biology. Namely, this is an experiment done by one of our students very recently. So what we are doing here is we are looking at the macropinocytosis. What it is that the cell, living cell, grows little ruffles. And if it has possibility of grabbing something into these ruffles, it will grab the stuff. So it can be protein and debris and our crystals and what have you. And then it will go into the cell and form this blob here, which is called macropinosome. And then with time, this macro, and you can see the process here. So here's the raffle, and then the particle goes in the raffle. You can see it here. And here you can see how those raffles are moving. And then what we want to do is to have those rotating particles in those macropinosomes, rotate them and see what happens dynamically when this macropinosome is now shrinking. And the shrinkage of it and the function of it. Why is it interesting? Because shrinkage of it and function of it differs between different types of cells and between different cells which carry certain diseases, like a cancer cell will have this process studied in, this process will look differently to cancer cells than it does to normal cells. Do we know it? No, we suspect that it is like that. Such measurements have never been done. So this is the first measurement ever. And I want to show you the result of it. So this is summary of what we have done. And I think that I can show you that here we are within macrophage cell. So it's a living cell, and the macropinosome has been formed here. And you can see enlargement here of a crystal that is being rotated within this macropinosome. And then I can do all my measurements that I want to do to determine with time changes in viscosity of that liquid. What else can we do with structured light? I can build rotors, diffractive optical elements, helices, and what have you. And here are examples of stuff that can be done. So here I use 2-photon photopolymerization process, which means I send infrared light to a polymer, and that's done in a pulsed system. So these are very short pulses of light that are carried, and I can build again structures to my liking. So this is very old structure from Kawata's group from many, many years ago. This is our Queensland, University of Queensland emblem, optical elements that we have built. Cell scaffolds can be done. This is our trap that we have made, and micro machines can be done that way. So I want to show you a few examples. I don't have time for that, but well, I will skip that as well. But the way to do it is that you send those ultra short laser pulses, you make them react with photopolymer, and then you scan it through the system, and then you build the structure you want to have. So you see here our optical micromanipulation group, and this is another structure here, or any other structure you want to build, you can build in this way. And you can see that those structures have a very high resolution profiles, and they're rather small. And so here I want to show you one example of what we can do with it. Okay, so what we have constructed here is an optical rotor. So I have my stalk here. I produce the stalk, and then I produce the rotor as well. Then I take 4 optical tweezers that you see here, and I thread the rotor onto the lollipop, and then I take orbital angular momentum beam and I rotate it. So here I'm threading the rotor onto the machine, and here I use orbital angular momentum beam to rotate it. So this is orbital angular momentum beam, which carries 20 LH bar per photon. And here is variety of other things that can be done. So this is the picture that I showed you before that came from this structure. So this is scanning electron micrograph of the structure. So it's pretty nice looking structure. And then you can produce other types of machines. So here are little 500 nanometers particles trapped in orbital angular momentum beam, creating a flow. And so the flow is being created, And so you can see that this particle will be dragged through the flow. And what we are doing here is using structured light for stretching red blood cells. So this is not orbital or spin angular momentum. This is linearly polarized light. And I am basically trapping one side of the cell and then dragging and keeping it stable, and then take another type, another optical tweezers and stretch the other side of it. What is it good for? I think I will save it to a next talk that you will be able to listen to some other time. And another example of what we can do is we can look at biological swimmers by using structured light. And so it's last example that I'm showing you here. So here we have E. coli bacteria, and I can use a structured light to look at how this bacteria behaves. And so in this particular slide, you are seeing that this bacteria has a little bit, normally if you trap something and it's not wiggling and swimming and exerting its own forces, you normally will have one Gaussian profile here of as a function of force applied. But here it's a double whammy here, and what it shows us that I have frequencies of body roll and frequencies of flagella here, so I can look at those rotations and analyze it better. But I can also use different types of beams to trap those bacteria in different configurations. So what you were seeing in the previous transparency is when I trap them in Gaussian beam, but I can also trap them in annular beams. So again, I use my spatial light modulator to construct annular beam. And depending how this annular beam looks like, I can rotate a motile particle with optical tweezers, but now when they are lying down. And here is the simulation of it. And here is the real-time stuff. So here's the beam, and I hope that you can see it. It's now being rotated in this annular beam. And this is of interest because under normal circumstances, E. coli is often going through very narrow channels. So it's never would be standing in the beam, but it will be in this geometry. More stuff will happen than in this geometry. So I showed you that that can be done. Okay. And so this is the last bit, or maybe I will skip that. And with that, I just would like to acknowledge all the people who have done all the work on this system. So this is my optical micromanipulation group. Some of the people are now in other labs. So Anatoly Kashchuk is in Italy now, and Isaac is in Switzerland, and Daryl runs his own group at the University of Irvine. And my atom optics group, these are the people with whom I work at the moment. So thank you for your attention, and that's it.
Thank you very much, Professor Rubinstein Dunlop. Sorry again for the interruption while you were...
You scared me good.
Sorry about that. Okay, again, thank you so much for the impressive talk. We can take some questions from our participants. You can use chat section if you like to ask your questions.
Okay. Well, they are only telling me that they thank me for my presentation.
Okay, I have one
Please
question.
ask me. Yeah.
One question. You mentioned optical tweezers in your talk. I am wondering if they can be used in medical applications.
Yes.
For example, for separating malignant cells from healthy ones.
Yes. Yes. So so they can be used for sorting. Normally, it is done in such a way that the investigator knows what type of cell is what she wants to separate from other cells by looking at the shape of the cell, and therefore they can trap the cell and then move it through quite long distances to another container, and in that way separate different parts. That has been done several times. Another thing that can be done with cells is that, trapping force depends on the size of the particles. So if the cells that I want to separate are very different sizes, I can design my tweezers in such a way that they will trap one of them, but not the other.
Okay, thank you so much. Okay, thank you again for your
Can I ask a question?
presentation.
Sure, go ahead.
Yeah. Thank you very much, Professor Halina, for your great presentation. There are some questions comes to us from the students here. They ask about the force order made by optical tweezer by using structured light. And they also ask about how the measurement of the force metry, the order, how we can change the order. We know it's the order of force is piconewton. Yeah? Yes. How we can estimate and talk, why in papers and in research people don't talk about the Newton unit, piconewton unit. They just also talk a comparative studies in angular momentum unit. Yeah.
Well, so you are absolutely right that in optical tweezers, the forces are of the order of piconewtons. Now, there has been work done, I'm sorry I didn't present it today, but there has been work done at our university where we are showing that by using structured light, we can at least change the applied force, enlarge the measured force 30 times. That's not huge, but it's at least a little bit bigger. So what it means is that would enable you to trap a little bit larger particles. If you are asking how I measure the force, is that what you were asking?
Yeah, how you measure the force.
Okay, so the force can be measured by looking at the spectral density profile of the particle. So what you do, you are analyzing Brownian motion. So you trap the particle with certain laser power. And then, if it is not terribly strong, then the particle will wiggle a little bit with Brownian motion in the trap.
Yeah.
Okay. And when it wiggles in the trap, I can measure that wiggle. I can follow, how these trajectories are varying with time. And then I can plot it as a spectral density, and I can see the role of frequency of the trap, and which will then be proportional to the force.
Yes, thank you.
That's one method. It's one method.
I would like to Professor Bülent Çakmak apologize to Professor Halina for the time. It's the late time in Australia. Just now, this was our mistake to in plan.
No, that's all right. That's all right. That was just counting on opposite direction to where I am.
Okay, thank you so much for your
Thank you so much.
Okay.
Thank you.
Right. Thank you.
Thank you.
Okay, now our next speaker is Navid Farazi.
Yes.
You are here? Okay.
Yes, I'm ready.
All right. From Research Institute for Applied Physics and Astronomy, University of Tabriz, Iran. The title of the talk, The Effect of Temperature on Refractive Indices in Too High Birefringence Liquid Crystals Using the Wedge Cell Technique. Okay,
Yes.
you can start. Yeah, can start your presentation.
Okay. In the name of God, the compassionate, the merciful. My article subject is the effect of temperature on refractive indices in too high birefringence liquid crystal using the wedge cell technique. I am Navid Farezi from Tabriz University, Department of Physics and Research Institute for Applied Physics and Astronomy. My co-workers are Dr. Habib Khoshsima from Department of Physics and Research Institute for Applied Physics and Astronomy, and Dr. Mohammad Sadek Zakir Hamidi from Department of Physics of University of Tabriz, Dr. Amid Ranjkesh from Condensed Matter Department of J. Stefan Institute from Slovenia, and Professor Tai Hong Yun from Department of Electronic Engineering, Pusan National University, Republic of Korea. In this work, we study the variation of refractive indices with temperature for two liquid crystal, high birefringence liquid crystals, 1734A and 1791. In this study, we measurement experimentally and theoretically the refractive indices for these two liquid crystals. The experimental method, we use thin prism technique, and our source is a helium neon laser with 632.8 nanometer wavelengths. And the theoretically method for this measurement is 4-parameter model used from Brooks equation, and at the end we compare these two data, and we show that these two data is in a good agreement with together. For this work, we use from liquid crystals. We know that liquid crystals are matters between solids and liquids. These materials poses some mechanical properties of liquids, and at the same time they show anisotropy like crystals, and these materials measure applications or displays. We show this application in our laptops or smartphones and smart watches. Due to anisotropy of liquid crystals, these materials show two refractive indices, extraordinary and ordinary refractive indices. These two refractive indices difference is delta n, and delta n is named by refringence of liquid crystals, and the birefringence of liquid crystals is an important feature of for understanding the behavior of liquid crystals, and one of the important feature of this view is the molecular constituents and the wavelengths, operating wavelengths and temperature are different from any temperatures, and in the experimental section, we use two liquid crystal, 1734A and 1791, with a large birefringency and a large clearing temperature. We use prism cells for this experimental work with 1 to 2 degree, and this prism coated with 1% PVA, and the liquid crystal produced into this prism. And for the source, we use a laser, helium neon laser with 632.8 nanometer. And for the control of the temperature, we use a temperature controller that we in the setup schematic I can show here. We have a helium neon laser for source, and the collimator for the collimate the laser, our laser and our source. Then the beam go incident in a prism, and due to anisotropy of liquid crystals, the beam split in 2 rays, and the screen has a 5 meter distance from the prism, and we can calculate the refractive indices NAE and NO from this experimental setup from some equations. Wedge cell method have some advantages and some disadvantages. The advantage is that its way is very easy to determine ordinary and extraordinary refractive indices of liquid crystals as a function of wavelengths and temperature based on simple geometrical measurements. In this method, we no need to use polarized or coherent beam, and a small amount of liquid crystal material is required for this experimental work, and measurement can be performed for highly birefringent liquid crystal. Unlimited number of light sources can be applied, and those wide spectral range can be considered for this method. This method is some advantage, such as that in this method we need a big experimental setup for process measurement of wedge angle, and for spatial separation of ordinary and extraordinary rays. And another disadvantage is that new wedge cell are required for each monochromatic laser source applied independently in the measurement. For theory of this work, we use the Fuchs model. The Fuchs model used to describe the wavelengths and temperature of liquid crystals, and we can describe the average refractive indices for liquid crystals from equation number 1. Their average refractive indices and the temperature has a linear relationship between each other, and we can write from this equation the equation number 2 for this relation. For describe the order parameter of the liquid crystals, we use Haller approximation, and this equation is show the Haller approximation. At the end, the fourth equation show us the relation between refractive indices and temperature in the liquid crystals. From these equations we use, and we describe the 4-parameter model. The 4-parameter model is describe the relation between extraordinary ray and ordinary ray or refractive indices with temperature. And from these two equations, we have four parameters: A, B, delta, N0, and beta. For in our work, in our experimental work, we calculate these four parameters for two liquid crystals. The four parameter model has four unknowns: A, B, delta N0, and beta. To obtain the values of these parameters, the iterative fitting was done in two steps. Once the refractive index are measured by refringence, and average refractive index can be calculated. In the first step, the two fitting, we used equation number two to fit the average refractive index data at different temperatures, and obtain the parameters A and B. In the second step, we use equation 4 to fit the birefringence data, and the parameter delta N0 and beta are obtained at different temperatures. Once these two sets of parameters are obtained, the value are used in the equations 5 and 6 to calculate the refractive indices NO and NE. For these two liquid crystal, we calculate experimentally and theoretically refractive indices for 1734A and 1791. The solid line and the dots is for experimentally and theoretically, and we show that they are in good agreement with each other, and we fitted these values from equation 5 and equation 6. At the second step, we calculate the birefringence of the liquid crystals. The birefringence of liquid crystals, as shown in these two figures for 1834A and 1871, and we fitted these values from equation 4, and we see again the good agreement between these two data experimentally and theoretically. And at the end, in the conclusion section, we study the optical properties of these two liquid crystals, these two high birefringence liquid crystals. We show that the refractive index for extraordinary ray decrease with the increases of temperature, and the refractive index for the refractive index for ordinary ray are found to be increased with temperature. The birefringence in exhibit by the compounds was observed to be higher at lower temperatures, and somewhat diminished as the temperatures the temperature increase. For theoretically, we use the modified four parameter model from Wook's equation, and we show the excellent agreement between the experimental data and fitted values. At the end, the modified four parameter model is found to be fit very well with all the different pure liquid samples we studied. It can be assumed to be an accurate model to study the effect of the temperature on the refractive indices of liquid crystal materials. And at the end, I thank you for your attention, and if any question, I can ask for you.
Okay, thank you so much, Parisa Suleimani. Any question from audience?
I'm sorry, I'm Navid Farezi.
Okay.
Yes.
Navid Farazi, your name is Sino. Okay.
Yes, yes,
All
yes.
right.
It's
Okay.
another
Thank you.
laptop. I
Thank you,
cannot.
Navid Farazi, for your talk. Is there any question from audience, from our participants? Okay, I think no question. Thank you so much again, Navid Farazi.
Thank you, thank you.
Okay, thank you. Our next speaker is Nader Safarinia. Are you here?
Yeah, can you hear me?
Yeah, okay, okay. From Department of Physics, Institute for Advanced Studies in Basic Sciences from Iran. The title of your talk is Studying the Effects of Indistinguishable Photonic Gases on Dynamics of Multimodal Quantum Optomechanical Systems. Okay.
That's right.
Yeah, all right, we can continue.
Sure, let me share my screen. Can you hear me fine?
Yeah,
is it okay?
We can
That's
hear
great.
you.
Well, thank you for the introduction. First of all, I have to thank all of you for giving me this chance to talk about my work. And here it is. My name is Nader Safari, and under the supervision of Dr. Shahpur Saedian and Dr. Ali Asadian, I'm gonna talk about studying the effects of indistinguishable photonic gases on dynamics of multimodal quantum optomechanical systems. So because the time is short, so I will just dive right into the main part. I organize my talk into two parts. The first part, I'm gonna talk about the Hom effect, the Hong or Mandel effect shortly, because I'm sure you all know better than I do what this effect is. And after that, I will talk about my system in a nutshell. Actually, we are going to see the applications of Hom effect in this system. Then I will just dive into the main part. I will talk about the correlation matrix method, a new method that I developed to describe the dynamics of this system. And after that, by turning into an open system, by putting this system in contraction with other with maps, we're gonna see the effect of this this phenomena on dynamics of the system. So let's start by describing the Hom effect. I'm gonna just use this picture from Wikipedia to describe the Hom effect shortly. Imagine that we have a 50-50 beam splitter from two input ports. We are shooting photons into this beam splitter. From port A, we are shooting horizontal photon, and from port B, vertical photon into the beam splitter. And these four different cases might happen, right? Both of them might bunch on one side of the cavity. They might both refract, or they might both reflect, or bunch on the other side of the cavity. But there's one rule here. Whenever we are talking about reflection, we have to add a phase shift of pi/2 to the equations, to the state, or a coefficient I. So in the first case, when we are talking about distinguishable photons, when two photons from two ports are completely identical except for the polarization, one of them is horizontal, the other one is vertical. When it is passing the beam splitter, these four cases might happen as I just described. They both might bunch in port C, or they might both refract or reflect or bunch on in port D. But as you can see, we have a coefficient I here because we have one reflection, and we have a minus sign here because there are two reflections, I squared, and this is a minus sign. But when we turn into the indistinguishable photons, when we replace this V over here by H, for example, these two cases would get completely identical. They are completely the same, and there's a minus sign here, so they both cancel out. And this is what we will see in the output ports. There would happen, there's a bosonic bunching in port C or port D with equal probability 1/2, 1/2, right? This is the Hom effect. But as I said, we are going to see the effects, the influence of Hom effect in our system. Imagine that this is the system. We have a cavity. In the middle of the cavity, we have a movable membrane, which is acting just like a beam splitter. And we have photonic gases on either side of this cavity, right? First of all, let me talk about these symbols here. Because we have two parts, two cavity parts, I associate A and A dagger to the ladder operators of the left side of the cavity, B and B dagger to the ladder operators of the right side of the cavity. And also because we might have horizontal or vertical photons on either side. So there are AH dagger, AH, AAV dagger, AAV on the left side, and also BH dagger, BH, and BAV dagger, BAV on the right side. So as you better know, we are going to model this whole system with a bunch of harmonic oscillators and with different modes. That's why we call this system a multimodal quantum optomechanical system. So the Hamiltonian of this system consists of two different major parts. One of them is the interactive part, and the other one is the non-interactive part. And this is the interactive part, H of BS and H of I. H of the beam splitter, Hamiltonian of the beam splitter, describes a situation when a photon is annihilated, is destroyed on one side of the cavity and is created on the other side of the cavity. For example, here, B dagger A, or is created on the other side, is destroyed on the other. And this lambda, of course, here is the coupling strength. Here is the H of the interaction between the photonic mode and the phononic mode. By phononic mode, I mean this beam splitter over here. And this XM is the place of the center of mass of this beam splitter. And also we have two non-interactive parts, Hamiltonian of the cavity, where we model two parts of the cavity with simple harmonic oscillators, and Hamiltonian of the membrane, where we model this membrane with a simple harmonic oscillator. But as you better know, these non-interactive parts have little influence on the system. They are going to just boost the energy of this system. They don't have any physical contribution. So we are going to ignore this part. And also we are going to ignore the Hamiltonian of the interaction because it has a cubic form. I don't want to get into the detail of that, but it's gonna introduce a nonlinearity into this dynamic. So we are going to get this G very small to compare with this lambda coupling strength between two parts of the cavity. And as a result, we are only dealing with one term in Hamiltonian. Here, this is the second order correlation function G2, and it is kind of a measure for occurring the Hom effect. As you can see, this is the cross correlation of a number operators of photons on both sides of the cavity. And of course, this is the normalization factor. So by using G2, we are going to explore in what situation and what instances this Hom effect would occur in this system. But there are some points I have to mention for quick. First of all, this membrane, of course, moves. And in some instances, when it is right in the middle side of the cavity, at that time, it is just like the Hom effect. But other times, because there would be an antisymmetry between two parts of the cavity, the Hom effect doesn't occur. So this system is not just like the Hom effect setup. So I'm going to introduce a correlation matrix approach here. Imagine that we have a matrix C consisting of three different blocks. CHH is associated with a situation where we only have photonic gases on both sides of the cavity. CHV, when a situation where when we have horizontal and vertical photons on both sides of the cavity, and CVV, of course, describes a situation when we only have photons with vertical polarization on both sides of the cavity. Here's the shape of the form of these matrices. For example, CHV, of course, it is the expectation value of second order correlations of different quantities, different operators related to horizontal and vertical photons. As you can see, for example, here we have the expectation value of AH dagger, AV dagger, AH, AV, and all other permutations of these operators. For example, AH dagger, BAV dagger, AH, BAV, and all other things. CHH is associated with the expectation value of the correlation of ladder operators associated with only one polarization, only the horizontal polarization. For example, here we have H dagger, AH, AH, AH, H dagger, BH dagger, AH, BH. What is the whole idea? Here it is. Imagine that what we usually do is to find the dynamics of these operators. For example, find the dynamics of A or B using the Heisenberg equation in a closed system. And after that, we have to take the expectation value of that operator to reach, for example, a result, right? But the idea here is that, first of all, take the expectation value of these operators and look for the dynamics of these expectation values. Look for the dynamics of these scalars. And this is the power of this method. It's going to simplify our work. Here, by using the Heisenberg equation, we can simply find the time evolution of this C2. And it is associated with the commutation of another matrix W and C2. As I said, the elements of this method, this matrix are scalar elements. They are just integers. And of course, there are 10 by 10 matrix. This is a 10 by 10 matrix. So it is very much more simpler to find the dynamics of a simple 10 by 10 matrix consisting of scalar elements rather than finding the time evolution of a big matrix, right? This is the first plus point. The second plus point is that this matrix has all different permutations of ladder operators, second order correlation of ladder operators. So if we want to find C2, G2, for example, second order correlation function, or any other second order correlation, we simply need to find the time evolution of C2. And the time evolution of C2 gives us all the information about all different kinds of second order correlations. So, and there is another benefit to this method, and it is a physical intuition. I just called it the Schwinger model of angular momentum, as you better know. I'm going to talk about that later. But what is this W here? This W is also a 10 by 10 matrix consisting of 3 different blocks. W of the indistinguishable nature, W of the distinguishable nature, and also W of the indistinguishable nature. What are these? WD has this form. I'm not going to talk about that. It's not something very special, but just take a look at this W indistinguishable over here. As you better know, this is the form of SX, Pauli matrix X, when we are dealing with spin 1. So what is this giving us? What is this form telling us? It is telling us that when we have a horizontal photon on one side of the cavity, a vertical photon on the other side of the cavity, we can model this system as what Schwinger says. We can model the system with a particle with a spin 1. And what beam splitter does is just like a rotation of this particle with a spin 1 in a Bloch sphere. So this is a physical intuition. By using that method, we could derive all the results of the paper I was working on. I forgot to mention the name of that paper. I'm going to do it for quick. This is the paper, Enhanced Energy Transfer to an Optomechanical Piston from Indistinguishable Photons, published in the Physical Review Letters. And as I said, we can easily reproduce the plots associated with this phenomenon. This is the time evolution of G2 in a case where when we have single photon on both sides of the cavity, either horizontal, both of them are horizontal, indistinguishable, or distinguishable. And I can reproduce the result. As you can see here, G2 reaches 0. This means that in some instances, when the beam splitter is exactly at the middle of the cavity, and the two photons exactly reach the beam splitter at the exact same time, the Hom effect occurs. And this is a plot associated with the situation actually when we have coherent states on both sides of the cavity, and of course, when we have thermal states on both sides of the cavity. There is a physical meaning here because as you can see, here is kind of a Hom dip occurring here. But we know that for the coherent state, it is a classical state. The Hom effect, the G2 should always be equal to 0. So I'm not going to explain why this Hom effect, this kind of Hom effect occurring here, but if you had any question, I can answer at the end of this talk. But what happens when the system turns open? By using the Born Markov approximation, we will reach the Lindblad-Maxwell equation, of course. Here, the time evolution of density matrix has two parts. First of them is the coherent part, what we had for the closed system, and the incoherent part associated with the open system. As we can see here, we put our system in interaction here. Hot baths and cold bath. The first term here is associated with a situation when the energy dissipation into the bath, and this term here is the energy absorption from the bath.
Sorry, Nadir, could you a bit speed it up, please?
All right, these are the last slides. We have to find the time evolution of the elements of C2 using the Lindblad-Maxwell equation, and as you can see, we will reach this time evolution of C2 here. And I plot the result for two different cases. Imagine that this is the plot for the closed system. For just notice the dot line here, where we have indistinguishability. When we add baths to the setup, this plot would just shift a little bit. Yeah, as we can see here. And also, there's another paper on observation of PT symmetric quantum interference published in Nature Photonics, where they actually imagine that we have two simple harmonic oscillators, only one of them in interaction with a cold bath, and they just described a situation where, as you can see, this dot line here would shift a little bit to the left. I could also reproduce this result too. This is the end of my talk. I just want to shortly talk about what I'm doing now, right now. We are trying to discuss a situation where the enhancement of energy transfer would occur in our system when we are talking about indistinguishable photons. I mean, the hot bath is pumping photon into the system and the cold bath is absorbing photon from the system. And we are talking if the indistinguishability would enhance this situation, this phenomenon. And if it does, then we can include this indistinguishability into quantum batteries. We can kind of increase the efficiency of quantum batteries using this method, using indistinguishable materials. And this is the end of my talk. Thank you very much.
Okay, thank you so much, Nadir, for the impressive talk. So we can take now questions, if any, from our participants. I think no question. I have one question. Is that possible to use this method in quantum computing, something like that?
This whole setup is not actually a physical setup. It is an imaginary setup. Yeah. but I haven't thought about any applications in quantum computing. If we find any effect of indistinguishability in this phenomenon, of course, we can discuss that in different situations when we are talking about different materials.
All right. Yeah. Okay. Okay. Thank you so much.
Pleasure.
For your participation. Okay. Our next speaker is Kemal Haydari.
Hello.
Hello. Yeah. Okay.
Can you hear me? Yes.
You are from Department of Physics, Institute of Advanced Studies in Basic Sciences in Iran. And the title of the talk, Simulation of Optical Coherence Tomography in MATLAB by using angular spectrum propagation and Fresnel equations for multi-layer samples.
Yes.
Okay, you can continue. You can share your presentation.
Okay. Thank you, Doctor. Hello, everyone. Welcome to my presentation. Good evening. My name is Kemal Haydari. I'm a graduate student of physics at Institute for Advanced Studies in Basic Sciences, IASBS, in Zanjan, in Iran. My presentation is simulation of optical coherence tomography in MATLAB by using angular spectrum propagation and Fresnel equation for multi-layer samples. If I want to explain shortly, optical coherence tomography is a 3D imaging method that it's widely used for biomedical applications because it is a non-invasive and non-destructive imaging method, and it's available for in vivo imaging. And here we developed a code in MATLAB to simulate optical coherence tomography. And here I want to introduce the simulation, and we want to use the simulation to improve our analyzing and the convolution methods. So I divided my presentation in 3 main parts. First of all, I will start with an introduction. Here I will talk about optical coherence tomography, OCT, and after that spectral domain OCT. It's one type of OCT, and how to process signals of ST-OCT or spectral domain OCT. In next part, I will talk about simulation and results. Here I will introduce our simulation approach and how to add noises and errors to the simulation. And here for a model, we simulated a human eye. And here I will talk about this. And finally, we will have a conclusion and I will talk about our future works. So there are many methods for 3D imaging, and there are 2 types of 3D images, topography image and tomography image. Tomography image contains text information of the sample, but topography image does not have this. So there are 2 parameters for tomography image, penetration depth and axial resolution. There are many methods for tomography, but here you can see some of them like X-ray, MRI, ultrasound, confocal microscopy, and the other methods. And as you see, every method has its specific penetration depth and axial resolution. And there is a gap here, and it filled by OCT. It means with OCT, we can capture image, 3D image, with penetration depth of about 1 or 2 or 3 millimeter. There are 2 types of OCT, but here I will talk about spectral domain OCT. And OCT is 3D imaging methods based on interferometry. And researchers usually use Michelson interferometer for doing this. And in OCT, we will use a light source with a broadband spectrum like SLD or supercontinuum lasers. As you see, there is a light source here and an optical fiber here to transfer the light of this light source to our system, and there's a collimator here. So we have two arms here, a reference mirror, a reference arm, and a sample arm. And there is a spectrometer here to capturing interference spectrum. It will be something like that. And by some processing, we can obtain the depth information of our sample. How we can process the signal? After detecting the spectrum, we should remove the background, and after removing the background, we had to resample our data. It's necessary because the spectrometer works on lambda or wavelength space, and we had to change our space to wave number space. So we will resample our data, and for increased accuracy of this resampling, we can use zero padding in Fourier space. And by calculating fast Fourier transform of resampled data, we can obtain the depth information of the sample. And with rescaling, we can calibrate our data. Simulation and results. Here is our simulation approach that we use. First of all, we will define the light source and features of our spectrometer. After that, we should define a space for propagating the light. After that, we can define the sample features like an index number or thickness or the other features of sample. After that, we generated two beams with arbitrary features. My mean is arbitrary wavefront, aberration, or intensity distribution. After that, we will propagate the light with arbitrary times of reflection into the samples layer. For propagating the light, we use angular spectrum method. And for calculating reflection and transmission coefficients, we use Fresnel equations. And after that, we can add noises that are effective on optical path lengths, like vibration noise. And then we can calculate the interference spectrum. After that, we can add the other noises, like electrical noises on a spectrometer and the other noises. And finally, we can analyze the interference spectrum. So here I want to talk about the noises and errors we added our system. One of the most noises in interferometry setups is vibration noise. Here in a black line, we assumed there is no noise, vibration noise. So it's like a delta function or something like that. But by assuming a vibration with the range of 50 micrometer for our sample, our data will be, our impulse response will be something like a red line. And by assuming 150 micrometer vibration range of our sample with Gaussian distribution, it will be something like that. Also, we applied a Fabry-Perot effect, and here we have a sample with a thickness of 50 micrometer as an example, with index number of 1.2, and we accept to repeat this distance, its optical path length, as the same distance, and it's accurate, and it works through Fabry-Perot effect on our simulation. Also, we can apply field angle of incidence light and dispersion. For dispersion, we use Cauchy formula, and also we can add spectrometer effects, some things like roll off in OCT. Okay, here is our human eye simulation. In figure A, it's a diagram of our simulation. And here we assumed two parts of human eyes, cornea and echoasis. So we assumed interference speed was 0 degree. And then our interference pattern by assuming an Gaussian noise in our interference spectrum, it will be something like figure B, it's our interference spectrum. And after analyzing this figure, this data, the part of our assumed simulation, cornea and echoasis is obtained here. And after that, we deconvolved this figure by Richardson-Lussier algorithm. So it will be something like figure D. Here we assumed there are dispersion, and for calculating, for assuming dispersion, we used data in this paper. Here we used index number for 3 wavelengths, and then we calculated coefficient A and B and C in Cauchy formula. So we can calculate index number in every wavelength, and we can apply dispersion and the thickness of every part, cornea and echoasis. Here we assumed our wavelength, central wavelength was 850 nanometer, and our bandwidth, wavelength bandwidth was 40 nanometer. And we assumed 50 micrometer vibration range of our sample. And then our resolution was 120 micrometer, and resolution after deconvolution was 80 micrometer. So conclusion and our future works. OCT, as I said, as we know, OCT is a non-invasive and non-destructive 3D imaging method, and it's available for industrial and biological samples. And here we developed an adaptive simulation, and we can improve the simulation and add other features like scattering. And by this code, we can improve the convolution and analyzing method in optical coherence tomography. So my colleagues in this research was Ali Ibrahim Zadeh, a member of our group, and Dr. Ehsan Ahadi Akhlaqi is a leader of group and in optical metrology. Many thanks for your attention, and I'll be happy to answer your questions if there are.
Okay, thank you so much, Kemal, for the interesting presentation. We can now have the questions from our audience, from our participants. Okay, I have one question, Kemal. What's the current situation in this technology, OCT technology?
OCT, OCT is
in the world.
Okay, what is application of OCT? You mean?
Yeah.
OCT is powerful 3D imaging, and it's widely used for biomedical applications, especially in ophthalmology. By OCT, we can capture images from inside of human eyes without it's not a distractive method, you know, and it's there are many applications in biomedical, like the other applications, like dental applications, urology, or the other applications.
It is currently used in medical applications, I mean in hospitals, yeah, at the moment in the world?
Yes, the most applications of it is in biomedical. Yes.
Okay, thank you so much, Kemal. Okay.
Thank you.
All right, thanks. Our next speaker is Mohammed Anjanji. Mohammed, are you here? Okay.
Yes, hello.
From the same department, yeah, Department of Physics,
Exactly.
Institute for Advanced Studies in Basic Sciences from Iran.
Yes.
The title of your talk is Using Mirai Microscope to Nanoscale Calibrate Piezoelectric Actuators.
Exactly.
Okay.
Thank you for your introduction. First of all, let me tell everybody my name is Mohammad Khanjani, not Khanjanji, as you said. But let's begin the presentation. Thank you. First of all, let me share my screen. So, again, hello and good evening. My name is Mohammad Khanjani, a Master of Science student in IASBS from Iran. I'm really proud and pleased to participate at the 3rd International Conference of Light and Light-Based Technology. In this article, we are going to present using Mirao microscope to nano-scale calibrate piezoelectric actuators. Let me bring my laser pointer. Okay. Now, let's go to the overview. We will a little talk about measurement, science, nano-displacement, applications, and piezoelectric as introduction. Then, as a main part, I will explain the main idea of our work. Then we will go to the results and we will have a conclusion then. Excuse me. So when you hear about physics, you might immediately think about measuring or measuring some things or etc. Actually, measurement science or metrology is a basic science that needs to be used in many other fields of science, such as surface topography, calculating refractive index or temperature and etc. It might be used in many measurements, in many sciences, excuse me. In many microscopic methods, such as atomic force microscopy and, I don't know, transmission electron microscope and other ways, such as optical tweezer or acoustic tweezers, we need a sort of tool that displays our object in nanoscale for scanning or other calculating other parameters. One of the most underrated and precious elements for this cause is a piezoelectric transducer. First of all, let's talk about a piezoelectric a little. First of all, what is it and where we can find it? As you see in the picture, piezoelectric element is a thing that causes the spark in lighters, common lighters. So it is not difficult to find it, but what is its applications and where we are using it and why are we talking about it in here? So this crystal can convert the mechanical displacement to potential differences and give us electricity that we saw in the lighter, or can convert the potential and give us displacement. It can also get potential differences and give us displacement or reverse. So this is the real picture of piezoelectric transducer, or we will call it later PZT. So advantages and disadvantages of these piezoelectrics are we can use this piezoelectric transducer as a nano and micro scale and displacer. We can use it for automation control with many devices. But on the other hand, it got non-linear behavior, and in some cases, maximum course of displacement is not enough. So we should figure out how to overcome these problems. So let's go to the next page. And So for studying the non-linearity behavior of piezoelectric transducer, we obtained some strain gauges and created some Whetstone bridges. I forgot its name. As you see, we use some strain gauges and create a Whetstone bridge, and so we can calculate the nanoscale stretches. And for this study, we use these, and this resists when you stretch it. The resistance of strain gauges will be increased or decreased. So we can find the stretches and nano and micro scale displacements from its resistance. But and therefore, a precise system is needed to determine the nonlinear behavior of output of the strain gauge due to the change in pz lengths. And finally, we have an accurate linear output of displacement. Mirror interference microscope is what we use to obtain this cause and observe the displacement change based on interferometry. This setup is what we built and we use, as you can see. But for more information, we will go on the schematic of this setup and discuss further. And discuss equations and what is really happening. As you can see, we use a helium neon laser as our light source. And after that, we used a rotating diffuser to reduce the effect of speckles and unwanted diffractions. Then we focused the beams to mirror objective, as you can see, and after that we could have interferograms and have interferometry. Why we can't see interferograms only with one arm of interferometry? Because we are using mirror microscopy objective. Mirror microscope objective actually got one beam splitter inside it and one reference mirror, so we can have both arms in one arm. Exactly. So as interferometry says, we got two electric fields came from object and referensive mirror. First of all, let me show you how this all work do. We got a setup, we got a laptop, and got a piezoelectric driver that controls the pz, as you can see, and we can move the mirror objective, so we can have different view of the our testing object. As you can see here, when it is going up and down, we are having some interferograms, and here we are singly watching one pixel of this CCD that collects the data of interferograms. So let's go to equations and talk a little more. By merging two intensities and electric fields to this beam splitter, we actually got the interferograms, and by receiving them from CCD, we can find phase and calculate the height differences of each phase shift steps caused by piezoelectric transducer that we are ordering from a piezoelectric driver. So we can see the stretches and other movements of this setup. In addition, it is important to mention that because of sensitivity of our work, especially vibration sensitivity, we reduce the vibration from 15 nanometers to 0.7 nanometers only, but by using optical table. As you can see, this is the equation of interferogram, and we are collecting data. This is the intensity, this is the intensity, this is the optical path difference. When it is going further and further, we see different view of interferograms, and finally we obtain the heights of the difference height of the piezoelectric that is stretching. Okay. So let's go and see the results of this experiment. In the first figure, as you can see, we recorded intensity changes of 0 to 150 volts that divided in by 0.1 volt steps, as you can see. As you can see, the plot is going up and go down. The bottom of it, it means a darker pattern of interferogram, and the top of this this plot means the lighter version of that plot, that interferogram. So let's after that we use this data to obtain the nonlinear behavior of piezoelectric transducer and sense how much one step in volt caused the real-time length change of a PZT actuator. As you can see, in the middle of this plot, it needs more voltage to do more displacement, but at the beginning and at the end of it, it needs less and fewer voltage to do same displace the piezoelectric, I mean. And at last, we use this information to calibrate the piezoelectric driver based on a strain gauge sensor's output, as you can see. And then we achieved a precise displacement tool for further studies. For example, we are using this in white light interferometry, white light phase shifting interferometry, and phase shifting interferometry, and multi-wavelengths interferometry. The last picture is our calibrated piezoelectric and its driver, control driver, and this is the mirror objective. So we have a precise device that can help us for those further studied, as I mentioned. Thank you, and I wish this lecture could help you. If you have any questions or you want to contact us, feel free and contact us. As I mentioned, we are working on white light interferometry, phase shifting interferometry, and etc. And thank you. Any question I can help you, I will be glad to be here.
Thank you so much, Mohammed Hanjani, for your interesting talk. We can now have questions from our participants, if any. I think there is no question. Okay, thank you so much, Mohammed, for the presentation. Okay, thanks. Our next speaker is Ali Ibrahim Zadeh.
Ali is not here, Professor.
All right, okay. Then,
thank you.
Okay, then the next one is Mehdi Rameh. Mehdi?
Hello.
All right, hello. Mehdi is from Department of Physics, Institute for Advanced Studies in Basic Sciences, again from Iran. The title of the talk, Acoustic Trapping of Large Microparticles. Okay, can continue. Okay, thank you.
Can I start?
Yeah, sure, you can start.
Okay. Thank you, your introduce. Hello, everybody. I'm Mehdi Rameh from Institute for Advanced Study in Basic Sciences in Zanjan, Iran. Today, I'm going to talk about acoustic trapping of large microparticles. First, I'm going to talk about optical tweezers, limits of optical tweezers, acoustic tweezers, and then comparing acoustic and optical tweezer. After that, I'm working to talk about our work, simulation, setup, and results. By focus laser, a single laser beam can use be trap, move, hold, and move microscopic particle, provided that its refractive index is larger than the surroundings. In 1986, Ashkin and his colleagues trapping the particles that today call optical tweezers. For levels of optical power that do not damage cells, these forces are very small, typically on the order of piconewtons. This force may be so small in the macroscopic world, but this is not the case for macroscopic particles. The force applied to the particle is linear with respect to its displacement from the center of the trap, as long as the displacement is so small. In this way, an optical trap can be compared to a simple spring which follows Hooke's law. This is a base for this is a force on balance between a scattering force in direction of light propagation and gradient force in direction of intensity gradient that force toward the center of the trap. Although optical tweezers have excellent precision for trapping the particles, but Ashkin optical trapping has its limitation. They may cause physiological damage to cells and other biological objects from potential laser-induced heating. And for large and heavy specimen or application of single beam, optical tweezer becomes problematic. An example of large living specimen, which can be trapped by acoustically, but not optically, is the tardigrade shown in this movie. This specimen, which measures about 190 micrometer by 50 micrometer in size, can't be trapped by optical tweezers. Acoustic tweezer trapping the particle similar to optical tweezers. The particle size that can be trapped is the order of acoustic wavelength. We can trap particles in the range of micron to millimeter by acoustic trapping. Waves not only transport energy, but also convey momentum and thus can exert forces. A wavelength of a sine wave can measure between 2 points with the same phase. When the waves go back and forth, the distance between the two nodes is half the wavelength. At frequency 20 Hertz to 20 kilohertz, we can hear the sounds. It's a hearing threshold. At a frequency about tens of kilohertz, we can trapping the particle in order of millimeter. At frequency about a few megahertz, we can trapping a particle a few hundreds of micron. And by using this device, high frequency transducer, we can trapping the particle about a few micron. When we apply a radio frequency to interdigital transducer, IDT, generates surface acoustic wave, SAW. The interference between them, the ascending surface acoustic wave establish radiation force, establish pressure field in the medium. This field generates acoustic radiation forces that act on particles. The acoustic radiation forces drive particles to nodes or antinodes in the acoustic pressure field, depending on the particle properties. Most particles are pushed on the pressure nodes because particles compressible than the medium. When we change the frequency, the pressure node change, then the particle move. One of the application of acoustic tweezer is trapping 1 millimeter polystyrene bead by acoustic transducer. This is acoustic transducer. These acoustic transducers work at tens of kilohertz and trap the particles in the order of millimeter. The another of is trapping living specimen about millimeter size. The elegance work before and after being fully stretched by acoustic trapping. And sorting the particles 2 and 10 micron polystyrene bead by pressure nodal lines is another interesting application of acoustic tweezers. Also, we can rotate particles, for example, pollen grain, as you can see in this movie, by acoustic tweezers, and can move and control and trap 10 micron polystyrene bead by acoustic trapping. Here, I want to an important difference between optical tweezer and acoustic tweezer. In optical tweezers, the refractive index of the sample is usually higher than the surroundings, which means that the gradient force pushes the sample into a maximum of the electric field. By contrast, for acoustic tweezer, especially for trapping of any solid or liquid in air and for most cells in water based biological media, the sample is expelled from high pressure region, antinode, and drawing to a pressure minimum node, antinode and node. Optical force is typically in order of piconewtons, and acoustic force typically is order of nanonewton. The force is equal power by velocity. Then the ratio of acoustic force to optical force, in principle, we explain by the ratio of the velocity of light to the velocity of sound. But in optics, we can focus only incident power by high numerical aperture lens into a particle volume. Whereas a particle trapped by acoustic tweezer is typically much smaller than the acoustic wavelength, and we can't use all the incident power. The use of tens of kilohertz in air for the manipulation of object in millimeter size, as well as at megahertz in liquid for manipulation the particle about micron region. We simulated 2 acoustic waves in water. In this simulation, we used 3 parameters: amplitude, frequency, and phase. By adjusting amplitude, we can set a magnitude of pressure node, and by adjusting frequency and phase, we can move pressure node. When we apply a phase difference, the pressure node move, and as a result, we can move trap particles. The displacement of pressure node approaches phase difference. As you can see, this is our setup. This is first function generator, driver illumination, oscilloscope, second function generator, arrow illumination, condenser lens, acoustic device, objective, mirror, CCD, arrow detector. The acoustic device contains an aluminum holder with 2 piezo transducers placed opposite each other to transfer acoustic wave inside a liquid chamber. We can trap the particle by adjusting frequency and amplitude. As you can see in this movie, we can trap 40 micron polystyrene bead in mixture of water and glycerol medium. In this picture, we have 11 pressure nodal lines. We can trap and control this particle in pressure nodal lines. In red circle, we can trap and hold polystyrene bead, 40 micron polystyrene bead by adjusting frequency and amplitude. When we change frequency faster, the particle move faster. When we apply phase difference, the pressure nodal lines shift up, and when phase difference is 0, the pressure nodal lines shift down, and we can control and trap the 40 micron polystyrene bead by pressure nodal lines and move this particle by apply phase difference. We can rotate a symmetric 80 micron polystyrene bead by applying phase difference. Due to the asymmetric shape of the particles, the top and bottom of the particle do not the acoustic radiation uniformly. So the particle rotate. This is our group, Dr. Akhlaqi, head of optical metrology group, and Dr. Hajizadeh, head of optical tweezers group. This picture shows physics department. Thank you for your attention.
Thank you so much, Mehdi, for your presentation. We can now have the questions from our audience. I have one question, Mehdi. What could be the application fields of this?
We can trap biological and living specimen by acoustic trapping, and we can trapping this particle from size about micron and millimeter.
Okay. Okay, thank you so much.
You're welcome.
I think, okay, Ali Ibrahim Zadeh is here, I think. Sorry about that, Ali, we missed you.
Yes.
Okay, you will be our final speaker, okay?
Yes.
You are from the same Department of Physics, Institute for Advanced Studies in Basic Sciences from Iran. The title of your talk is Simultaneous Thickness and Group Index Measurement of Multilayer Thin Films with Spectral Domain Optical Coherence Tomography.
Yes.
Yeah, okay. You can share your presentation and start, please.
Yeah.
Yeah. Can you make it full screen, please?
Okay. You can see my...
Yeah, we can see it. You can make it full screen, please. Yeah, okay. Thank you.
Thank you. Hello, everyone. My name is Ali Ibrahim Zadeh. I'm graduate student of physics at ICPS, and I am also a research assistant of Dr. Akhlaqi. In this article, we work on the simultaneous thickness and group index measurement of multi-layer thin films with spectral domain optical coherence tomography. We present a spectral domain optical coherence tomography method to determine the group refractive index in the geometrical thickness of the multi-layer transparent thin films simultaneously. My presentation will take about 12 minutes, and I hope you enjoy this talk. I've divided my presentation in 3 parts: introduction, and method, and result. In the introduction, I will start with a brief explanation of the thickness and refractive index and the importance of measuring them. And in the next part, I will explain OCT and our experimental setup.
And finally, I'm talking about our result in scanning 2 and 3 layer samples. Measurement of geometrical thickness and the refractive index of the different sample is always a challenge in research and industry. The refractive index is one of the substantial physical properties that are significant for optical design and metrology. It can be changed by exterior conditions such as electric and magnetic fields, tension, temperature, etc. This gives rise to a variety of methods that can measure these physical quantities with the help of measuring the refractive index. Therefore, measuring the refractive index and physical thickness of various samples such as thin films, glass plates, and living tissues are always consequential. Numerous methods like interferometry, diffractometry, reflectometry, and confocal microscopy and optical coherence tomography are developed to measure refractive index and physical thickness. Each of these approaches has a particle resolution and penetration depth that prove superiority for a specific application. However, simultaneous measurement of refractive index and physical thickness is still a challenge in optical metrology. In this work, we can measure refractive index and thickness by one-time data acquisition. OCT is a technique with low coherency light that works based on white light interference. Using interferometry, the object under the investigation is examined point to point. This method will analyze the light phase information, gives deep information of the sample. OCT works with Michelson interferometer. And there are two methods for this technique, time domain and Fourier domain. In the time domain, the light comes from optical source with low coherence, then by one beam splitter divided in two beams. One of the beams hits the reference mirror and reflects. The reference mirror is movable to scan different sample layers. Another beam hits the sample and reflects, and finally two reflect beams interact with each other. By analyzing interference fringes, an image of the sample is obtained. In the other hand, Fourier domain, reference mirror is fixed, and to scan different layers of sample, a grating for separation different wavelength is used before the beam splitter, or detector which usually use the spectrometer that has a grating. The advantage of this method is the high speed of data acquisition and noise reduction, or the same increase the signal to noise. In this paper, we present a simple and cost-effective method to measure the group refractive index and the geometrical thickness of optically transparent multi-layer thin films simultaneously, without any previous knowledge about them. The method used a common spectral domain, Michelson-based optical coherence tomography setup. The sample is positioned through to the one arm in dual arm interferometer rather than the ordinary position of sample in OCT that is shown in the left figure. As you can see in the right figure, and according to the reciprocating path of light and the optical path difference, we have this equation for delta R and delta L. Also, the sample rotates about an axis perpendicular to the beam propagation path at specific angles and provides more information about itself. By using OCT theory, rotation changes coefficients in the equations. Refractive index and geometrical thickness of each layer of multi-layer sample can be determined by solving this system of equation. To test the method, measurements were carried out in multi-layer samples of PDMS on the cover slip, SU8 photoresist on the cover slip, and PDMS SU8 on the cover slip. This figure illustrates the result achieved for the sample of PDMS on the cover slip. That A shows an interferogram of the sample. The Fourier transform signal in B presented several peaks that are delta R and delta L by 20-degree rotate. And this figure shows repeated measurement result of the total geometrical thickness and refractive index of this sample. And as you see, thickness and refractive index for PDMS and cover slip have been achieved. The figure show result obtained with a sample of SU8 photoresist on the cover slip. And this figure illustrates the result achieved for repeated measurement result of the total geometrical thickness and refractive index of this sample. Finally, this figure shows the result obtained from 3-layered sample of SU8 on PDMS on the cover slip. To measure the refractive index and geometrical thickness of each layer, sampling should be at 3 different angles. And also this figure illustrates the total geometrical thickness and refractive index of the 3-layered sample for 10 repeated measurement at the stationary point. We compared this data, which are the thickness and refractive index of the 3 samples, with the data obtained from white light interferometry, which obtained a large agreement. To sum up my talk, we proposed a cost-effective and simple method based on optical coherence tomography configuration to measure group refractive index and geometrical thickness of plane parallel optically transparent sample, simulate landscape. Puri Omidi and I worked on this article in collaboration with Kamal Haydari and supervising Dr. Akhlaq. Thank you for your kind attention, and I hope it was a useful presentation.
Yes, it is. Ali, thank you so much for your useful presentation.
Thank you.
Okay, we can have questions, if any, from our participants.
Okay.
All right. Okay, Ali, thank you so much.
Thank you.
I think we finished all the speakers, so we are going to finish this session. I would like to thank all the speakers and participants who followed the session, the speakers, the presentations until the end of the session. Thank you so much to all the participants following this session. I think without any break, we are going to continue another session. Okay, thank you so much.
Okay, so here we are with the 5th and last session of this conference today. We will start with 2 invited talks and continue with 6 contributing talks. And our first speaker of the day is going to be not Professor Rubinstein, because she already gave an excellent talk. We will have instead now replacing with Professor Akhlaqi from Zanjan, and he's been advising many of the former graduate students that we have listened today. Now we will have a chance to listen to himself. And Professor, thing is connecting. I think you're still muted. Okay.
Hello, thank you for your introduction. Could you hear my screen? See my screen?
Yes, perfect.
Okay. Let me I start my presentation. Thank you for your introduction, and also would tell my appreciation to the Applied Sciences faculty and the Photonics Research Center of Gazi University for their invitation, especially to the scientific and executive committees headed by Professor Suleiman Özçelik. Yesterday, there were valuable talks about the basic of optics and its application, especially in measurement. And today there will be good talks about the structural light and the construction of nanoscale devices. Also, before me, my group's members presented their talks about optical metrology methods. In our group at the ISPS, we research about optical measurement methods and try different optical techniques to increase their accuracy and quality of optic outputs and generally improve their features. Accordingly, we design and implement different measuring devices for production. Currently, these sections are active in our group. Bioimaging and fluorescence microscopy, digital holography and macroscopy, optical coherence tomography, and diffractometry. Between these topics, I have chosen diffractometry as a practical, accurate, and simple optical measuring method to present. Based on information that I have about the audience, I know here we have a wide range of audience from undergraduate students in optics and photonics to experienced professors. And therefore, to give an attractive presentation for this wide range is difficult. However, I try to address both basics and results. First, I will review history and origin of the diffraction, then theoretical basis, and finally introduce the works we have done in our group. Okay. When a light beam changes under the influence of an absorbing aperture, which abruptly changes the light wave parameters such as phase, amplitude, and the polarization of the light, the intensity distribution changes against the prediction of ray optics. It behaves like this, in which the intensity of some areas is more than the average intensity, and in some areas where the ray optic don't predict the presence of any light, the light intensity can be detected. These changes depended on the propagation distance, which usually is divided into two regions, near field as a Fresnel diffraction and far field as a Fraunhofer diffraction. But when a beam of light changes under the influence of a semi-infinite aperture, the light intensity distribution is changed, but it is not dependent on the propagation distance. And now we have just the Fresnel diffraction regime for all the space. Okay, after this brief origin of the diffraction, let me talk about the history of it. Diffraction is a fundamental phenomenon in optics that has been considered for a long time. Historically, the Italian scientist Francesco Grimaldi was the first to report this phenomenon and called it diffraction. And other scientists, such as Fresnel, Fraunhofer, and Maxwell, improve our knowledge about it. As the calculation of diffraction were complicated until 2 recent decades, no special attention was paid to it. But in the last 2 decades, thanks to expansion of the use of computers, more attention has been paid to use of diffraction and its applications. Tabassoli and his colleagues were the first to pay a special attention to this issue and have presented several papers to introduce its formulation and its application in the field of optical measurements, such as determining the refractive index of liquids and solids, the spectrum of light sources, and the thickness of thin layers, and so on. Almost of all these works have been based on the use of a phased step. Okay, now we review a brief history of the diffractometry, and at first, let me review the basis of the diffractometry from the phased step. Phased step is a transmitting or reflecting plate that causes an abrupt change in the phase of light, such as a transparent plane parallel plate with a smooth edge as a transmitting phase step, or two mirrors with axial distance as a reflective phase step. Also, the diffraction pattern depends on the wavefront of the incident angle, incident light. For example, here, in the right figure, the diffraction pattern of a cylindrical wave from a phase step can be seen. The use of the phase step diffraction gives the advantage of obtaining more data about the understudy sample, so it can be good candidate for the basis of the optical metrology methods. The diffracted field can be interpreted and formulated based on the wave optics. According using Fresnel-Kirchhoff integral, the optical field on the second plane can be determined based on the optical field at the input plane. We can write the integral for a plane wave illuminates as a reflection phase step as like this equation. Here, C0 and S0 are the Fresnel integral, and the delta phi is the phase difference between the two reflected beams. Delta is related to the wavelengths and corresponding the incident angle and phase step height. In the transmission mode, in addition to the parameters related to the reflectance mode, the refractive index of the environment and the phase step are also involved in the phase difference. Now we can know the behavior of the diffraction pattern against the parameters of the system. And next, we want to find a way to extract the data from the diffraction pattern. Assume a plane wave illuminates as a phase step. The intensity distribution changes depends on the phase difference of the phase step. So that when the phase step difference is equal to the P, the intensity changes intense around the average, and by changing the phase difference to 0, the amplitude of variation decreases. And these figures show this behavior. Therefore, by defining the relation for visibility in this way, a plot can be obtained in which the vertical axis is the visibility and the horizontal axis the phase referring to the phase step. And by measuring the visibility in terms of phase difference, various parameters such as refractive index, thickness, and wavelength can be obtained. Okay. In our research group, we use this method to measure various parameters, such as determining the thickness and refractive index of thin films simultaneously, and 3D macroscope imaging, and precisely determining the fractional part of topological charge of vortex beams, and also introduce a new source of Fresnel diffraction, which I will try to review each of them briefly. At first, we said the diffraction occurs due to the abrupt change in phase, amplitude, and polarization of light. But here, I will introduce a new source of diffraction, which means that despite just the singularity of the phase gradient, diffraction also occurs. We have all seen Fresnel's double mirror in textbooks as an interferometer model that creates an interference like these fringes. But if we look at it as a diffractive element and write the Fresnel's integral equation